well. Let me go online. So yeah, I think we'll go on. Yeah.
But the Ron is still on, right? I cannot share,
No,
right?
I killed my screen sharing.
Okay, okay, let me
So
see.
you should be
Okay,
able to get yours on.
I don't get my on. That's the problem.
Let me say. Let me
Do
make
you see
you.
mine?
Yeah, I think I don't see the share screen.
Yeah, let me share my screen.
Yeah.
Okay, share screen. I don't see. How can I?
You might have to take your mouse near the bottom of the window, and then there's a green box that says share screen.
I cleaned that. It's an. Let me see. Let me do it again. Okay.
Mm-hmm.
I cannot share. That's so strange.
Does it give you an error message?
No. No
What?
error message.
What do you press share screen, or do you not see
I
it?
press the share screen.
Then what happens?
Okay. I don't have. I have a one. Okay. Why it does not give my screen? You only have a computer only portion of the screen. Let me see.
Now we see it.
Yeah.
You're okay now.
Yeah.
Okay, let me see.
Well,
Some big blue
Let me
blob.
open.
Yeah.
well, we
Let me open with my.
Yeah.
Can
Looks
you see
good.
my-
Yeah, but looks on the left.
Let me share my full screen.
Mm-hmm.
Yes,
Yeah,
okay.
Perfect.
Yeah, perfect.
Perfect. Okay, I stop sharing. Give it back to Ron.
Okay.
Okay.
I'll be next because I'm going to do a short presentation before we start. So Guang, can you make me co-host?
Oh, sure. I will do that. Let me say, okay. Yeah.
Okay, so yeah, we'll maybe just wait a couple minutes and then I'll start with a few opening remarks.
So how tight are you guys trying to keep to the schedule? Because you have a very compact schedule here. You don't have any time in between talks to
Yeah.
argue.
We have some time between the morning talks, so maybe we
So
can.
you're anticipating running over, I guess, a little bit.
Mm-hmm.
But ideally, maybe you would stop like 5 minutes before your scheduled ending time, so we have some questions.
Yeah, I'll try to do that. But I talk very slowly, so.
That's good. Yeah, that's good. Everybody understand.
So it's a 12-hour difference from here, from Singapore and Purdue, or from
Yeah.
Yeah.
Sure.
your morning 8 o'clock something.
Yes.
Yeah.
Mhm.
Oh, okay.
Yeah, we're glad you could join us.
I will go sit in the talk until noon, midnight. Then I go sleep. I will
Yeah.
skip afternoon talk. Yeah.
Well, they'll be recorded, so it's okay.
Oh, you're gonna record it. Okay. So you're going to put on the conference webpage or whatever.
Yeah.
Yeah, we will send out email to ask for your permission. If you agree to put it that on the web page, we'll put that.
Okay. So good thing is that your audience can be all world around. That's a good part for the online conference.
Yeah.
How many people can you accommodate?
We've got 300 here on Zoom, and then people can also watch on Facebook Live or YouTube live streaming.
Yeah, we have
Yeah.
about 600 people registered.
How many?
600 up, like 650.
Well, did you get $10 from every one of them? Hi, Jintel.
Oh, hi, good morning.
Hello.
Because of the speakers.
Hi, Jin Cao.
Hey, good morning. Oh, no, good evening. Yeah.
Good day, good day.
I have some trouble to get into this room. Okay. Wait a minute, did you change the room or what?
Yeah, change the link.
Oh my gosh. Okay, I was, okay, I'm in. I'm just. Oh, there's one of a lot of people.
Yeah, all right. So it's, as Ron mentioned, we have a pretty tight schedule, so maybe I'll get started with a few welcome remarks. Just a reminder, if you're not the speaker, then you should mute yourself. So if you're not the speaker, you should mute yourself. And I will start off here. Okay, so it's a pleasure to welcome you all to our IMA supported workshop on mathematical foundations and applications of deep learning. We've got great talks today and tomorrow. I just wanted to make a few brief welcome remarks, and then we'll start with our first talk in just a couple minutes. So just a little history, since we're talking about neural networks. I guess you can trace the history back in various ways, back to Hebs or whatever, but in some sense, neural networks or perceptrons were developed by Frank Rosenblatt in 57 with a grant from ONR. And there was hype already at that time. So the New York Times said the Navy thinks it'll be a computer that will be able to walk, talk, see, write, reproduce itself, and be conscious of its existence. So these were going to solve everything. Not that much later, Minsky and Paper said that the predictions were grossly exaggerated. And so this whole cycle led to kind of some periods of boom and bust for artificial intelligence and machine learning, et cetera. But at this point, starting in maybe 2012, after kind of a long period of kind of development in the background, deep learning led to a lot of amazing results and successes. So here are just a few examples of the kinds of things that we can see using neural networks at this point. So they've had a huge impact on society. They're continuing to have a huge impact on society, both for good and sometimes not so good applications. So, it's a little bit hard to say. It doesn't seem like, the bubble is going to completely burst the way it has in the past, because we've already had such amazing results, but it might not continue exponential growth for a super long time. So we'll have to see how things develop. And even at this point, there's still plenty of hype. So back in the original 57 announcement, the Navy said it was going to be great. Here, just 2 years ago, March 2018, well, maybe 3 years ago now, Stanford Magazine said in 2 years, there could be 10 million self-driving cars on the roads. I'm pretty sure there aren't that many self-driving cars on the road at this point. So, there's always a lot of excitement, but then, in the end, we have to get back and do the math that underlies successful results. And that's where this workshop comes into play, because we really want to develop the foundations, mathematical and engineering foundations, that can lead to neural networks that are reliable, quantifiably accurate, and efficient. So, we want to have guarantees about the kinds of approximations we get. We want to have effective and efficient optimization routines and bounds on those results, et cetera. And we have a terrific group of speakers today who are going to touch on many aspects related to those ideas. We also have contributed talks on both evenings. And so we've got this Zoom presentation, and then There's also live streaming on YouTube in case we run out of capacity on Zoom. So with that, let me just do one bit of shameless advertising. Purdue is investing a lot in data science. So are many other places. But since I'm part of Purdue, I'll just point out that we are hiring new faculty. We have a very supportive dean of the College of Science who's investing a lot of money into data science. We just have approval for the development renovation of an existing building into a new data science building with kind of a conceptualization here. There are lots of initiatives in data science and machine learning, in math, computer science, statistics, and across engineering. And like when I came here 20 years ago, West Lafayette was not considered the place to be, but it's improved a lot. And so just recently it was rated #1 by something called Smart Asset. Unfortunately, they put the ET on there, it might not be so appropriate. But Smart Asset rated West Lafayette as #1 in the best places for career opportunities in 2021. There's a lot of investment going on here in aerospace. Engineering is great. And from the point of view of math and data science, that provides a lot of opportunities to not only develop data science, but also see it applied in practice, working with engineers and companies and making sure that we really do develop methods that are reliable and quantifiably accurate. Okay, so let me just finish with a thanks to the Institute for Mathematics and its Application for funding this conference. Thanks to all of the speakers and to the attendees. We have more than 600 people registered. Thanks to Guang and especially Haizhao. Haizhao did nearly all of the organization for this conference, and we're really appreciative of that. So welcome to you all, and I hope you enjoy a terrific workshop. All right, so with that, I will turn it over to our first speaker, Ron DeVore. And let me just, right, so with that, I will turn it over to Ron DeVore, who is the Walter E. Koss Professor and Distinguished Professor of Mathematics at Texas A&M, and he'll be discussing thoughts on deep learning.
Thanks, Greg, for the introduction. I'm now looking for the file that I had so nicely before. Anybody see? I see Purdue.pdf, but I don't think that's the right file I want, but I will try it. No, that's in Tech Shop. Can you guys see this?
Yeah, we can see
Yeah.
the PDF file.
Okay, so I guess I'll give the talk from this file, even though I wanted to give it from Adobe PDF file. All right, so let me begin by saying I used to spend a lot of time at Purdue with Brad Lucier, and I have very fond memories. I haven't been there in probably about 10 years, but Purdue lives close to my heart. So in regards to this learning, I've been trying in the last several months to get my arms around deep learning. A lot of the ideas are sort of counterintuitive to me. And so this talk is a mathematician's view of the problem, and hopefully it'll illuminate some of the foundational issues in this area. So what is the learning problem? To me, it's the following. We have some unknown function f that I'll assume is real valued, and we have some data about f. And from that data, we want to construct a function f hat, which I think of as an approximation to f that will predict what f looks like away from the data. you can keep in mind a very simple example where your data comes from an interval 0, 1, and you have a univariate function. This is not, very much not, the typical problem we address in deep learning, but it's still a useful toy example to keep in mind. The real applications are in very high dimensions, where the function is a function of d variables, where d is huge. Typically the number of pixels in an image, for example, when you're doing classification and the like. I'm going to assume that the measurements are noiseless. You can put a layer of noise on top of this if you like, but I like to separate the issues of noise and noiseless because I think it illustrates more easily what's going on. So let's begin with the mathematical formulation of the problem. How would a mathematician view this problem? First thing, if somebody came into his office and said, hey, I have this data and I want an algorithm to tell me what the function looks like away from the data, mathematician would say, well, look, I can't tell you anything unless you give me some extra information about f, because it could be anything away from the data. This extra information we typically call model class information. So if you're solving a PDE, this may be some regularity results for PDEs, or if you're in another domain, you should try to extract what information you actually know about the function you're trying to find. So that's the first point. And this is rather important because in deep learning, frequently you don't see model classes, at least explicitly discussed. Sometimes you do, sometimes you don't. Another issue, a mathematician would say, well, please tell me how we're going to evaluate algorithms at the end of the day. If I come up with this clever algorithm and I think it's a great way to recover this f, that is to create this function f hat, how are we going to decide whether I did a good job? And in mathematics, we like to do this via some norm. And so that's what I'll assume, that there is assigned to me a norm, how we're going to measure the error after I've created f hat. Namely, I'll look at the deviation between f and what I've created in f hat. And I'm going to assume that this norm is a Hilbert space norm, although whatever I say can be carried out in a general Banach space norm. And you can look at this paper here to see how that's done. The data I'm going to assume are given by linear functionals applied to f. So it's linear data. And so what do I know about f? The totality of information I know about f is that it's in this model class K and that it satisfies the data. So I let KW be the collection of all functions in K which satisfies the data. That is all I know about f. It could be any function in KW as far as the information that was given to me. Well, given the setting, there is actually mathematically a very easy description of the best recovery that you can make. That is the best approximation f hat you can give to f, given that f is any one of these functions in KW. And it's most easily explained by a graphic here. So let's let KW be this blue set. So the blue set here in this graphic indicates all functions. So this is in my Hilbert space, all functions that satisfy the data and lie in K. So this is the set KW. The best I could, that's all I know about f. So the best I could do to approximate f is to take the center of the smallest ball that contains KW. This is called the Chebyshev ball, and its center is Chebyshev center, and the radius is the Chebyshev radius. And that's the best error you could ever attain. And the best algorithm would take your data and find U star. How to do that numerically is a big issue, but that would be, if you could achieve that, be the best algorithm. In reality, this is a very hard problem to find U star, and we do surrogates to that problem. And we would be happy if we found any point close to this ball. In particular, if we found any point in the ball, we would know we were within a factor 2 of the best performance, and that would be satisfactory to us. Okay, so there is an optimal solution, and the optimal error you would get is this R star of R of KW, the radius of this ball. Hopefully everybody followed that. All right, now let's try to understand, what does the data give? What does the data tell me? Since I'm operating in a Hilbert space, the data are linear functionals in the Hilbert space, and so there's something in mathematics called the Riesz representer theorem that says every linear functional is the inner product with an element omega j from the Hilbert space. These are called the Riesz representers of this data functionals. So I could take these omega j's, which ostensibly would be known to me. For example, if you think about point evaluation, you may think of the delta function as the omega j. I can form the span of the omega j's. This is a subspace of my Hilbert space. And the information I get from the data, it tells me what the projection of F is onto this finite dimensional space W. So it gives me the projection of F onto W, which we denote by PW of F. What I don't know is how F looks away from the data. And that mathematically is, we don't know the component of F in the direction of the orthogonal complement of W, called W perp. And what we want to do is we want to use our knowledge about F to predict what PW perp of F is. So that is in essence the problem. What is F off of the data? What does F look like in this W perp direction? There's a simple graphic to explain here what's going on. In this graphic, there's a blue blob here, a three-dimensional blob. I mean, the graphic is in 3D, so it's not very illustrative of the high-dimensional problem. But the blue blob is my set K, right? That's my model class. I know F is in the blue region here. What does KW tell me? It tells me that there is in general, hyperplane cutting through this blue blob. In my 3D example, this is just a line segment. These are all functions. If you extended the line off to infinity in both directions, this would be all functions that satisfy the data. And what I know is that F is on this line segment, on this line, but I also know it's in K, in the model class K, so I actually know it's on the line segment that enters K and then exits K. And so F is any point on this line segment. And as we already discussed, the best we could do to recover would be sort of to take the midpoint of the line segment in this case. Okay, so that's our problem, to find what is the component of F in this W perp direction. Now so you would say at this stage, well, it's a lot of mathematical nonsense. It doesn't tell me a mathematical algorithm or a numerical algorithm to actually do the job. How do I find the center of this Chebyshev ball? So let us now entertain what are possible numerical algorithms. Of course, the best and most commonly used is least squares. What would you do in least squares? You would find a space sigma here, a finite dimensional, typically a finite dimensional linear space, and try to solve this problem. Look at all functions in this linear space and find one that's close to satisfying the data. And in the old days, we always took the dimension of the space smaller than M. Our rationale was we didn't want to fit noise if we had noisy data and various things. So we took the dimension to be less than M. In current deep learning, one typically takes N a lot bigger than M, over parameterized deep learning, right? And moreover, you don't take sigma to be a linear space, you take it to be a nonlinear manifold. So the typical setting in deep learning is to take a nonlinear manifold with a number of parameters much larger than the number of data points. So here now you're going to have non-uniqueness. And so which of the functions, you're going to have many functions that are going to give you error 0 here. So which of those functions are you going to pick? That would be, to me, the question to ask somebody in deep learning. What function are you choosing if you're using over-parameterized manifolds? Which function are you choosing to fit the data? I know I can fit the data exactly. Which guy are you going to choose? So I'd like to understand what's going on there. Now, if you think, first I want to tell you that least squares absolutely does not meet our goal. If you try to analyze least squares and say, okay, I pick a space sigma and I do least squares, can I prove anything in terms of the function that I've created, f hat, matching my goal of being a optimal or near optimal algorithm for learning in terms of giving me an error that's close to the best error I can achieve, which I discussed on the earlier slides? The answer is no. And the reason is that although you may have used this model class K in the beginning to choose your space sigma or your manifold sigma, you may say, oh, I'll choose a sigma that approximates the elements in K very well. So even though you've done that, after you've done that, when you do least squares, you throw away completely your knowledge that F is in K. So when you solve this problem, K is not appearing. You've only used K to select sigma. So the bottom line is least squares does not fulfill our goal. Is there a remedy? And the answer is yes. Penalized least squares will do the job. So what is penalized least squares? So let's take our model class K, and let me assume, and you can get around this, but for the moment, let me assume that this set K, this model class, which is a set of functions in the Hilbert space, I want to assume that this model class is convex and symmetric about the origin. In this case, and this is rather typical, by the way, of most model classes like Sobolev spaces, Besov classes, and Barron classes in your deep learning and the like are all strictly convex and symmetric about the origin. In this case, you can view K as a unit ball of a Banach space Y, which is a subspace of H. In fact, you define Y via the norm on Y is defined via K. K would be the unit ball of that norm. So if you view it in this way, then if you solve one of these two constrained optimization problems, then you would have a near optimal solution or an optimal solution. What are these constrained optimization problems? Now, they're not numerical because I'm going to look at all functions in the Hilbert space that satisfy the data, and I'll find the one which minimizes the norm of G and Y. What does that mean? That since I know that my original function F, which beget the data, was in Y, this function f lambda hat will actually be in K, will be in the model class. So this will be a function in the model class, f lambda hat, and it will satisfy the data. So it lies in that Chebyshev ball. And we know by my earlier remarks that this will then be a near optimal algorithm with a constant 2. Sometimes one prefers to put this in the lasso framework where you add the penalty term here with a parameter lambda in front, and then you can show that if you drive lambda to 0, make lambda small enough, again, you do get a optimal solution or near optimal solution to our original problem. So what does this tell me and suggest to me? It says, look here, the problem with this isn't a numerical algorithm because I have to search over all of H here. However, it tells me some information that maybe what they're doing in deep learning makes sense. Namely, since I can't do this over H, I have to take a set sigma as a surrogate for H, and I'll take a linear or a nonlinear manifold as my surrogate for H, and I would like that manifold to be bigger and bigger and bigger. That is, I'd like to do over-parameterized, solve an over-parameterized problem, because this will get me closer and closer to having, to emulating H in this minimization problem. So this simple exercise tells me, well, these guys aren't so stupid. Maybe it makes sense to solve a over-parameterized learning problem. And the fact that they don't necessarily regularize, that is, inject K into the picture, this suggests to me that, well, I need to inject K into the picture, but in the lasso formulation, it can be in a very weak form because it's only when lambda tends to 0 that I get the optimal solution. So I hope at this stage people have see some of the motivation for what they're doing in deep learning. Okay, now let's talk about actual numerical algorithms. That was a pseudo numerical algorithm because I had to search over all of H, which we can't do. So what we do in reality is we replace H by a linear or nonlinear space sigma, and we solve the corresponding problem, not where we minimize over all of H, but over sigma. Now, of course, we're going to incur some error. The bigger we can take sigma, the finer the space sigma is, the better we're going to do. And one can give, in fact, a quantitative estimate. I don't want to get into it too deeply, but you can give an estimate that tells you how close you are to actually giving an optimal solution to the learning problem. And it depends on how well sigma or how nice sigma is at filling up H, as measured by the distance of your model class to sigma in this Y norm. Okay, so let's now talk about what a typical, so this tells me a numerical strategy for solving the learning problem that I can prove it will give me a near optimal solution. Let's now talk about what deep learning does. How difficult this solving this numerical problem is I haven't discussed. This is a very difficult problem in high dimensions to do, but I haven't discussed that yet. But let's see what a typical learning algorithm does. So what does a deep learning algorithm do? It takes its data and it divides it into two sets, a training set and a test set. It takes, for sigma, remember I said you want a good space sigma to approximate your model class. It takes sigma as a highly over-parameterized neural network. So it uses neural networks And it uses neural networks with a lot of parameters, many more parameters than the number of data. Okay. It then prescribes a loss, could be the square loss that I mentioned before, or it may have a square loss with a penalty. Typically, there is no penalty. And it goes and tries to solve the, minimize the empirical loss over this class sigma, right? So that's what the deep learning algorithm is attempting to do. It does this by starting with an initial guess for the parameters of the neural network, and then utilizes either gradient descent or some relative to gradient descent, such as stochastic gradient descent, to update the parameter choice. How it implements this gradient descent is a real issue. There's something called the learning rate, which tells you the step sizes you're going to utilize in gradient descent. And there is, in my reading, I don't see too explicitly the stopping criteria. How do you decide when to stop when you're doing the iterations of gradient descent? And at the end of the day, after they create their F hat using the technology I just described, they evaluate performance on the test data by something called generalization error. We're going to get into this in a moment, what generalization error is, put this on the side for the moment. But the important thing is they don't certify the performance of their algorithm in a mathematical sense of an error estimate. They instead look at an empirical quantity, namely this generalization error, which is seeing how well the F hat they created performed on the test data. Okay, so my initial reaction to this way of doing things is the following. I'm bothered by the fact that there's not generally a model class lurking in the background in this, either in the formulation of the problem or in the analysis part of the problem. As I mentioned, if you don't have a model class, you can't prove anything. So this is a red flag to me. A second thing is there's not a precise formulation in their implementation of gradient descent in terms of the learning rate, initialization, stopping criteria, et cetera. Different people do different things. And it's not like I'm telling you that if you use this initialization, this stopping criteria, this learning rate, I guarantee certain performance. We don't see that. So the design of algorithms is, I would say, more a work of art versus what one typically does in numerical analysis. Another point, which I'll say something briefly on a little later, is that there's no restriction on the computational budget. That is to say, how long do they spend offline learning F hat? How many iterations of gradient descent? How much tweaking? What do they do offline? This is contrary to what we do in numerical analysis, where we sort of say, well, we know that the more computation we do, the better. So we're interested in what is our error versus the number, the amount of computation. So the bottom line is that this world that they live in is quite different than the world of mathematics or numerical analysis, where we look for certified performance with guaranteed error estimates versus the amount of computational effort we have put forward. Okay, let me move on now. So let me talk about some of these components of deep learning. The first thing I want to talk a little bit about, and I think a lot of this conference will touch on this subject, is why do they choose neural networks as the vehicle for creating their algorithm? Well, they must think that neural nets provide a good approximation to this model class, even though they haven't explicitly told me what the model class K is. They somehow think that it provides a good approximation. And secondly, that it's somehow numerically friendly. It should be easy to implement neural nets. And so what I want to do is address these two issues. Why is it a good approximation? If so, why? And is it numerically friendly? So there are a lot of several expositions on the approximation properties of neural nets. I mentioned Alan Pincus originally. This is getting now a bit old and doesn't concentrate on the deep neural nets. It's typically a single layer neural net that it analyzes, but these other articles go into deep neural nets more deeply. Okay, so let's first take a perspective on what neural net approximation is. In neural net approximation, what we do is we prescribe an architecture for the neural net, and we prescribe an activation function sigma for the neural net. Once we do that, if we look at the functions that are created by varying the parameters, as you vary the parameters of the neural network, and let me call n the total number of parameters you're using. Deeper and wider networks would use more and more parameters, right? But the collection of functions that you produce is a nonlinear manifold, right? As you vary the parameters, you get a different function, and this is the manifold. And this manifold has a little bit of structure, namely it's a Lipschitz manifold. You can prove that if you restrict the parameters to lie in some ball in Rn, this is the set of all parameters, that this is a Lipschitz function on this ball. So again, what is Mn? Given that I've chosen the parameters A to approximate F, Mn of A would be the function that I produce. Turns out to be, if I think, for example, of ReLU activation, the function I produce will be a piecewise polynomial on a very complicated partition. And so it's a function that depends on the parameters that I've chosen. And Mn is describes what this function is as I vary the parameters A. Now, what is an approximation method? So in deep learning, you use gradient descent or stochastic gradient descent to decide what the parameters are. And so the approximation component of is how do I find, given F, how do I find the parameters for F? Okay. What deep learning does is it uses gradient descent and a loss function, et cetera, to find the parameters. But you can view the approximation process as selecting, given F, selecting the parameters. And I denote that mapping by AN. So the form of approximation that's encompassed by deep learning and neural nets is what we call manifold approximation. We're approximating not from a linear space, not by something like polynomials or splines, where we have a fixed linear space. We're approximating from a nonlinear manifold. And we have these two mappings that describe, one, what the manifold looks like, and second, how we select the parameters. So if you want to say, well, gee, neural nets are great at approximating, my first reaction would be, well, oh, I didn't know you were going to allow this general form of manifold approximation. And if you allow me to do that, let me try to understand what manifold approximation could do in general. And the bottom line is manifold approximation can be fantastic. Why? because you know that you can find face-filling manifolds. You can find a one parameter manifold, a manifold depending on only one parameter that fills all of K. So if you open the door to me and say you're going to use manifolds to do the approximation, I say, well, wait a minute, be cautious, because I could take a one parameter manifold and use that for the approximation instead of your neural nets, which use a lot of parameters. Of course, the problem is that these one parameter manifolds are very unstable. As you search to find a good parameter, changing the parameter ever so slightly changes the function Mn of a tremendous amount, leading to high instability. And so keep that in mind. Neural nets are opening the door for instability. We, in fact, know, this classical example of instability, that you trained a network for a classification problem of identifying what objects are in an image, and you train it, and part of the training is this image, which is correctly classified as a pig, and then you subject it to a little bit of noise. And what you find out is if you add a little bit of noise to this image, you get something that looks like exactly like your original image, and yet it's classified incorrectly. So the algorithms are very unstable. This reflects the fact that the function Mn is, although it's Lipschitz, it has a very large Lipschitz constant. So instability is an issue. Okay, now let me say a few words about neural net approximation. So, I mean, people write, there are lots of papers written on this, making claims that, well, neural nets do a great job at approximating. So do they? Well, I'll just give you my quick view of the situation. I think that Zhuawei will talk about results of this type. Namely, that we know that neural nets can do a better job than classical methods. First of all, it does at least as well as classical methods of approximation, by which I mean polynomials, splines, wavelets, and the like, finite element methods. Anything that those methods can do, you can prove that neural nets with the same number of parameters or the same complexity do as well. Second, you have these super performing results that say they actually do much better. For example, a lip1 function on 0, 1 can be approximated to accuracy n to the -2 with n parameters. This defies what we normally get in numerical analysis. Normally, we would only get n to the -1. And so you might look at this and say, wow, that's it. That explains why neural nets are so great. They do better than classical methods. They have this super convergence rate. In fact, you can prove super convergence in a very, very general setting. I think Zhuawei will talk about super convergence for Sobolev balls and the like, but we'll see what his talk unfolds. My point is that these super convergence results, interesting, very interesting mathematically, but they have to be unstable. In fact, there are theorems that tell you they're necessarily unstable mapping. So it will be hard to find this super performing approximation. And then this is where I would say, well, if you give me unlimited time to look and search for this approximate, then maybe I can find it. Because if you put no budget on my computational time, maybe I can search over this manifold and find this great approximation. I think the real value in neural net approximation lies in the fact that there are new model classes, not the classical ones of classical smoothness like Lipschitz, Sobolev, Bessoff, but new model classes where neural nets are provably good at approximating. You're probably familiar with Barron classes, which are the convex, basically the convex Hall of the ReLU dictionary. This is actually an inflation of the Barron class a little bit. But there are other ones built on the idea of self-similarity, fractals, iterated function systems, and the like. And I kind of feel that maybe these are the reason why neural nets are a good method to choose to build your numerical platform to do learning. That they're very robust, that they cover a lot of model classes, not only the classical model classes, but very different new model classes that might match the application you're interested in. Okay, so let me now talk a bit about data. So one question you could ask is, well, how do I know I have enough data? You know, of course, I think in many of the modern applications, they have a humongous amount of data. And so they may say, well, that's not an issue for us. But to a mathematician, we would say, well, do we have enough data? So if we have our model class and we're given M pieces of information, how well can we recover a function f in this model class from these M pieces of information? The bigger that M is, the better we can do, right? In general. So there are ways to measure how well you can do. The most famous is the Galfond width that says that if you allow any M linear measurements, that is any M linear functionals, then it tells you if you choose these linear functionals, these data sites, as best possible for the set K, then it tells you how well you can do. So in your given setting, you'll never do better than the Galfond width. So I think it's important, my view of the subject is you need a model class, and it's important to understand what the Galfond width of the model class is to understand how much information, how many measurements M you would need to attain a certain accuracy. Delta M would tell you the accuracy, the best accuracy you could attain with M measurements. Now, of course, in learning, we typically don't have general linear functionals for measurements. We use point values, right? We have the values of function at some points, xj. So this wouldn't fit into Galfond widths exactly, because Galfond widths allow any linear functional, and here we have to use point evaluation. So you can introduce an analog of Galfond widths. When you see the P on the bottom, here the P stands for the fact that I've restricted my measurements to be point evaluation. And delta M P would tell me the best error I could do if I could optimally choose the points x1, xm for the set K. So I know K, I now look for the best points, and delta MP would tell me the best error. And it will be worse than the Galfond width, but it would be interesting to know for a given model class, how does this behave as M tends to infinity? And then finally, you have the problem that, well, you don't get to choose the points, right? You're given the measurements. Those points have been chosen, the xj, have been chosen for you. You didn't get to choose them. So what do they do in deep learning? They say, yeah, you were given those points, but we assume that these points were a random draw from some probability distribution. And so you could say, well, all right, given a random draw, how well do you perform? And now, of course, the draw can be bad or it could be good, but you can say, okay, on average, how well do I perform? That is, for example, an expectation, what would be the best I could recover? So my point is here is it would be very useful if in deep learning, one analyze these quantities, Galfond widths, pointwise Gelfand width and the average width to understand how much data you need to learn functions from a given model class. Okay, so if you propose a model class, I just said it, you should evaluate these quantities to understand how good your model class is, how many measurements you will need, do you break the curse of dimensionality, questions of this type. The point of that discussion that I gave is that to understand whether a model class is good is not simply a matter of understanding whether neural nets can approximate well the functions in the model class. In fact, there's a gap between how well you approximate and how well you do from data. And this is now being enumerated in some papers. It's called the theory to practice gap. All right, so I've pushed model classes. I think when I talk to people doing deep learning, they don't typically use model classes and they argue against it. So what is their viewpoint? Their viewpoint is, well, we have an algorithm and we know our algorithm is great, right? We know this deep learning does a wonderful job. We can show you empirically in a lot of examples that it's doing well. We don't have a model class, but we somehow know that deep learning is picking out a certain function as how it takes the data and extends the function off of the data. And there are attempts to explain what that function is. You're probably familiar with neural tangent kernels for single layer networks, and people are trying to understand what is happening in deeper networks. So their view is that, well, we have a good algorithm. It wasn't that we started with a problem where we knew the model class and now we'll create an algorithm depending on the model class. No, we forget the model class. We have the algorithm and now we'll try to understand in essence which model class was lurking in the background that our numerical algorithm was actually finding. So this is a different view. And one thing that bothers me is that since they're using the same algorithm, no matter what the underlying model class was, that seems very strange to me. Seems to me different problems should indicate different learning algorithms. Now they would argue that, well, we do that by changing the activation function, by changing the architecture, maybe changing learning rates, et cetera. But then it becomes sort of an art to figure out what the algorithm is. Okay.
Ron, I'm gonna interrupt just a minute. We've got just about 3 or 4 minutes left before
Yeah.
we have to move on.
Yeah, I'm gonna move fast, okay? Okay, so I'll do this in 1 minute. I said, okay, what functions are we learning when we use deep learning? So I said, let's take a simple example. Let's take the function x squared. I'll give you data at 100 equally spaced points on 0, 1. You tell me what function you generated. What is f hat when you use deep learning? I put it into TensorFlow. I get nonsense out. All right, you know, I try TensorFlow and the functions it gives me as the approximation to x squared are like constant functions or the zero function. And so this is very poor. And I know then I must be doing something wrong. I call Boris Hanin, say, what have I done wrong? He tells me various things that are the state of the art. That is, you have to really choose networks which are wide, and you have to use the slow learning rates and so on. So the point of this is that you can't just take an off-the-shelf algorithm for learning, throw in your problem and walk away and come back and get a good fit. It doesn't work that way. After you do some, art work of designing the algorithm, you will get a reasonably good fit, but I don't see a theorem in the form that do this and I guarantee you that you will get a good fit with a certain accuracy. Okay, so I think I have 2 minutes. And in this 2 minutes, I want to turn to generalization error, which I alluded to already. And it's peculiar to me that this idea of generalization error has supplanted what mathematicians would usually like, which is a certified theorem that says, I guarantee you a certain error that is the norm of f minus f hat is small if you use my technology. Because this would be certifiability of a learning algorithm if you had an explicit error estimate. But instead, what's done in practice is one looks at the test data and, for example, looks at a square loss and says, okay, we train and we find that this loss is small. And so good, we have a good fit to our function f hat. Is this truly a good fit? What can you say in terms of certifiable performance? And the answer is, well, you can't say anything with certainty, right? Because the draws that you have of the data, as I mentioned, could be good draws or bad draws. Now you may say, well, I'll say something in terms of expected error, that even though the quantity I've computed, I can't guarantee that the true error is bounded by this quantity or anything related to it. Maybe I can say something about that with high probability on the draw that this would be the case. And if you go into that world, then the best you can say is that the error with high probability, the true error behaves like this, where m prime is the number of elements in the test set. So you could think of m prime as replaced by m. Notice the minus a half, which comes up from concentration of measure inequalities. And even though epsilon m may be very small, right? Much smaller than m to the minus 1/2, I'll never get a certification that I'm performing near optimally. Can I get 1 minute to finish this last slide, Greg?
All right, go ahead, and then we'll have to move on.
Yeah. So simple example, take the Barron class, dimension 1, it's the toy example. Approximation rate is n to the minus 2 if n is the number of parameters. Gelfand width is m to the minus 2 when m is the number of data. Point wise Gelfand width is m to the minus 3/2. Average Gelfand width is m to the minus 3/2 log m. This would be, if I knew the model class, injected it into my algorithm, I should be able to get this rate. If I do generalization error, I'll only get this. I will never get close to the optimal performance. Bottom line, I don't see generalization error as a good concept to measure whether you are performing near optimal rate or giving you good guarantees on performance. Okay, I stopped there. I sorry that I took a minute over and that I sort of rushed through these last parts, but I'll stop at this point. Okay.
No problem. Thanks very much. If anyone who's willing, why don't you unmute just for a second and we'll give a round of applause here. Just unmute briefly and we'll give Ron a round of applause.
Okay, thank you.
Great, thanks very much. We don't really have time for questions, but maybe we can have some time later on to do some questions offline.
Okay, I'm going to stop screen share.
Yep.
Okay.
And then Zoe, you can start your share.
Can you see?
Yes, looks good.
Okay.
Great. So as our second speaker, I'm happy to welcome Zuowei Shen, who's the Tan Chin Tuan Centennial Professor of Mathematics at the National University of Singapore. He'll be speaking about deep approximation via deep learning. So take it away.
Thank you. Thank you for the introduction, and thanks the organization committee for the invitation. And today I'm going to talk about, okay, it's a really match with Ron's talk very well. Talking about approximation by the deep neural network. To me, the deep neural network, the difference between the deep neural network and the classical approximation is a deeper neural network is approximation by kind of composition of the functions. And how do I move? Okay, I will start with a brief introduction of the approximation theory, which most part Ron already done, and then I will.
We can't see all of the text on the screen. I'm not sure what happened. It's cut off.
Yeah, it seems that I only have a small window here in the middle. That's in the middle of my screen. That's the green window. I cannot get yeah, that's true. That's all. How do I do? Let me see.
Maybe stop share.
Stop share.
Close the PDF viewer. Close it. We open that. Maybe it will work.
What do you say?
Close the PDF file and open it again. Maybe it will work.
Okay. Let me stop share first, right?
Yeah.
Okay.
And close it and we open it.
Okay. Let me. I close. I just not open.
Yeah. Open the PDF viewer.
Here's my PDF.
And then choose share screen. Share screen.
Okay. I share screen. But okay. This is if I open with this one. Okay. I have also problem. Can you see my file now?
No, you have to share screen first.
Okay, let me.
And if it doesn't work, you can just do what you were doing before. At least we could see something.
The problem is that's you gave me a green window. Only the green window, but my file is okay. I can.
It's okay. It's better now.
Okay, I see. I can open the bigger window. Okay, now let me do. Okay. Okay, that's all better.
That's good.
Okay, so okay, let me because of time, let me get over there. Okay, start with approximation. Okay, approximation is like that. You have f from RD to R, and you give an epsilon. You want to have find a simple function g, such as f minus g. In sum of norm, you decide to smaller than epsilon. That's about approximation. Then function g can be very simple as a line. That's a linear function. But to make this to the sense, your g even can be Rn to R. To make sense, you need a trans map T, so that the function f or g composed with T that have a good approximation to f. So for the classical approximation, T is the map T is independent of f or data, and is given basically. And but number of n is depend on the epsilon. Your bigger epsilon, normally your n is big. But the early learning, the T is linear for T is depend on data, but it's only few parameters. The deeper learning, you open the T in many layers. That is a decomposition of the T to many layers, and many levels of simple function, you make a composition. So this n can be independent of epsilon. Okay, let's talk about the classical approximation. The linear approximation is very simple. You have a generator. Generator is number of generators n. You basically using the projection or pseudo projection or interpolation or kind of this. So get the best approximation. Linear combination of the generator to get the best approximation. And because this, if you want to have a good approximation when n, small n increase, that means your function should be smooth. That because that means your coefficient should decay fast. In other words, in most time, like a Fourier series, your function should be smooth. That's why all the approximation theory, you start with smooth function. Okay, smoother the function is, the better approximation you have. And another is the n-term approximation. Long is the expert. That's about the linear, non-linear approximation. Basically, instead of you have n generator, you have a bigger dictionary. Dictionary can be infinitely many, and you just, but you need to what? You only for each f you only allow your n non-zero coefficient, your budgeted given. So for this kind of approximation, it's non-linear, but you see, you choose only n best coefficient you can choose. The decay of the coefficient requirement of that, requirement of decay of the coefficient is smaller, is less. So therefore, it's kind of approximate piecewise smooth function instead of a smooth function. That's why this wavelet approximation is using this the theory of the nonlinear approximation theory to achieve the good approximation. And that's also why wavelets is good for the image. And because the image is piecewise smooth, in fact, most time it's piecewise constant. Also, the n-term approximation, because you fix your n, you have a flexibility to choose a bigger dictionary from bigger dictionary. That's also related to the sparse approximation. That's also this comparison sensing, sparsity, all related to this n-term approximation. And I spent almost 20 years of my life on this. Now I will talk about the deep learning. So for the deep learning, you have a neural network. Given neural network with a depth error and width n. And this is your function in long term is in your sigma. Okay, this is a parameter with my parameter is sigma instead of a or theta. Okay, your phi can written as g composed with t, where each t can be further be decomposition to the composition of the t1 up to tl, where each ti is a simple, is a composition of the two functions. One is affine function. This w is a matrix and b is a vector. So this affine function, this sigma is activating function. Okay, later I'm going to show you a few activating function. So this each tj is this simple, and then your phi is basically composition. Mathematically, neural network is that each ti is your one layer. So this is mathematically this is what a neural network is doing. Here, your affine map is parameter, the w matrix w and b all are your parameter to learn. Okay. So to find phi x theta, essentially to find
right.
So for the fixed theta.
Yes,
What? Sorry, what did you say? For fixed theta, consider this inferred arrow. So you have a arrow. This arrow it can depend on this say you have a data have a distribution. The arrow is depend on your distribution. Okay. So for simplicity, the error is the distance you choose. The error I can choose L2 norm. This is your Euclid norm, and U say suppose the uniform distribution. Then your RD zeta can be written is basically L to L. Okay, so deep learning, ideally, you try to find the zeta, okay, to find the parameter zeta, so this get to the minimum. That's what a deep learning. But of course, reality is you don't have a function available. If you have a function available, you try to minimize that. You only have a data available. You only have a sample available. So you instead of that, you have this empirical risk. That's the least square error. That's what Ron mentioned many times. So the given data, my data is simple, is xi, fi. Okay, so deep learning algorithm essentially is minimize that, found the zeta such that zeta s, find the parameter to minimize this empirical risk, okay? And practically, you even don't get zeta s. You only have a numerical solution. It doesn't matter which algorithm you use. You don't get zeta s, you get zeta n, okay? So at the end, you get zeta n. What's all the approximation Ron talk about is essentially you want to know RD zeta n. That means your phi x zeta n distance between phi and f, okay? This arrow is kind of divided by the 3 components, okay? This first component is the RD ZRD. That's what we call approximation error, okay? This is you have a target function which belongs to some class. That tells your capacity of your neural network, okay? It's independent of what kind of data you give. This error is optimization error between the zeta n and the zeta s. This is the model solution. This is the numerical solution. This is your optimization error. This is your generalization error. These 2 terms together is the generalization error Ron talk about. Okay, so for reduce the optimization error and the generalization error, you need algorithm, you need data. It all depends on what kind of model you use, empirical model you use. You kind of put the regularization in, but for approximation error depends on your target function. That's what the target is. That doesn't mean that in Ron's term is the model of your function. Doesn't mean where your function belongs. And this approximation error tells you if you give your neural network with the given depth and width, what's the capacity of this hypothesis space, or in Ron's term is the manifold, okay, the capacity. Whether you're able to get it or not is not my discussion. My discussion in this talk mainly on this part, how to estimate this error, the approximation error. Okay, to pick in a picture, okay, you have this hypothesis space. That is I call it hypothesis space. That is the Ron's sigma n. Okay, given a parameter, given a length and width and depth of the neural network. This is your target function. Target function may belong to some space or some class like a K, or in Ron's terminology. What we are doing here is, I want to say that what's the best approximation between the what's the shortest distance you already gave if you give between this hypothesis space and to the target function, okay? And of course, of this kind of thing, normally you want to minimize, and you minimize it to the optimization. You have you go to iteratively go to get your model solution, learner solution. But learner solution you get from the empirical risk. This is the optimization error, and for empirical risk and to this real function distance, this is the generalization error. Okay, again, my talk here is mainly focused on the distance between, focus on the approximation error. That means distance between the hypothesis space and to the target function, which belong to the certain class of function space. Okay, idea. The idea about the classical approximations, there are 2 key ideas. One is to reproduce certain degree of polynomial, locally reproduce polynomial. Second is using the smoothness of function. You have a smoothness function, you do the Taylor expansion using the because it's a locally reproduced polynomial, you get the remainder. Then to reduce the error, you make the step size small. That means cut the domain, subdivide domain. That's the all the classical approximation is about this. Of course, each theorem you need many technique, but idea is a reproducing polynomial and the smoothness of the function. But if you look at deep learning and you think about the composition of the function, it's different. In fact, smoothness is not the key rule. The key rule is instead of your divide the domain, we are think of divide the range of the f. Okay, if you divide the range of the f, and so the approximation always there because you can have the ball bi can be very small. That's the interval here. Your interval can be very small. You will get an approximation. The problem is the inverse of each small interval is very complex. So at the end, I think traditionally we think the good function you are either have a high smoothness. It's easy to get a better approximation. But I think if you think about deep learning, you talk about approximation only. The level set is more important. Level set of a function, the geometry of the level set, and the complexity of the level set is much more important than the smoothness. In all my proof, sometimes I do use some smoothness property, but smoothness property is not aiming to get a Taylor expansion or this. The aim is this, when you have a certain smooth, like a smooth function, you can easy to get inverse of B. Okay, otherwise it's so complex to understand the inverse of B for if you have a function like that. Okay, so the next way, let's talk about mathematics first. Talk about the approximation of a function by composition. Okay, as a setting is that you have a given data. You want to through data you can try to construct your T and G such that the T composed with G have a good approximation on F. Okay, so before we can ask the first simple question. If we given F and G, is there any measurable function T such that F can be equal to G composed with T? The answer is yes. And if you have any F and any G, and as long as your image of F, this is the key condition, image of F is a subset of image of G, then you always can have the second condition, G is continuous, you can even weaken this condition. Okay, but it doesn't matter. The G you can choose anyway. So then you can always prove exist T such that F equal to G composed with T. The proof is not constructive. It is a existence proof. Okay, we don't know, even if I gave you F, we don't know how to construct T. The second question, then, if you have you cannot get equal to the constructive proof, we can how about a given epsilon? If I choose epsilon, can we construct T? Suppose you have F. So theoretically, it's true. Yes, you can. Okay, you can always in fact, this proof is very constructive. Suppose you give me F. Okay, the third question, of course, if I don't have F, practically, if I have a data only, can I have a decomposed T to the composition of the T1 to TL? Each one is simple, and you can learn TL. Okay, this to do that. We also theoretically we can prove there is such TI exists, and you can do that. Also, we have an algorithm to learn how to learn those TI. Okay, to prove the concept, we also know the stop criteria, whatever. So I skip to prove some concept. We try to test this for image classification, emptiness, and fashionness. Of course, this already have a set us results, and we are not talking about we are beating that. But if we use this, we can see we get almost the same result, but we use a fairly small network. Okay, the network more or less like only have 4 to 36 channels, and only have a depth only 2 to 4 layers. Okay, this is small net, you can get the same thing. Okay. So this is about the mathematics. Okay, so people may ask, okay, that's your theory. Your theory is beautiful. You also have a numerical result, but whether people really use this, you really okay. Then we look at into this particular network. They're called residue nets. Okay, the residue nets you can consider as x as written as xk plus 1 equal to that. Your each h is your activating function. In this case, we say ReLU or something else. Okay, there's ReLU. And then you can continue time idealization for that. You get the ODE. Okay, dynamic system, ODE dynamic system. Okay, this is the ResidUnet can be viewed as a continuous time idealization. Is not our invention. Okay, this is my collaborator Chen Xiao and Wina, they did it. Okay, but we are the first time to using this to start approximation for the residue nets. Okay, now how do we connect with T? Your T is basically the flow map for your this solution of this ODE. Okay, you start with X. Your flow map is mapped from your X to XT. Your X can be X0, then this is XT. Okay. So this fits very well. When you parameterize T, you can decompose T to the T to T1 up to TL. So basically, you just need the dynamic system. You from the time 0 to T, you decompose this interval to the different partitioning of the time 0 to tau. Then you can get each TJ. Okay, this is exactly fitting well. So once you have a T, you can choose G. So G compose with T. Now the question is whether G compose with T have a good approximation. That's what kind of condition we need to impose on the control set F. This is basically the activating function. So the result is very simple. We just for any d bigger than 2, bigger or equal to 2, for any f, and if k for the any compact set, and you need this is the same condition. This is the image of G should contain the image of the F. That's what we need. And then the F, there's a control function. We need to satisfy some very mild condition. I'm not going to put the condition in. Later, I'm going to show you an example. Then for actually epsilon, you can get that. Okay. For this one, if you discretize this ODE, you get the UEP or the universal approximation property for this neural network, for the residue network. Okay. Now, why I say this our condition on the F is mild, because okay, the 3 commonly used activating function, say ReLU, this is a sigma, and this is a tau. All those 3 functions, the corresponding the fully connected this layer, they satisfy my condition. Not only all those, if you have a little residue net generated by these 3 activating functions, they satisfy this condition, my mild condition. So the corresponding residue nets have a universal approximation property. Not only that, and commonly in the practice, they use this block kind of structure for the residue net. For this block structure also satisfies my conditions. Okay, here I talking about activating function. Later, I'm going to talk about more about the activating function. And many people write comments says activating function, they like this comment. So there's almost like a close to 0 or fairly calm. Then you suddenly start, then it's keep calm. Okay, status there like your neural. You feel it when my talk is boring, you just sleep. Then I talk something loud or exciting, your neural turn on. Turn on. If I keep telling you something interesting, you stay on. But this one is not. You keep asleep. Then when you wake up, you wake up forever. But we all know the ReLU. You have a two ReLU combination. You can have the same shape. So this shape seems ideally. People like this kind of shape. Okay. Okay. Now I talk about this is the technical part of my talk, and this is about this approximation rate in terms of width and depth. Okay. First, we start with the ReLU. Okay. So for this first part, we only talk about the approximation rate for the ReLU. Okay, for a given width parameter, okay, with parameter n and the depth parameter, that's two variables. One is related to the width, one is related to the depth. Our question is what is the approximation rate in the terms n and l? Okay, for the ReLU network. Answer is that when this f is Lipschitz with a constant lambda, then your function, your L is this. Okay, and we have an exact estimate for what's the depth of the neural network, what is the width of the neural network. Okay, this estimate is optimal. Optimal in a sense, you cannot improve further. Of course, this one you can generalize to for the continuous function. For the continuous function, instead of using this, you have to using this module of a continuity, and in terms of module of a continuity, you can get an estimate. Okay, this is essentially similar, and so this is a literature that for n for d equal to 1, when d equal to 1, for the n for n equal to 1, so you only have a one layer. For n equal to 1, sorry, n bigger than 1, L, you only have a one layer. L is equal to 1. Then it's people all believe that the rate should be n over or 1 over d. Okay, it's well known for d equal to 1. For d bigger than 1, I don't find any proof in the literature. I don't find, and I don't have a proof. But I know that's you cannot be better than that. Okay. Then Yorosky had a paper say when n is 2d plus 10, then L is sufficient. These are asymptotic kind of result. You have rated that. When Ron mentions that he had a result in terms of the parameter, because his parameter is also based on, because your n is fixed, so your parameter is found in terms of the L, so that they have a system. But this is asymptotic. They say L should be large enough. When we had a first result when only have a L is 2 when the d equal to 1, and L is bigger than 3 when d is bigger than 1. We have this result. That's our earliest result. It was done in also 2018, and then we get the result. Final result we get is n bigger than 1, L bigger than 1. We have the result like that. Okay, this is different from Yorosky, because we have two variables, width and depth. They can change freely. Okay, with the width and depth is not a dependent variable. They are two independent variables. Okay, this is a set of the paper on this on this ReLU result for the Lipschitz function or continuous function. Okay, as I said, this estimate is almost optimal, and it's no way to improve. But people are not happy with that result, because people say this is the curse for dimensionality, although it's already much better, but there's all kind of complaint. So if you want to improve this one, you have no other choice you only have two choices. One is change the target function space. Second is change the activating function. So I'm going to continue for these two things. Okay, for change of target function space, of course, I can change it to space to so small to the function space is your polynomial space. If you have polynomial space, your results are good. Essentially, polynomial space, if you have a ReLU network, as long as your network has the right size, you can have a n+1 to the power of -57k L. That also shows the power of the deep neural network. Your L go to the power, your depth become a power. Okay, if you take a polynomial space. Of course, this the results for if you have a smooth function. This is a smooth function. You can have a better result. You have a if smooth function f is in CS, you have a S here. Okay, your result you have a power, have a S. Okay, this is the result. Okay, of course you also have the key here. We have a exact estimate for the each size of a neural network. It's not asymptotic. All the difficulty for our proof is we need to know exactly the size of the neural network. In terms of basically our approximation is in terms of exact size of the neural network. Okay, now for the space, of course, if you go to barring space, maybe you can get a better. But you can go smaller space. Of course, you can have a chance to get a better result. Another way is how I gave up ReLU only. I have a more choice about the activating function. I can choose between ReLU and floor. Say, I can build a network instead of each time I use ReLU. I have freedom to choose ReLU or floor. Okay, basically it's the same neural network. Each time you have a ReLU or floor to choose. When the system comes the neural network, you can have a much better approximation result. The result is like, okay, you have N and L, and your system is your width is this one. Your depth is also in terms of the L. Then your approximation like more or less like the look at the whole continuous function looks more or less similar to the ReLU to the polynomial. You have n to the power square root of L. Okay, that is very good. Then you don't have this D appear in your approximation order. Okay, this I think is if you do a little bit further. If you do a little bit further, this is the paper we did, and you have to do. You can have a 3 floor or 3. You can reach to achieve this approximation. This is exponential approximation in terms of the depth. You just need a 3 layer in terms of the parameter. Okay, sorry, you can have exponential kind of 2 to the minus n kind of the approximation. You by 3 layer. If you adding one more kind of a activating function. Okay, this is the done in these 2 papers, and people still complain because you're using floor function. Okay, people think about floor maybe not so good, and this is it probably motivate our next work. This is I'm going to talk about the universal approximation property. Okay, we all know the universal approximation property is a common property everybody talk about. Okay, it's a fundamental kind of concept. But what's the key difference from what I'm talking here and the other results? Here we achieve, okay, in the literature, when people talk about a universal approximation property, you always ask the number of parameters goes to infinity when you go to absolutely close to your function. Okay, and we achieve the universal approximation property by fixed size of a neural network. But that means by fixed size, fixed number of the parameter. Okay, So our key idea is just change the activating function. The activating function is simple. It's not so complex. This is our activating function. From negative infinity to 0, we choose our function to x over 1 plus x absolute over x. Okay. From 0 to the positive infinity, you have this periodic function, is a triangle wave function. That's basically a combination of the ReLU. Okay, piecewise linear head function. That's my favorite function. Okay, this is my activating function. With this activating function, I generate the neural network same as before, x, phi, x theta, and this t is a affine map. My activating function sigma is the sigma I used before. Okay, is his function. This is my sigma. If we use this one, this is here I just need this part is similar before. I need to introduce a hypothesis space that is a long sigma n. Okay, this hypothesis space, that means you given n is exactly width, and L is exactly the depth. You give the layer that you have all the function generated by this neural network with this depth and width. We call this a hypothesis space with index n and L. Okay, there's a fixed side, n fixed, L side fixed. This is a fixed side. Our main theorem is very simple, and the proof is very hard. This hypothesis space is dense in a continuous function as long as your n is bigger than this one and L is bigger than 11. Okay, D is the dimension. Okay, n bigger than this basically like more like a d square, rate over d square, and L your depth bigger than 11. What does that mean? That means we achieve using this simple activating function, we achieved universal approximation property. Okay, that means this set of a function dense in C continuous function space with maximum norm. And okay, mathematically says for arbitrary f, your arbitrary epsilon, you always can find phi such as there in there. Okay, you don't need to change n, change L. Just as long as your n is bigger than that. Okay, what is this good? If you think about, if you still want to recall, I talk about the rate of the ReLU and whatever. If you still want to talk about the rate, that means for given n and L, as long as your n is bigger than this two magic number, your rate is infinity. Like infinity, you have any rate for arbitrary epsilon. Okay, so not only once you have one such function, you can generate a class of function have this property. We have a theorem, and with that theorem, you can generate one. The one I like is this one. This one is really like a sigma model kind of function. This function, you also can achieve that. Only difference is your L should be a little bit more than 11. Your steps should be a little bit more than 11. Your n is still d square rate, but as a parameter, the coefficient constant is a bit bigger. And this function, you can write it out. You have an analytical form to write that out. Okay. Okay. Finally, I want to talk a little bit about application for all those ideas to the classifications. Okay. Classification, I can think most successful for supervised learning is a classification. Okay. Most successful example for supervised learning is a classification. Okay, classification in fact, its function is very simple. You have a two set. For its binary classification, you have a omega x in omega 0, you want to be 0, x in omega 1, you want to be 1. But this is the omega 0, and this is what I said at the beginning. The level set is important. The whole business of the complexity of the function is the complexity of the omega 0 and omega 1. So whole the task for the classification, you want to be able to separate from omega 0 and omega 1. That's all. That's all. So it's nothing to do with smoothness here. So we can show that if your f in fact is in that, you not to say you need to approximate for if you have a this f is in that, as long as your closure f is have a no intersection. This is the minimum condition, because you must have, if this two closure of omega 0 and omega 1 is not the intersection of the two sets is not empty, you cannot separate them. Okay, so this result is, I think that means for classification you don't have approximation error. Okay, your function is in your hypothesis space. That's you just need to find, you given data, you need to find this function in that space. Okay, so this of course it's a kind of easily generalized to this multiple M class classification. The same result. Okay, that's the same result. Okay, you can do that. This is our most recent paper, and you can get it from archive or from my webpage. Okay, to summarize, my talk here is talking about, essentially we are talking about approximation error. What the approximation error is, basically you're given the neural network with fixed depth and width. We have tried to find the distance from your, if we give your norm of the distance, then we try to find the shortest distance from your hypothesis space to your target function. Okay, your target function most time we decided is for the continuous function, and sometimes this distance can be as close as you want, it's essentially 0. Okay, what's important for this study? The importance is that because approximation error, at the end, no matter what you do, okay, no matter how fancy your algorithm you develop, you want to find RD theta n, you'll find the error for your solution. So your solution will be bounded by 3 parts. One is the approximation error, one is the optimization error, one is the generalization error. And this approximation error itself does not depend on your data, does not depend on your algorithm. Unfortunately, my theory does not provide your algorithm if you only have a data. However, it's crucial. If you don't know this bound, you don't get anything. Even you have a very good optimization error, you have a very good generalization error estimate. You only can estimate the function in the hypothesis space. Okay, so I think it's mathematically you understand the approximation error is important. And of course, next is how do we develop algorithm to reach to that best approximation. As you may already learn from the Ron's talk, this is highly non-trivial and almost impossible. However, the key is still how do you reduce these other 2 errors. Okay, I think I finished here. Thank you. You can get my paper from my webpage.
Great, well, thank you very much. We have a couple of minutes for questions. Are there any questions? I think you can just go ahead and unmute yourself if you have a question.
I'm sorry, because at the beginning, my slides don't work, so a little bit disturbing. Then my talk is not as smooth as it should be.
Oh, no, it was great. No, it's fine.
I have a question.
Yeah.
So for the approximation theory, do you investigate the densenet? I see in your work you have developed the approximation theory about the ResNet. How about densenet?
What net? What do you say?
Densenet.
Which net you talk about?
DenseNet. I think he said DenseNet instead of ResNet.
Yes.
No, I think this is the for the dynamic for the using dynamic system. This is for the ResNet, and for the rest part of the theorem, we just have assumed your network have a depth of error and width of n, then we estimate in terms of n and l. We don't study any special architecture.
Okay, I think Guoji, maybe you're next.
Yes. I was wondering, because you choose this special activation function, was it crucial
I have a
to?
class. I cover a class of activating function. Okay, it's not easy because at the end, okay, if you want to have an approximation by the deep neural network meaningful composition, at the end you have to have this activating function. Somehow you can generate. You can read our paper. Idea is to generate a few kind of like a step function or approximate step function. You have some periodicity. You can have so that you can generate kind of approximate as many points as you want. That's the key. Okay, but to do that is the proof is really technical. Idea, but I think we put an idea first. Idea is simple, but the proof is technical. That's I think you can look at the paper. Paper is not short either. Okay.
Okay.
Yeah. But the good thing is that we not only generate one activating function, with one good one, we can generate. We have a theorem. With this theorem, we can generate a class of the activating function. Some activation like I feel this one is better than the first one. So in terms of shape, people will like this one better than my the original one. But this one also was generated by this one. Okay.
Okay.
But we prove our paper is first we prove this function have this property. Then we prove another theorem. Once you have one function, how one theorem tells you can generate many function by this function. Then we generate many other functions. Okay.
Okay, I see. Yeah, thank you.
Okay, and Jean-Feng Liu, I think you can go next.
Yeah, so I think this was also a point that mentioned in Professor DeVos' talk, so about stability of these approximation results, right? So in some sense, we see these super approximation results. So just wondering, like for example, for using such activation functions, what can you say about stability of these approximations?
Okay. As I said, so far our results says the capacity of your hypothesis space. Okay, this is independent of your data. Okay, once you talk about approximation, then you depend on what kind of data you give, what kind of algorithm you choose. But the one good thing for this whole business is that we prove that for the classification. So the function is in your hypothesis space. Once you know the function is in hypothesis space, you may be able to develop some good algorithm for that. Okay.
Yeah, so
this is different. You are not to say I use this like in Ron DeVos case is your sigma to approximate your target function. Your target function is in there, in your sigma n, in my hypothesis space. So,
yeah,
we are not we did not have an algorithm, but still, of course, when you do that, you still have all these issues. Whether it's all you all depend on how many data you give, right? Our theorem, in fact, is constructive, but constructive in the sense you have F available. What I mean F is that means you can get the data as you wish. Okay, so that's another reason. So I agree that from this theory to the really you have an approximation scheme to reach to that level of the approximation. That's different. But
I think one way to ask this question can be without using any algorithms, right? For example, for classification, I mean, you have this linear separator, and one can ask if one perturb that a little bit, how does the function approximator in your class perturbs, right? So
yeah, that's it's not a topic of this paper. Topic is that we only try to get this one. Okay, done. This is the we did not touch most of the time. In fact, in my view, most of the time you talk about the generalization error, right? Yeah, how do you reach how do you estimate the generalization error? And also, of course, then your algorithm. If you do the deep learning, if you're using current deep learning practice, basically you try to as bound these two errors. Because your error, essentially your numerical error is 3 terms. One is the approximation error, that I already gave to you. Okay, one is the generalization error, one is the optimization error. But the generalization error and optimization error all depend on data, algorithm, and model. Okay, all this, whether you have a stable data or stable algorithm for the good model, we don't know for you. But for the key that no matter what you do, if you don't have approximation error, even you have everything great, only you can do the classification. That means your functions in this hypothesis space. So now we have approximation error. That's it. Okay. Yeah, I'm saying I think amongst all these 3 errors, approximation error is technical, but it's still simplest one. Among, if you don't want to, optimization is a highly non-trivial, it's a non-convex problem. And this is a generalization error also all depend on the data, depend on many others, depend on other people in my term. But your approximation error depend on you. That's all.
Okay. I think we better move on for now. Let's unmute for just a moment and give Zoe a round of applause.
Thank you, thank you. Thank you. Let me how do I want to unmute myself.
You could
Okay.
you can do stop share.
Yeah.
There you go.
Yeah.
Let's see. Jin Xiao, are you on? Could you just test your share? Great. Okay. And then let's stop just for a second. We'll have Zhangfeng. Jin Xiao, could you stop just for a second, your share, and then we'll let Zhangfeng, can you test your share just for a minute? So we'll make sure we're set to go.
Oh, I need to log in another device. So maybe I think Jin Chao can go first, and I will try to do that later.
We have a tea break for 10 minutes, I think, right?
Yeah, we've got a couple minutes break.
Oh, I see. Okay, yeah, then I can
make sure that everything was
just
set
a
up.
minute.
But if maybe you're an experienced presenter, so it's okay. But
So Greg, I started 10, 20.
Yeah, we'll have a short break. I just wanted to make sure that all the technology was set up so that everybody's ready to go. But yeah, we'll have just a couple minutes break here. Start at 10:20.
Well, can I use this break to ask you or make some comments?
Yeah.
You hear me?
Yeah, I hear you.
So, I mean, what you're creating.
But everybody else also hear you.
Oh, well, it's okay. So in the last part of your talk, you were showing how to create space filling manifolds, right?
Yeah.
I
Yes.
mean, because you get every function is approximated to arbitrary accuracy by
Yeah.
a fixed.
That means in your terminology,
number of
I have a sigma
parameters.
n. I have a sigma n, which is, I have a sigma n that can fill the space. That's basically
Yeah.
in your
For
terminology.
fixed n. You
Yeah.
don't need n to get large. Now,
But
you know,
my n is fixed in some sense. Yeah.
yeah. Well, you know that Alan Pincus and Majorov also exhibited such a network. It's it's summarized in Alan's paper that was in Octa Mathematica, right? They exhibited a network of a certain width and a certain depth. I don't remember the exact numbers, but I mean, the number of parameters was very small, like 40 parameters, a neural net with a certain activation function and a certain width and depth, and the depth and width were fixed so that the total number of parameters is like fixed, 48, something like that.
Mm-hmm.
And of course, the way they do it is in the activation function, they have sections of the activation function as you march and the activation function changes just as you have. You have sections, for example, in your sawtooth example, you have the ability to utilize an activation that is either one hat function or many hat functions. This is similar to like wavelets, right?
Mhm.
Or Fourier. And in fact, it's going up and down. And so, but anyway, my point is that any such space-filling manifold is necessarily unstable, right? I mean, you can't, how can you fill space with a fixed dimensional manifold without having the property that if you slightly change the parameters, you move very far in the space. It's necessary.
Mhm, mhm, mhm.
Yeah.
I think if you're given data, it's a
I mean, just from entropy, you can figure out that it has to be unstable. So the real question is, now, I argue against unstable methods, but somebody can argue, no, we'll allow stability, we'll allow instability. We'll just spend more time, right, learning the parameters. Instability means it's going to be very hard to learn the parameters. It's like tuning a radio, and you want to tune to a certain station. And since your radio has the capacity to learn every radio station, as you turn, you quickly jump between stations. So it's very hard to tune and find the right parameters. On the other hand, you can say, well, yeah, but if you don't limit me on time, if I have years to learn, eventually I can learn the right parameters to fit the function.
okay.
So I think that part has to be addressed.
Yeah, this part I understand. May I comment that this only when I see you have activating function using finite parameter to get the density. That's the activating function is not a really function. It's really they build all the because activating function already build all the density in there. They put the dense space into the activating function, not like you have like we have an analytical film for the activating function. They don't have. They have the basically you have use all the rational for the base rational linear combination for the basis. You got a countable dense set, then put each interval something like that. Okay, that's the difference. So this is basically you don't have activating function. You exist activating function. Secondly, that I'm hoping that for the classification, because the story is different. Classification now my function is in my hypothesis space. Whether I have a slightly better analysis or more stable, I hope for that. But I approve that for the classification function, it's just in my space, not just kind of approximate. It's in. You always have a one parameter. It is that function. Whether in that situation, whether we can do better, I have no idea. I have no idea. I'm not thinking of the arbitrary function. Say for the classification function, we already prove this function is in my space, in my hypothesis.
I don't.
Okay. I'm gonna sorry. I'm gonna break in. We're gonna have to move on to our next.
Okay.
Maybe you guys can talk offline.
Okay. Yeah, we can.
No, I think it's a great discussion. I'm really happy stimulating this kind of discussion. But we need to move on now to our next talk. So I'm happy to welcome Jin Xiao Xu, the Vern Williman Professor of Mathematics at Penn State. He'll be talking about training and analysis of numerical PDE by neural networks. Take it away.
Okay, thank you, Greg. Thanks for having me here. Thanks the organizer for having me here to give this talk. Today, I'm actually going to talk about some very simple questions here. So there's a lot of success, of course, deep neural network for things like image classification, natural language processing, and recently, of course, there's quite a growing interest in applying neural network for solving PDEs, and So the question I'm asking is that suppose you take any, let's say I call it numerical realizable discretization method to solve a PDE based on your network. How much can we actually prove about the convergence, like a convergence rate, like what I have here, without making any unverifiable assumptions? How much we can prove, do a rigorous proof. Another one I want to say that, how much accuracy can we actually numerically obtain without worrying about the mathematical rigor? I just say if I have an algorithm, I can implement it. And this problem has much to do with what Ron, Professor DeVos talk mentioned a lot about this, talking about a stable algorithm and stuff like that. And so to me, the answer to these two questions actually has not been very encouraging, because when I look at the literature, and there's always in there are many analyses, many papers, there's always come with some kind of assumptions. And when you see the numerical method, you see some kind of convergence of, especially when the number of neurons gets large, you stop somewhere. But when we're trying to repeat those tests, in my group, we can rarely see it. We cannot continue to get the asymptotics correctly. So I'm actually giving this talk here one way to probably because there's lots of papers in this topic. Frankly, I cannot keep up with them. And if anybody can help me to answer these questions, and you have, for example, you have an algorithm, you say you can observe the asymptotics and things like that, I'll be appreciate to know those results. So I would apologize that in advance if I miss a reference that this related to these two questions. Anyway, so I'm coming from a finite element background. I begin with a finite element method. So you talk about piecewise linear method. So this is a piecewise linear, and you usually have the basis function, we call a height function like this. And this base function can be written as this locally supported basis function can be written as some scaling and translation of this fixed things. So by writing this basis function at the top can be written, some combination of ReLU, which is the most popularly commonly used activation function. And so we can say that the finite element method is in this neural network, what we call. And so I'm trying to relate to this finite element. So you can think about a neural network is in this sense as some kind of generalization of finite element by freeing those nodes, moving arbitrary nodes and a grid point. You can also do a higher dimension. You simply replace this linear function in 1D by multi-dimension. You also get a piecewise kind of a linear function. And excuse me, may I ask the organizer to disable this security, let everybody in, because every time somebody want to come in, there's something show up on my screen. I'm sorry. Is that possible? You could go to security, you enable the waiting room on disable it. Then people come in not being asked. I would appreciate that because it shows up on my screen. I don't know why. Maybe I didn't set it up.
Okay, I think maybe it's disabled now.
Okay, I appreciate that. Thank you. It's kind of distracting me. I don't know why.
Sure.
And that's why I'll be doing the. Okay, and thank you, great. So again, I'm going to choose my very special activation function to be the ReLU to the case power. So if you do that, and this multi-dimensional this neural network function is actually a finite element of a piecewise polynomial degree k. And so you can also do this deep neural network. I guess in this audience, I don't have to repeat. So the interesting thing is that for the deep neural network, as a set of functions, the ReLU DNN with the deep network is actually the same as linear finite elements, what we do for ages. And if you do the ReLU of the k, and it's piecewise polynomials of higher order, but but it's different. Only in the linear case are the same, but it's going to be piecewise polynomials with on some kind of very strange grid, which maybe curved boundary or stuff like that. But anyway, there are piecewise polynomials. I'm interested in this kind of neural network functions. So approximation property. This again one of the things which again I'm going to mention what Professor DeVore just said about the stability issue here, and I'm going to actually address this constantly, repeatedly in this talk. So in this particular case, the stability is imposed in this coefficient sigma AI. This L1 is bounded. This is what I call a stable neural network approximation. And if you do that, you can also do more general kind of a dictionary. And so you given this M a priori, you just want to consider, what kind of approximation, what kind of function this what I call a stable neural network can approximate. And so you can think about this like a dictionary. You take the closure, if it's m equal to 1, that's called a B1D. And using this one, actually, I use this notation from Ron DeVore's this survey article, and they call it K1D. So you can treat this as the unit ball. So you can take the informal R such that if this R time in the like the radius R or F is in there, so you can call this the norm. And so then this will be the unit ball, and so then you define this K1D as all this norm is bounded. This is what we call this is actually you can prove it's a Barak space. And so the interesting thing is that one of the questions I asked earlier, and guys around mentioned quite a bit about the model class. So a natural question to ask is that for any function at all that can be approximated by my stable manifold, my stable neural network, what kind of function class that should be? So we identify here is that it is affine only if in this K1D space. So we're talking about the qualitative convergence in norm, the strong convergence, if it can be approximated by this this function class at all, and this function class 7, and this function to be approximated has to be in this K1D. So it's the minimal or largest function class that can do the job. So that's the qualitative convergence, but you can also have the quantitative convergence is that you can actually get this, this end of the negative half of things, which is shown in the literature everywhere. So so if again, it is very important to have a stable neural network. But if you have the stable neural network, then we identify the functional class. It is actually this K1D space. And in the most of the existing literature, you get to the end of the negative half. And it turns out for the ReLU to the case power, we can get this estimated 15, pretty much the upper bound, the lower bound matches. And you can get the extra power here, minus half minus 2k plus 1 over 2d. So what this means that if you have a function that can be approximated at all by this stable neural network, it has to be in this K1D. But if it's in K1D, in the previous page, I said it has to be n to the negative half. What we actually say is that you get extra power, minus 2k plus 1 over 2d, but this number goes to 0 when d increases, but nevertheless, this is the optimal bound. We can prove it's also a lower bound, probably some kind of logarithm. And that's, but if you compare this with the finite element method, and you would get a, if you compare these two, you actually get a better convergence. So now if you remove this this bound, sigma AI is bound. Now this is coming again about around what you call it, maybe this is not stable. If you don't have stable, then you have super convergence here. You can actually, you do have the super convergence n to the negative k plus 1. And if f is very sufficiently smooth, but again, this is what I call unstable approximation. So if you don't worry about stability, you can get a very high order of accuracy. And this is going to, if you compare with finite element method, and you can raise the power of d in comparing with the best of finite element approximation. That's really super convergence, especially for higher dimension. And but the price to pay is to remove the stability constraint. So we have a piecewise polynomials, and we want to use the numerically solve PDEs. So let's do some simple PDEs. Let's do this 2m's order. Maybe you can think of it as Laplacian. And the way to do is that even the higher dimension with high order, well, I'm talking about, sorry, I flashed it too fast here. You think about this PDE as like 2m's order PDE in any dimension. So I want to say I'm going to have to solve this by my numerical, my neural network. And so the interesting thing is that this, if you to the raised power, you can actually, this thing is a subspace of HM. In the finite element, you get a conforming method or even spline to get a piecewise polynomial. It's globally smooth. It's highly non-trivial problems. But in a neural network, it's pretty trivial. Now the question is that so this piecewise polynomial in this shallow neural network is going to be piecewise polynomial in this very funny looking grid there. And then let's take a Riemann boundary problem. The way I solve this problem here, I'm going to just do minimize this Dirichlet interval. If you do if surprisingly, you can actually do you minimize the Dirichlet interval, so you minimize in this case in the discrete in the neural network spaces, and surprisingly, you can actually prove it's still best approximation, even though this is a highly nonlinear optimization problem. And you can still get a best approximation, which is not pretty simple to prove. But if you did the best approximation, if you use the super convergence estimate, or you can use the stable estimate, you can get the error estimate. So, so that's the theoretical result we can prove for neural network. But I wouldn't call this a numerical realizable because you have other issues. You have, for example, numerical quadrature. So this is just only a theoretical issue. In practice, you have to worry about other things. But again, this has lots of super convergence. If you compare with finite element method, this is without worrying about the stability. But even when you put the stability into account, you can also get super convergence, but it's not so dramatic. So I'm coming back to the, so if you look at this comparing with finite elements, this is piecewise polynomials on curved elements. And you can get a very high order of accuracy. And you can even get a spectral accuracy when you increase the number of layers, and even k equal to 1, you can do spectral accuracy. And if k greater or equal to 2, you can reproduce a high order polynomial. I have some papers here I mentioned here for any arbitrary order. So I think this neural network function is kind of self-adaptive. Both, I would say, you can, because it contains a piecewise linear function for, we have proved that it contains any arbitrary adaptive locally refined mesh. So you can do local adaptivity, but you can also some global adaptivity. So it's kind of multi-scale adaptivity in some sense. So I find this kind of class is very interesting. But again, the question that how do you actually solve the optimization problem? There's many issues I'm going to address right now. So, for example, the how do you if you suppose you do the minimization of the Dirichlet integral, then you need to evaluate this integral. So we're gonna have to do it doing some of the numerical quadrature, okay, for 12. So you can do a different kind of numerical. There's actually quite many papers in the literature analyzing this with various different assumptions so I guess the two approach you can think about, you can do the random samplings and for this numerical quadrature. Then you can, again, maybe you can use the Gaussian quadrature. You can pick so in terms of the data, and you think of using machine learning language, and this integration point you can think about the training data. So then you want to say, okay, after this training data, if you do these things here, so how do you estimate the error? That actually what I would call the generalization in this context. So to do the convergence analysis with this numerical quadrature would be to do the generalization for this very simplistic problems of numeric PD. So we're doing the generalization sense. So if you go to the undefined element guy, when you go to the area analysis, if you do numerical quadrature, one of the things which is being used is what we call inverse inequality, 28, or maybe Bernstein inequality. If you take the higher superlative order, something in there, it will be bounded by a certain power, polynomial power of this number of neurons. That's what we call Bernstein inequality for the low order subgroup spaces. And many attempts have been made in the existing literature by using this 28, making the assumption the Bernstein inequalities actually hold to do the analysis. But the bad news is that the Bernstein equality does not hold for this neural network, at least for the reduced case power. We can construct a counterexample. You cannot prove Bernstein equality for neural network space. And we've done in this paper. So this analysis, based on the assumption of the Bernstein equality, would not apply to reduced case power. It could apply to the other ones, but I'm talking about the reduced case one. So the comparison again is this to solve this issue again is the stability. You need the stable neural network. The stable neural network again is the coefficient will be bounded. So in this case, now if you solve this, so you instead of H1 omega, you actually we restrict the function class in this K1D space. You minimize that, and so when you do the numerical quadrature, you also minimize this this function class is K1D. So the norm is bounded by M. That's pretty much equivalent of saying that the coefficient is bounded in L1. So we have worked out this analysis here. If you assume that this dictionary is bounded in the WK infinity norm, and if you do that one here, so because you choose, this has to do with the smoothness of the activation function. If they reduce the case power, if you scale the things appropriately, the 32 will be satisfied. So this means that this function class, my stable, this K1D space is pretty smooth, and And it's very small functional class. And this is what called around called a model class. But we're not talking about a very big logic class. We're talking about something very quite smooth here. That's the only the theorem can work. And in this case, you can do the numerical quadrature. You can prove the numerical quadrature because the integrand, which even in the discrete case is smooth, you can do the numerical quadrature. You can use, for example, if you can do a Gaussian, you can do the estimate 33. And so now, so again, we have two type of we have two types of discretization. But if you do the random sampling, again, you think about the integration policy is pretty much analogous to the training data from the machine learning language. And one way to one of the important quantity in this, when we do the generalization is Raman complexity. And I assume most of people know this, the definition of it. It's showing in 34. And we have proved that for Monte Carlo method, and if you do the, if you use our stable manifold, the stable dictionary or stable neural network, the 35 will be bounded. You can prove that this Raman complexity is bounded by n to the negative half. From there, you can say that on the 36 that we can prove that inside the stable neural network function, the K1D, this model class. So the Dirichlet interval, you have this n to the negative half, and in this case, you can actually, this is what I call the 37 is the generalization error, because you do the, in this case, if you do random sampling, it would be you do the expectation, and so now we can obtain the 37. So there's you have the sampling points, n is number of neurons, and if you balance that, you can. And now the question here that, okay, we have proved the 37. Now the question here is that here's something I need to get some help from the audience. So suppose you want to say, I'm going to minimize this or the Dirichlet interval. Suppose the most popular method used is the SGD or the Adam method. The SGD Adam method use the machine learning, of course, almost exclusively. But most people in the literature use this method to train this numerical PDE things. My question is that can you train the numerical PDE to see some asymptotics? We have read as many pages we could read and try to repeat what people report in the literature, and we just could not go. If you in the very beginning, if the number of neurons are not that many, you can work very hard at the other method. You see the asymptotics, but if the n is large, we just cannot do it. We just couldn't do it. You get things get flat. This is what I call a numerical error, and we don't observe the asymptotics. So again, there's a lot of Ron mentioned earlier. There's a lot of parameter tune what works as. I asked many of my students collaborate to work on it. We just could not keep going. When n is getting large, you just, no matter how hard you work, you cannot do it. And so I called people I know. So how could you do it? And for example, I called, I think like some people. They actually told me that, wow, this is what they also observe that is what some people call the optimization error. It's kind of, you have some kind of, and again, I think this this other method, or this method, when you train these things, there are stability issues. I think this problem is really, when you have this unstable method, or this which Ron mentioned repeatedly in his talk, is that I believe this is quite relevant here. You just, when n is large, it becomes so yield conditioned. This reminds me when you solve using Gauss elimination for the Hilbert matrix. When n is large enough, you just cannot get good numbers. And so the one I'm going to show you here is that this is my second. If you the first one, this is the numerical PD result I'm going to show you later on. If you do the other method, you afterwards just get flat. So we are using this thing called a greedy algorithm, which I'm going to show you in a moment. It's a different kind of training algorithm for this particular case. You do see the asymptotic. This is the point I'm trying to make here. This is what I call the greedy algorithm, which again is in Professor DeVos, and his group written many papers on this. There's something called an orthogonal greedy algorithm. And you solve what we call argmax problems. You pretty much if you take the data fitting here, you just look at the residual. You try to get the best direction in the residual direction, and you do the orthogonal projection. So you keep going. And sorry, I'm using two different notation here. In the numerical PD case, the residual is the gradient of this Dirichlet interval. So it's kind of the gradient descent because you're looking for the gradient direction, and which is matches the direction as much as you can in the dictionary. So you go from there. And this 40 involves this orthogonal projection, but the 41 is called a relaxed greedy algorithm. So every time you do is either a neuron or something, and you just keep going. So we have started quite a bit of a neuron, with I should mention that all this work is done by my postdoc, Jonathan Siegel, and we have written many papers on it. Jonathan especially spent a lot of time trying to understand all this greedy algorithm. In the existing literature, maybe wrong, you can correct it if I'm wrong. I think most of if all the results, the greedy algorithm can only achieve n to the negative half. And we just studied, okay, maybe we can do better for this special dictionary. Now, it turns out, if you take this stable K1, this PK, this Reynolds case power, we can actually achieve the optimal rate, 42, by using orthogonal greedy algorithm. Well, very, very happy with this result. And a stable method can be trained. Unstable method, we don't know how to train it. Stable manifold. We can prove. I believe this is the first result that is bit to the n to the negative half. I'm not 100% sure, but we couldn't find it. So so again we in this the stable neural network, we approved the 42 is the best approximation. But we can also achieve this best approximation by this greedy algorithm. And also the analysis I mentioned before. If you do the numerical quadrature, you do sampling, you also have to be in the stable neural network. So I can do the analysis. I can also do the algorithm. So from there, you can actually show if you do the relaxed greedy algorithm, because this is kind of a convex combination, you can actually prove that during the training process, my U of n is always stay in this K1D space in the same bound. Then you can prove that this target function is bounded by 1 over n. But there's one open problem right now. When you do the orthogonal greedy algorithm, we have not been able to prove this one yet, because but numerically it works very well. Anyway. So you can, so that, but there's a, this, what's the greedy algorithm? But there's a catch. You have to solve this, what I call Argmax problem. You find this best possible direction in the dictionary. This involves a d-dimensional optimization problems. Everybody, we all claim the neural network is going to be great for high-dimensional problem. I'm just asking a kind of naive, a simple question. And for let's even worry about the low-dimensional problem. For the low-dimensional problem, this is a feasible thing to do, but you can maybe do brute force. That's what we did in the numerics. But the larger D becomes a high-dimensional problem. Then you have to also worry about these things. There's some books, I think, working, various literature people talking about these things, but we haven't. But the way we do is that we just brute force solve for 1 and 2 and 3D. That's is doable. By the way, with this greedy algorithm, we can achieve this bound, asymptotic bound numerically. But we do not know any other method, SGD, other method. We could not get them to work to get a asymptotic rate. We just couldn't get it. Again, if anybody in the audience, you know, I'm sure that many people know better how to tune this other method. And so we can talk about the numerical experiment here. Sorry. So for example, I'm going to, again, I think Ron mentioned you fit the x square, you do the SGD. It's very difficult to fit the x square to use SGD or other method, but it is pretty easy to fit by this orthogonal greedy algorithm. You can actually see that we actually proved, of course, in this stable, neural network and stable function, then you can actually achieve the best approximation. We actually numerically realize that you can see the asymptotics. Increase the number, if you increase the number of neurons, you see the asymptotics, but you cannot see that in the. For example, I can take this one-dimensional problem here. And again, you can use the orthogonal greedy algorithm. You can achieve the asymptotics by provided by our theorem. But now, suppose you want to solve this by other method. Again, if you solve this by either method, in the beginning, this either method looks very good from like n to the 248 neurons. Actually, get a pretty good accuracy. But if we increase the number of neurons, you iterate hundreds of thousands of iterations, you adjust the learning rate, and all that. And we just couldn't get it. You get flat. This error will get flat. But well, the greedy algorithm, you get the asymptotics rate. You get all the way to 512, you can keep going, you get that. But not by either method. I'm not talking about theory here. We have a theorem for the greedy algorithm, but I'm not talking about the theorem for, but I'm talking about just practically you tune your method to see the new, suppose maybe use your computational power, computing power. If you use a bigger computer, you do a larger n. Can you observe the numerics? But when n is getting large, we just couldn't do it. Again, maybe somebody in the audience will know how to do this. And you can actually, I mentioned this earlier that the neural network you kind of have the self-adaptivity. You can do a local adaptivity, global. It's all in this optimization algorithm. You can just, there's an underlying grid in 1D, but if we tested some kind of singularity, it gets it right, actually. And You can do a first order problem. You can also use the greedy algorithm and get a pretty good asymptotics. But again, if you do the other method, there's no way we could do it. After a while, we just couldn't get it anywhere. You can do 2Ds also. And so in this, we can, we have the theory for the linear problem, but we can prove, but the non-linear problem, we don't have a theory, but we run the non-linear problem, we still get the predicted accuracy. Oh no, the accuracy like in the linear problems. And so we use we also tried some other non-linear problems, Poisson Boltzmann and all that. You still get good at you see the asymptotics numerically. But again, we're still doing the theory. So so I want to summarize the things that I like this deep ReLU K because neural network, because the piecewise polynomial of the degree of piecewise polynomial of continuous function, so very closely related to finite element methods. And so you want to do a comparison of so you total. Now the question is that this kind of functional class, what kind of functional class, or maybe model class, this kind of neural network can be approximated. If you impose the stability in this neural network spaces, so the function class is this K1D is this what in the statistical literature is called a variation space, and in deep neural network, some people like Weyla, Professor E would call it a Barron space, and we can call it a Barron space in general. And it is the largest space that is for stable approximation, in the sense that the coefficients L1 is bounded. It's the largest. That's the if and only if things. For the ReLU to the case power, we can get in this functional class, we can get this optimal error estimates. This optimal is because you get an upper bound, you also get a lower bound. And the third one, I'm just thinking which were very high, is you can, now it becomes, when you have a stable neural network, you can actually train it, you can actually get it in terms of, well, by this orthogonal greedy algorithm, we can get the same rate. But if you, so this of course, it amounts to solve a optimization problem of D dimension. If D is larger, that I mentioned there's an issue there. But but if you remove the stability, you can get a super convergence. And again, so when you do the analysis for the neural network for the solving the PDE, and we'll emphasize that the Bernstein inequality doesn't work. We have counter example. So you cannot use traditional methods to analyze it. But Bernstein inequality is satisfied if you do the okay, I'm saying the Bernstein inequality does not work for the neural network space. It's for the unstable one. If you do the stable one, it's okay. Actually, I'll be more specific. If you do this work in the stable neural network, you can do the convergence analysis, very rigorous. And then again, use the greedy algorithm to solve the discrete energy minimization. You can numerically observe, we can also theoretically prove. And, but we are not able to do this for other method numerically. And now we're all kind of excited these days, many people using neural network for numerical PDEs. But somehow, especially for high dimension, but my experience or what I know, my group with my students is that there are lots of practical theoretical issues. Practically, it's just very difficult to solve that optimization problems. And if you get most of the paper in the literature, you get a 10 to the -3 accuracy or something like that. But you cannot go down. You can go down further. So anyway, this talk, again, if anybody in the audience will know better in this topic, I would be grateful to know the literature. But in this talk, we try to provide the answer to this question somehow. One of the key issue here is the model space. Is this K1D, is the stable neural network space? Then you can do the analysis, you can also train it somehow, and then you can prove some theorem, you can numerically also looks good. And but these are some papers which you can find from archive, and some of them published. And I'll stop here. Thank you very much.
Great. Well, thanks very much. Looks like we have a few minutes for questions. If you go to the bottom of your screen, there's reactions. You can raise your hand that way. It looks like maybe Guoji has a question to start. Is that right?
Yes. Thank you for the talk. So you have mentioned that there is a stable approximation and there is a bound. How to have the estimate for this bound for the coefficients?
How do we prove it?
Yeah, how to get this bound basically.
So first of all, you want to you can do the we did some using the sum. You can actually do a sampling argument, and you do technically sorry, you can find it. I don't know if you want me to go through I don't have I used to have an outline of the proof, but it's in the papers. Yeah, we have proved that. Wait a minute.
So you have the bound for the coefficients of the neural network, right?
Yeah. This is important. This has been used in I think it's around the walls of papers, and I would do it in this is in this one. Then you get this bound, which we actually say is optimal. Actually, this is something we're very happy about it, and it's optimal for you get a lower bound as well. Yeah. And but if you remove the stable assumption, you get a super convergence. You get a higher order.
Okay, Jintao.
Yeah.
How big is your K1D space?
That's a small space, I think.
Okay. Also your K1D.
But if you do here's the issue. I don't know. There's lots of claims in all these things works in high dimension, all that things.
Your results is working for any dimension, but it's a one layer, right? Oh, not the multi-layer, right?
This is one layer. The multi-layer, is a bigger issue.
So, do you have a definition for multi-layer for the K1D space?
You can always talk about in terms of dictionary. You can do a lot of stuff, but it's not so. The answer is that we've been working on it. I think Professor for example, he has his Byron space of renewal. He has some paper written with some.
Yeah, he also basically in a few layer, not a many layer. Many layer. Also,
he has written.
I asked him. Yeah.
He has written some papers on it, but this seems to be very difficult problems.
When one layer become bigger, yeah.
But one layer, okay. To answer your question again, I don't know. Suppose you want to be, if you don't want to be stable, we can do all the weird. You can, for example, the beautiful result. You do the space filling manifold, whatever. You can only need a few parameters. You can do lots of stuff. But if you want to think about stability, in this notion here, you can do the L1 stability of the coefficients outside of the iteration function. If if you want to do any analysis at all, like for example, numerical quadrature, I couldn't get around without that assumption. And we can also use a greedy algorithm to train that one, which is good, encouraging. And so stability assumption, which Ron mentioned many times, seems to be quite necessary. Okay, if that's what you accept, then the function class is K1D, not more, nor less. It's just that function. Okay, now the question is that function is quite small.
Yeah,
now the question is that, okay, why do you even, now the question, one of the questions here is that, this works for any activation function, even though I just say reload to the case file. You can, now one of the interesting questions is that what kind of activation functions in the world out there, you give the largest K1D. We don't know the answer to that question yet.
Okay,
Maybe,
but
Okay,
also-
okay, hang on. I'm gonna cut in here in just a minute. We got a couple other questions, and then we can stay on after the final talk during lunch and have more discussion then. Ron, did you have a question? Quick question. We don't have much time, but maybe a quick question.
Well, more a comment. First, thanks, Jin Zhao. I thought it was a very nice talk.
thank you.
I think one of the main points you're making is that to do the optimization, we don't have to wed ourselves to gradient descent or SGD, that there are sometimes better alternatives. And
Yeah,
greedy
exactly. It's
algorithms-
actually the algorithm you studied. Yeah, right. But the SGD item for me is hopeless. Or correct if I'm wrong. Anybody out there?
Okay, and Raghu, did you have a quick question?
Really quick question. Thank you again. Very nice talk.
Thank you.
Can you comment, please, on how you chose your mini batch size or sample size when you're running SGD or ADAM? Did you scale it with as the number of neurons increased when you try to observe the asymptotic rate?
Reduce the variance or stuff like that. But we tried many things. I'm not the very best person on my group. I call somebody like George's group, like Lulu. I just say, okay, tell me, how do you do it? So he has a beautiful pictures. But the thing is that, again, then I ask him to do a larger N. So I have a student work with him. So actually, too many days, okay. No success.
Thank
so I don't quite know we tried many different things we could try, but we did, of course, change the mini batch size. But whether we get on the right track, I don't know. Sorry.
Okay. Okay. And Plamen, you have a quick question?
Yeah. Can you hear me?
Yeah.
Yes.
Okay. For those type of elliptic equations, most of the action happens near the boundary because the equation is elliptic and inside it stabilizes very quickly. So will that method capture some oscillatory behavior near the boundary? I mean, the L2 norm doesn't really capture this behavior. So that's my question. Does it adapt to put finer mesh, roughly speaking, near the boundary if needed?
Again, this all has everything to do with what training algorithm you do. Theoretically, yes, because I can prove that the neural network, if you increase the depth, the layer, it captures all the adaptive finite element method. And now the question is, can you train to get there? This is a big open problem. Theoretically, yes. Practically, I don't know. No, I don't know. We don't know how to do it.
Okay, let's stop there. Unmute for a second, and we'll give Jin Zhao a round of applause. So thank you very much.
Yeah, thank you for the great question.
Thank you.
Shoot. No. Okay, and then let's see, are we recording still? Okay, looks good. Okay, so I'm happy to welcome next Zhanfeng Liu, professor of mathematics, chemistry, and physics at Duke University. He'll be speaking about a priori error analysis for solving high-dimensional PDEs based on neural networks.
Yeah, before I start, I would like to thank the organizers for putting together such a wonderful workshop and also giving me the opportunity to share with you some of our recent results here. And in fact, I will continue what Professor Xu has started on the topic about numerical analysis for neural network-based methods for high-dimensional PDEs. And what I'm going to talk about today is joint work with a former postdoc, Yulong Lu at Duke, who has moved on to a tenure track position at Amherst, and also Ming Wang, who is a current postdoc at Duke. Okay, so my focus is really kind of thinking about how to get error analysis for neural network-based methods for PDEs. And more specifically, I will be only interested in high-dimensional PDEs. Okay, so as you have heard already from Professor Xu's talk, typically what we observe is that if you're using neural networks to solve a PDE, and the error sort of saturates at 10 to the -3. Okay, so coming from a classical numerical analysis scientific computing background, we know that, well, if you want to solve Navier-Stokes equation to the accuracy of 10 to the -3, I mean, there are plenty of methods available there, and neural network isn't the most efficient one. And also, I mean, if we solve like easier PDEs, like Poisson equations, and then, I mean, we even have fast solvers, and why on Earth we should use neural networks, there was really no point. But I mean, to me, I mean, I think the possibility that neural networks or the machine learning type methods opens the door for us is really try to tackle the numerical PDEs in very, very high dimensions. I'm speaking of like thousands and millions of dimensions, which is even 10 to the -3 is already very satisfactory. I mean, because if you're using conventional methods, there is almost no hope to solve such PDEs within practical computational budget. Okay. And also for those of, I mean, maybe you haven't seen some of these high-dimensional PDEs, so let me just try to give a list of examples to convince you that these are actually very ubiquitous and I mean, fairly fundamental to many branches of science and engineering, including the many-body quantum systems, which is of one of my main interests. And also, like, if you want to have a phase-space description of chemical reaction systems, Fokker-Planck equations, or interacting particle systems, these are also high-dimensional PDEs. And also for high-dimensional control problems, you can easily have a Hamilton-Jacobi-Bellman type of equations in 100,000 dimensions if you have like 1,000 control variables. And also, I mean, if you want to kind of do some financial math and you want to do asset pricing on stock market with, I don't know, 1,000 assets, then it's a kind of Black-Scholes type of things and with 1,000 dimensions. So there are many applications, but I'm not going to focus on all these applications, but I mean, rather want to think about the questions that we can ask as a numerical analyst or like PD analyst. So one of the motivation to study these is, of course, I mean, these are possible approaches to solve these high-dimensional PDEs, which again, I mean, are almost impossible for traditional methods. And another interest to me, like from a trying to analyzing the PDE perspective and a PD analysis perspective is that, I mean, oftentimes when we develop, I mean, when the PD theory was developed over the past 100 years, maybe, most time the focus is not really in a dimension. So that, for example, I mean, oftentimes if you open a book of Gilbert-Tudinger and you see, okay, so there was a constant and the constant depends on somehow on the dimension, and it was never explicit. And in fact, if you trace the proof, sometimes the dimension dependence could be really bad. Because, I mean, it's not like we cannot get better estimates, but just because when we develop theory, we have PDEs of 3 dimensions or 4 dimensions in mind, so we never care about that explicit dependence. I mean, how bad it could be, right? But if you now want to start to think about numerically solving PDEs in 1,000 dimensions, then the constant really matters. So that's also, I mean, whether we can get better solution theories or regularity theories for these PDEs with better dependence on dimension or more explicit dependence on dimension. That's also one of the motivation. And I also rather to say that, I mean, this is not, I mean, I don't think this is just application of machine learning, but it also provides a very good platform to understand the performance of some of the machine learning algorithms. Because, I mean, in the PD setting, the numerical PD, I mean, we have really well control of everything. For example, we have control of the sample points we choose. It's not given by practical images. And we know, I mean, kind of a priori estimate, like what kind of approximation error we can hope for. I mean, because we know the function. I mean, in principle, we know the regularity of function, while in the like ImageNet, I mean, you do not really know the regularity of the classification functions there. So I think this could also provide a very good test bed to theoretical development for machine learning and deep learning in particular. Okay, so enough on the motivation. So I don't think I need to really go deep into these kind of basics about numerically solving PDEs, since many in the audience are really experts and in this topic, and also approximation theory. But let me just quickly recap. So what you typically need to do if you're facing a PDE in very high dimension, let's say, is, I mean, to put it in a computer to numerically solve it, I mean, first, you need to decide how would you represent the solution, right? So in the sense that because the computer, I mean, we're talking about numerical computation, so that you only use finite number of degree freedoms. And so how would you represent this kind of infinite dimensional object, this function, using finite dimensional degree of freedom? And also, once you decide about that approximation space, then you need to find the candidate to kind of approximate the true solution, right? So, I mean, we have seen this morning about all these approximation theories, so that I think I can go quick. But I mean, it's the traditional PD, numerical PDEs, all in a sense based on these linear approximation ideas. So you fix a basis functions, and then you trying to find the best linear combinations of them, right? So that this is essentially like a one-slide summary of finite element. Okay, and also spectral method and many others, I mean, depending on what kind of approximation space you choose. And the issue that we sort of know if we want to go to high dimension is that such approximations face the severe curse of dimensionality. And also, as you have seen in Professor Wall's talk and also Professor Xu's talk, I mean, so you can do M-term approximations, or what I would call just a nonlinear approximation with a fixed dictionary, like what we do in wavelets. And in the PD context, this is sort of like the particle methods or mesh-free methods and so on. And so, I mean, also in the quantum chemistry, these are called selective CI and so on. And these methods, as we know, that are more powerful and provide a better approximation rates. And then we have the neural networks, which is like the what I mean we think about as like manifold approximation, or I mean a general nonlinear approximations. Where, I mean, so I don't think I need to kind of specify the form of neural networks, but most of this talk, I'm going to talk about the two-layer neural networks, so that there's one activation function and then some weights. And collectively, let's just denote all these weights as some parameter theta. Okay, and now, I mean, it's kind of like we have a nonlinear, I mean, it could be smooth manifold, or it could even have some singularities, Lipschitz, things like that. But in general, we just have a nonlinear family of functions that we can use to approximate. And the approximation class is no longer a linear space, and no longer, I mean, it's kind of a complicated object. And I mean, so we can use these things to approximate the unknown solutions to the PDE. Let me also mention that this is actually not only I mean, this framework is not only for neural networks. Actually, even before the the popularity of deep learning, people have been trying to use such framework to solve high-dimensional PDEs. For example, one of the sort of series of works is try to use tensor network-based methods, or I mean, depending on which community you're from, you can call this tensor train or the matrix product states, and so on and so forth, to use for high-dimensional quantum systems. And I mean, it's kind of like a multilinear parameterization, because now you're trying to parameterize the function as a tensor instead of a linear dictionary. And there was also in the world of quantum chemistry, because these people need to face high-dimensional PDEs from the beginning of their field in the 20s. So they already need to solve like PDEs in 100 dimensions, and they develop various kind of like so-called wave function methods in terms of parameterizing the solution to the Schrödinger equation as a nonlinear parameterization, and trying to develop numerical methods to find a solution of these. Actually, I mean, maybe for people who do not know that, I mean, actually a lot of the machine learning techniques are very similar to the techniques that independently developed by the chemists and physicists in that community. For example, the SGD is called variational Monte Carlo there, and there were, I mean, other many related things that were independently developed. In fact, sometimes actually earlier than the machine learning people and also computer scientist people. Okay, so now, so let's say that we fix some approximation class already. Okay, so FFM, and our focus will be on the neural network space, but let's still stay on a bit of abstract level. So we want to find, I mean, numerically, we want to, I mean, once we determine this finite dimensional space, we want to find a kind of candidate U to approximate the true solution of the PDE. Okay, and I mean, so there are many ways to do that, but I mean, I'm just going to focus on some sort of like, I mean, most how to say, I mean, adapted to the neural network or the machine learning kind of style of the method. So in the sense that we want to come up with a kind of functional or variational problem, and we try to determine these parameters by doing some optimization. Okay, I mean, could, for example, using SGD. And also, we need to be a little bit more specific, because, I mean, as we know that for different PDEs, I mean, the numerical methods for solving different type of PDEs could be really, really different. And now for this talk, I'm also going to focus on this kind of specific elliptic PD type problems, which is a bit. I don't want to do Poisson because Poisson is almost explicit. So that this is the kind of like Schrodinger equation from quantum chemistry of quantum mechanics, and so that the elliptic operator is just the bare Laplacian and plus a potential term. Okay. And so, and then, for simplicity of the discussion, throughout the talk, I will going to assume natural boundary conditions, or non-boundary conditions. But some of these theories can be extended. Okay, and also to be simple, we are going to, neglect the, because the problem is already difficult in high dimensions, so let me not adding additional difficulty in thinking about really complicated domains. So we are just going to focus on the very simple high dimensional cube. Okay. So now, what can we do, right? So that, there are, I think if you open up the book for numerical PDEs, and the first thing that you can think about is that, well, we can rewrite this PDE in equivalent forms. And one popular way, I think in the deep learning solving PDE context, they just use a strong form. Okay, which is essentially just like you want to solve AX equal to B using residue minimization or L2 minimization. So this is, sometimes people call this ping, but I think, the name is not really important. It's just using strong form and putting the ansatz. Okay, so that this is the L2 residue of the equation. And this is some penalty for the boundary term. And you are just writing down them explicitly. And this is the variational form. And this is the variational principle that you want to solve. You plug in the ansatz of U and doing some minimization. Okay, and one caveat, and I just want to mention, is that one thing that you see is that sort of the boundary condition, even if it's natural boundary condition, is sort of putting here as a soft penalty. So you need to kind of tune the penalty parameter to make sure that the boundary condition are satisfied or approximately satisfied, and which typically requires a large penalty so that increase the condition number or difficulty of solving the problem. And alternatively, of course, one can try to encode the boundary condition into the ansatz, but depending on the task, this could be easy or not easy to do. Another thing I want to sort of point out is that you see that we need to, because you're using a strong form, so that you need to use twice the derivative here. Or if you kind of rewrite it into a PDE, it's actually corresponds to a fourth order PDE. So depending on whether the PDE type, also the activation function that you will try to use, this may or may not be an issue. Okay, but this is a potential concern of using a strong form. There are also people trying to use weak form, so just like what we do in the Galerkin type of methods, but now you're testing it against a function. Okay, and so you're testing against the U, and then you're trying to solve a soup or saddle point problem. This is, kind of related with the GAN business in the machine learning context, because there also one need to solve a saddle point problem. The optimization could be difficult, but there are also some works following along these lines. But what I'm going to focus on most, which is also kind of related with what Professor Xu discussed earlier, was to use the variational form, because we are solving an elliptic equation. So that, I think, naturally, this is sort of the most natural framework. Okay. And this is, essentially what we do in finite element. And also, this is like, we are combining the finite element idea with the neural networks. Okay, so the variational form, we rewrite this PDE as the energy minimization with some right-hand side. And so from variational form, we know that if we solve this, the energy minimization, if we do it in H1 space, okay, and then we get a true solution of the PDE. Okay? And now the natural business to do, which is, this known as the Galerkin method in numerical analysis, is that, okay, so now we have a smaller, in principle, we have a smaller function class, which we call F. And now we want to find the approximate solution among that approximation space, by doing some minimization. Okay. And so, I think the earliest reference to write these down is the deep Ritz method by Wei-Na and Bing Yu in 2018. And we sort of did that without knowing their work, but then realized that actually, realized that they published the work before us. Okay, so that I will just go to use the deep Ritz method as a name, which is quite natural. But then again, the question that we really want to ask is that, okay, what is error? Okay, so that if you do this. All right, so let's think about, how to approach this problem, right? So that we have this UF, and we want to know what's the error, between the UF and U star, right? U star is our true solution. And because we're doing elliptic PDEs, I think the most natural way to measure this error is H1. So, that's what we're going to stick with. All right, and then, the standard roadmap for numerical analysis for such problems is, of course, the first is consistency. This is like, in the language of approximation theory, this is asking about approximation error. So in the sense that, whether we know that the true solution of this PDE lies close to our approximation class. Okay, so whether, this error is small, where the approximation class, I denote the best approximator to be U tilde. But of course, the consistency does not guarantee that the method would converge, in the sense that UF could be very different from the U tilde. So we also kind of need to say about stability, in the sense that if, whether I found by this kind of minimization here, whether the solution I found is close to the best approximator I can find in the class, right? It cannot be beating this because this is the minimum, but I hope it's not too worse. In the final element, this is no CS number. So, whether we can have a kind of analogous result here. And then if you, simply if you combine the consistency and stability as usual in numerical analysis, then you get convergence, right? So that we can show that these two are close. But also, as already kind of mentioned, actually, if you want to use this framework for neural networks, it's actually the problem is not that simple. So that we actually need to face additional issues. Okay, so the additional issue is the following in particular. So that this is sort of related with the numerical quadrature issue that we face in traditional finite element. The point is that because recall that this thing, this EF, I'm not going to write the full thing down, but it involves terms like this, right? So that we are doing a high dimensional integration in a d-dimensional cube, or with some kind of potential and so on and so forth. And so it's just hopeless to get this thing accurate. Okay, so especially if you're using a very complicated activation function and you're using neural networks and so on and so forth. Okay, so here, to practically use these methods, you have to approximate the energy function by something that is practical, kind of possible to compute, right? So this is kind of like numerical quadrature. So which I denote as E of n. Okay, so n is the cost of this numerical quadrature. And because of this, so instead of solving the original problem, in practice, if you want to limit your computational budget, you don't want to kind of waste the whole time to evaluate this numerical quadrature and without getting the approximate solution. The only thing that is possible to minimize in practice is actually a surrogate, right? So that this is kind of related with the empirical loss function in the supervised learning language. And instead of finding the UF, okay, which is the true minimizer within the class, you can only actually find a UN, which is like you're minimizing something surrogate. Okay, and now the error between these actually typically, using the language of machine learning, these are typically called generalization error. And or if you want, using the language of numerical analysis, this is kind of like the error due to the numerical quadrature. And we hope also that this error is small, right? So that, because, we following the usual standard consistent stability, we can show that UF is close, but now we also want to hope that the UN, which is the minimizer of a slightly different energy functional, is close to the true minimizer within the class, okay? And then there is also another very difficult but important question is that in practice, now somehow we come up with this surrogate or empirical loss, okay? And we need to kind of solve this optimization problem to get UN. But in practice, this is a very challenging problem. Because of the non-convexity of the energy minimization with value of theta and so on and so forth. And there are many methods have been developed. So popular methods, SGD and ATOM, and also we have heard other kind of orthogonal pursuit type of methods in early talks. But overall, I think it's very hard to guarantee that, in practice, these optimization procedure will give you actually the UN, right? It will give you actually the true minimizer. So there was also this approximation error or approximation guarantee, which is very hard to deal with. Which is kind of one of the central problems in understanding machine learning, except in some of the simplifying regimes that maybe one can say something, but but in reality, in practical cases, it's just very hard to get any guarantees for this. Okay, so now let's just recall that we have these 4 issues to face. Okay, and also, I mean, because one advantage that we're using the variational form or we are using the rescalar is that stability is actually automatically guaranteed because, I mean, so if we want interest in H1 and we're minimizing the energy, and because we can use the energy to control the H1 norm, so that this is just coming from the continuous PDE, and this is the advantage of also of finite element because you just inherit the stability from the continuous formulation to the discrete formulation. So we don't need to worry too much about stability. And also, as I said, the optimization guarantee, this is, I mean, as I already alluded to, I mean, and also we have seen in various previous talks, I mean, this is not something that we can really say much about, and neither can us, I mean, except, as I said, in some of the overparameterized regimes, so that it's actually not really nonlinear anymore. So it's very linear and the neuron tangent. So, I mean, I don't want to go to that regime. I mean, if we want, we can develop theories too. I mean, focusing on that, but that's not something that I will focus on today in this talk. So that what I'm going to really talk about is these two errors. One is approximation error, and we have seen from several previous talks about these things, and also about generalization error that, I mean, maybe less, not as much from the previous talks, but also I think play an important role in practical solutions to these numerical PDEs. Okay, so just to recap a bit, right? So that we're going to consider, so because we're not going to consider optimization guarantee, which, I mean, just remind you that this is what I denote as UN optimal. Okay, so that, I mean, getting from optimizer. So, I mean, I'm not going to consider this guy. Okay, so that I'm going to only consider the difference between the solution. So UN is the solution of the, I mean, within your class of, sorry, this class is FM, and of this surrogate functional. Okay, and where U star is the minimum within H1 of the true energy, and UF is the minimum in the class of the true energy. Okay, so I'm going, I mean, so now just to recap, I mean, the words, that terminology that we use, I mean, but because the different community using different language, but just to putting us on the same page, what about interesting is the difference between the UN and, the UN and the U star, the true solution. And due to stability, we know that it can be controlled by the energy difference. And now we're going to separate it into two errors. One is the error between the UN and the UF. I mean, due to stability, this is really equivalent with the H1 norm, so that I'm just thinking about energy difference. So what is the error between UN and UF? So that this is the generalization error, because this is due to the fact that UN is actually not minimizing the true energy, but minimizing something that is surrogate. Okay, and then this guy is the difference between, I mean, it's caused by that, the fact that I'm using a small function class rather than H1 to solve the problem, so that this is the approximation error. Okay, and one thing that is already obvious is that if I enlarge the approximation class, okay, so then certainly, I mean, my approximation, the UF, was getting better and better, because, I mean, since I'm putting more kind of possibilities into this minimization here. And in here, in the terminology of the approximation error, so that approximation error would get smaller if I'm using a approximation class that is larger. Okay. And but on the other hand, for the generalization error, okay, so now let's be slightly more specific about these numerical quadratures. And what I'm going to consider is, I mean, so it's one of the most natural approximations. You can do something more sophisticated, but I mean, for the analysis, let's be somewhat simple-minded. I mean, I'm just going to rewrite the original energy, which is, I mean, recall that I wrote it as an integral before, okay? But I mean, of course, this integral is just the expectation of a random variable within the uniform distributed within the hypercube, and then I putting all these terms in there, so I rewrite this integral as expectation, okay? And I do a numerical quadrature, and as I said, the most natural thing to do is just do Monte Carlo. So that's what I'm going to do. So I would define the, this is like in the machine learning language, this is the population loss, or the energy functional in the variational language, or the numerical analysis language. And I'm going to do the empirical loss, okay, which is En. And now remember that N indicates the number, the computational cost of doing this. And the N correspondingly, more specifically to the Monte Carlo, what I'm choose is that N is the number of quadrature points. which is I desampled according to this uniform distribution in the cube. Okay, and then I just doing Monte Carlo summation approximating the expectation. Okay, so that this is the, I mean, so in this language, you can understand the generalization error. It's sort of kind of like the worst quality error, because I mean, we do not know which U we need to deal with, because I mean, we do not know a priori what UN or what the solution, numerical solution that we will get. So we want our quadrature to be uniformly good to some extent to all the functions in our approximation class. Okay, I hope this is intuitive. And now, because of that, right? So this is the kind of the way that we're going to measure the error. I mean, in a sense that, I mean, in the best scenario, you know UN. If you do a posteriori, for example, then you can estimate the quality error posteriori. But since we want to do a priori analysis, so that, I mean, we can only be pessimistic, and we assume the worst error there. And so the worst error, I mean, of course, would get larger. I mean, if we get a larger, we use a larger approximation class. Okay, so in other words, at least in this way of thinking about generalization error, is you see that generalization error would get worse if you're using a larger approximation class, so that it's not the case, I mean, even aside from computational cost, it's not a case that when solving these numerical PDEs in high dimension, the more complicated approximation class you want to use with trillions of parameters, the better. Because also remember that if you're using that, then you need a very sophisticated way to get, so to ensure that the empirical loss that, I mean, the get that you want to minimize is actually giving you something that is close to the true minimizer. Okay. So in practice, actually, one need to get a kind of a balance or trade-off between the approximation error and generalization error. I mean, used by choosing the appropriate approximation class. Okay, is that so far so good? All right. So I mean, many of these things are kind of really like the background, and also I mean, just to fix some terminology for people coming from different field to understand what I'm going to talk about. And now to address all these errors, I mean, the two errors, right? One is approximation and then generalization, and especially the trade-off between them. Our approach, I mean, there are several ways of thinking about these. And as I mentioned already briefly, there are certain prior works that trying to do things a posteriori, so that you assume that you have access to UN, which is your numerical solution, and then you analyze what the error is. But I mean, we want to take a more a priori step, in the sense that given the PDE, we do not want to assume that the solution has certain regularity. I mean, because that defies the purpose, right? So, I mean, because we do not know the solution yet. And so in order to achieve that, to a priori analysis, so as have been already discussed in Professor Xu's talk, you kind of need to develop a function analysis framework, or try to develop like regularity, I mean, or try to decide which kind of function space that you want to use for these high dimensional PDEs. Okay, so in some sense, you're asking the question that what kind of function space that you want to put this true solution in. All right, and then the most natural class, I mean, at least for numerical analysts, is that, okay, of course, we use Sobolev and Holder spaces. The reason that is natural is because that we have been using these for, 100 of years, and then these are very classical, and also a lot of theories are well developed. But one thing that I was also want to mention that, which I already said in the beginning, is that it well developed in the sense that people don't care about dimension dependence. Okay, so if you actually dig into the real dimension dependence of many of these results, actually they are either very implicit or very not optimal in the conventional way of doing this analysis. So that, I think there are still a lot of work that has to be done, even if you want to stay with Sobolev spaces, okay, or Holder spaces. And one thing that, which is sort of clear, from today's talk, is that they are in some sense really not suitable for high dimensional problems, because these function space is just too large. Okay, unless you assume, of course, a crazy amount of regularity. For example, if you assume that the function is in Sobolev space in 1,000 dimension, but it's 2,000 times differentiable, of course, then the space is small. But let's say that we are solving elliptic PDE, and a priori we only know H1, and then the space is way too large. And then the complexity grows exponentially. And so that, even if we know that true solution is in H1, that doesn't help us too much if the PD is in 1,000 dimensions. Okay. And so now, in some sense, because of this, we really need to restrict ourselves to smaller function classes. And in particular, a recently becoming kind of popular choice is that for analyzing supervised learning and for other neural network tasks is to thinking about the so-called Baron type spaces, which of course by the name, originally kind of goes back to Baron and has been, I should say that all these spaces, well, I list these references here, including what's been mentioned in the previously in Professor Zhu's talk. They're not exactly the same. Okay, so there are several different types of the same thing. Of this similar idea. The basic idea is that you want to develop a function spaces that are well suited for the two-layer neural network approximations, or in some cases slightly higher ResNet or multi-layers. But then, the way that people approach the problem is slightly different. So sometimes, in the original idea of Baron, which I will recall a little bit later on, is to use the Fourier expectation, which is and kind of is L1 spaces in the Fourier parameters coefficients, and which is very similar to the F1 spaces that Francis Bach used to think about neural network approximations for supervised learning, and also analyzed further in Baron's work. And now what Weinan and his students, collaborators has done is slightly different, because they are kind of thinking about neural networks as particles, and they think in terms of kind of a mean field approach in a way, so that they want to represent the function classes that can be approximated by a distribution that is kind of fixed with a fixed activation function. So these two things are slightly different, but they're of similar flavor. And the most kind of advantage of why people are looking into these spaces is that they're kind of well suited for high dimensional problems. And for example, these spaces here, which I'm not going to talk about it because they're probability. So that if you think about kind of you do an empirical approximation of the probability and do a kind of a usual, you view each neuron as a particle, then you get a natural 1/n² convergence. Okay, but the downside is that as far as we know that, so there was really, not much theory, built, when we are starting to work on these things, there was not much solution theories to marry these spaces with high dimensional PDEs. Except in some very, as I said, in some special cases, if you can write down the explicit solution, of course, then you can verify. Okay, so now to be slightly giving you some more precise formula, so that this is our way of using the Baron space. It's also slightly different from others because we have to do it on a compact space. We're doing the high dimensional cube, and also we want to build in the natural boundary condition. So instead of Fourier, we do it the cosine because of the natural boundary condition. And this is the flavor of the original, next slide. This is the flavor of the original Baron spaces that defined by Andrew Baron in 1993. So that he is doing some kind of the weighted L1 norm of the Fourier transform of the function. Okay, so because we are doing PDE, so that we want to think about regularity, so we need to add in some derivatives, so that instead of using the 1 here, we are putting some weights here to S to kind of denote that it has S derivatives. Okay, so because kind of corresponding to this, the norm is defined like this, also with S in. And one thing that I want to point out is that you see that this is actually not a Hilbert, this is not an inner product space, right? Because this is L1, so that this is like a Banach space, and which makes all the familiar PDE analysis becomes tricky, because we don't even have, for example, Lax-Milgram type of things. Okay, and so nevertheless, we can develop a solution theory for these high-dimensional PDEs, somewhat parallel to what we are familiar with, except that we change these underlying functional spaces. So this is sort of the, we have developed the results for approximation generalization. We'll come to a bit later, but I think this is one of the key sort of insight from our work in a way that we can generalize the solution theories for high-dimensional PDEs to these function spaces that are suitable for neural network approximations. So essentially what it says is that, if the coefficient of the PDE and right-hand side are nice, are in the Baron spaces, PS, okay? So think of this as L2, all right? And then what you can say is that your true solution for the PDE has 2 additional regularity. So they're in H2, if you like, in the traditional language. But so the important difference is that if you use H2, these are really too large to be approximated by neural networks, while the B2 or the or the Baron spaces are good approximate. Are actually very suitable for neural network approximations. Okay, And also, let me point out that, I mean, we need to assume that right-hand side is sort of nice. I mean, so it's not crazy. I mean, it's not just arbitrary H1 function, which I think is sort of natural because you don't expect you can solve every possible high-dimensional PDEs with arbitrary data. And in fact, even to do the numerical quadrature, right, to do the empirical loss, you need to approximate these things by quadrature. And in high dimension, if you assume this is H1, then, I mean, as we know, I mean, as we have seen, even the best approximation error has quite worse dependence in terms of dimension. While here we can achieve very mild dimension dependence because we establish results in barrel space. Okay, so I don't think I have time to go over the proof, but one thing I want to point out that the proof is kind of, I mean, at least I would say that this is not the way that I would prove PD regularity traditionally, but I mean, we develop, we kind of, in the end of the day, we find that we one needs to use Phantom alternative and to do a fixed point approach, but I'm just flash this through. Okay. And also, let me just, I think I want to leave some time for the question discussions. And also, I would just want to briefly mention that, I mean, it's sort of natural that once you get the fact that the true solution lies in a very nice space to work with for the neural networks, then the approximation error comes, kind of naturally, which is, this is the approximation error that one can get. Using M neurons, you get 1 over M, so that this is like a very classical scaling you would expect. And then the generalization error also comes in kind of naturally, it's 1 over root 10. Some people complain that but this root M dependence, but I think it has to do with the regularity and so on. So, this rate may not be optimal, but this is at least what we can get. Okay, so, I will encourage experts in the audience, try to improve this, for example, to match the lower bound. Okay, and now, I want to show you briefly about these some numerical experiments that we have done, and as also already mentioned, that these numerical experiments sometimes are tricky to perform, but we do observe some kind of trade-off between generalization and approximation. So that the horizontal axis here is the width of the neural networks, and we are fixing the number of training samples that we use, and you do see that as the width goes to higher, this error starts to grow due to the generalization error. And of course, there is also optimization error that we we cannot analyze and also hidden also in these numerical results. But we are trying to do the optimization long enough and sophisticated enough so that we're not really suffer by a lot of these. But as far as we can tell, there is kind of balance between the approximation and generalization. Okay, so there's a slightly different side zoom in figure for the error curve. Okay, so maybe let me also mention that so the result previously is about solving elliptic PDEs, and we can also generalize the solution theories to more general PDE problems and more general function spaces. So one result I want to mention is a more recent result with Yudong. So this is, going back to the solving the high-dimensional quantum mechanics problem that we want to solve a high-dimensional eigenvalue problem. So that this is the eigenvalue problem. So instead of, the right-hand side here, instead of the right-hand side as we see in the PDEs, we now are thinking about the eigenvalue problem, and we want to find. So lambda 0 is the minimum, is the ground state. So the lambda 0 is the mean of the energy with respect to the L2 norm of the normalization where U is in H1. Okay, and so we can actually develop. Again, the proof. This result looks extremely similar to the traditional result that you would expect using Sobolev theory, but the proof is completely different. So, as I said, we do not have Lux-Milgrom, we do not have Krohn-Fischer. We're not using L2 spaces, and we have to use some kind of fixed point theorem in L1 type of things to get this result. But the proof is, the statement is sort of like, okay, so if V is in S regularity, and as one would expect from elliptic regularity, one can show that U has 2 additional regularities. So one can show that U is in BS plus 2. Okay, and as a result, because we can have this a priori solution theory for the PDEs, one can get following a similar route of getting approximation and generalization error. And one can get these kind of final approximation errors of the difference between UN and U star, which is the kind of denoted left-hand side here. And again, the right-hand side, this is sort of approximation error, and then this is the generalization error that we can get. Again, I mean, these upper bounds may not be optimal, and I think I would encourage experts to try to improve these. But I mean, these are really our initial steps trying to develop a theory and regularity theory for the PDEs, and I mean, for different type of high-dimensional PDE problems, and then try to use them to give a priori error estimates for neural network-based methods. Okay, I think with that, I want to conclude here. So I mean, I think there are several points that I mentioned. So that I mean, one we use is this spectral balance spaces for high-dimensional PDE problems. I mean, the reason is mainly because that these function spaces are kind of small, but they are also good enough to capture the solutions of PDEs, and they are small so that they are actually very well suited for approximations by neural networks. Okay, and then the difficult job in some sense is to develop the solution series for PDEs in these spaces, and we have done that here for the Schrödinger equations and the Schrödinger eigenvalue problems. You can, I mean, in the paper, we also did it for Poisson and so on, but I mean, these are slightly simpler. Okay, and then, I mean, with these tools, I mean, then one can develop a priori error analysis, generalization, approximation errors for the solution methods for PDEs. I mean, we are focusing here on deep roots, but once you have a solution theory, I mean, you can also do it for ping and so on and so forth. So that if you like, because I mean, so a lot of, I mean, if you look at many of these analysis works, people often assume that suppose the solution is nice, and then we can get this and that error. And what we provide is that we can prove rigorously that the solution of these high-dimensional PDEs is indeed nice in the sense of spaces that is good for neural networks. There are, I mean, of course, there are many new directions, challenging problems that people can kind of follow. And for example, I mean, here you can say that these balance spaces really designed for two-layer neural networks or one hidden layer neural networks. You want more general function spaces for more general activity. I mean, for more general architectures for neural networks, and certainly you can use something better than the naive monocolored quadrature. And I mean, and also like we can think about more complicated domains and boundary conditions, symmetries, and more challenging PDE problems, and even other numerical approaches. But I mean, I will leave these to future works. And with that, I want to thank you for your attention. And if you want to read, these are the two references that I mentioned. I mean, the first one is published in Code, which is actually next week, I think. And then the second one is currently in the archive. Okay, thank you.
Great. Well, thank you very much. We have a couple minutes for questions. So yeah, you can use your reaction button to raise your hand. Raghu, it looks like you have a question. Then Jin Chao, I'll put you next.
Yes, thank you. Thank you for the really nice talk. I have a quick question. On your error bound, I think in the penultimate slide, on slide 34, when you talk about the probability at least 1 minus 3 delta, this space, the probability space is induced by the Monte Carlo samples. Is that right?
Yes.
So the
yes, you're right.
So the second,
I did. Yeah, actually, I didn't mention these details here, but I mean, because the two results are slightly different in flavor. This is expectation, and then in the later result is a high probability result. But I mean, you can also change this expectation to high probability as well. So that so this is really a high probability result in a way.
so the second term really doesn't need anything, right? That's a deterministic sort of an error.
Yeah, because second is approximation, right? So that this is asking, I fix this approximation class. I mean, how much error that I make approximating the true solution by a candidate in that approximation class. So that is fully deterministic. The probabilistic comes in because we're using the empirical laws, right? So that the quadrature depending on the sample points that you choose. So there is, of course, it's not going to happen, but there is kind of catastrophic event that, for example, all these points that you choose in the Monte Carlo quadrature collapse into one point, then certainly you're not going to get these rates. So this high probability result is essentially preventing that.
All right. Jin Chao, did you have a question?
Yes, thanks, Jennifer, for the very nice talk. And I noticed that in your numerical example, you take both the potential function and the right-hand side to be periodical. And what if any one of them is not periodical? Is your analysis still go through? Because you have to extend your solution to be periodical in the whole domain.
No, our V doesn't have to be periodic. I mean, the
you
reason
can
that,
give,
first of all, we choose these things just because we can write down the solution easily so that we know what to compare
if
with.
we are periodic, your solution you have this Fourier expansion, the cosine. You do the even extension in each direction, so you do periodic extension that way, right? And
yeah, you just need to have these L1 coefficient. Sorry, the Fourier coefficient decays fast enough. So so in fact, for example, these things are not in cosine, right? These are sines. So
what I'm saying is that in this Fourier series, you have to extend the solution periodically in the entire space. That even extension is the derivative. You cannot take a second order derivative there, right? Because you can at most get a Lipschitz or maybe H3 half or something.
yeah, that's true. So, but I mean, so yeah, because I mean, we have instead of periodic, we have Neumann. So that that's why we are doing even extensions.
But even extension, you will not. You have limited regularity if you do extension. Then how can you expect? I talked to Yu Long about this question, but.
But this is, in a certain sense, this is hidden in the assumption of the V that is in barrel, right? Because I mean, if you really have kinks, and so the cosine coefficient does not decay fast enough, then it's not going to be L1, so that the V will not be in the barrel space. We do have later results that extending these things to entire space. So but I mean, there we sort of using a slightly different function spaces.
Okay, thanks.
Okay, Ben, you have a question?
Yeah, very nice talk. So my question is, do you think I have similar result under the strong form?
Yeah, I think so. So even though we didn't write it down, but I mean, in a certain sense, there are, I mean, results in the literature saying that if you're using a strong form, and if your where's the strong form? Sorry, it's way back. So if you're using a strong form, and if you assume enough regularity for U, then you can, if you assume enough regularity for U, then certainly one can get approximation generalization. And to some extent, our results of regularity results provide you the assumption to justify these unverified assumptions in the prior works. And I mean, we didn't combine the whole thing to get error estimate, but that's it's possible to do.
So you think you have similar bounds for the barren space?
So yeah, similar, but I mean, the detailed rates, I mean, one needs to verify, one needs to check.
And do you think if you use work like Sabro from Chicago TTI, you can also push your result to this algorithmic driven minimization instead of just minimization under some variational norm?
You mean that you kind of start to assume that, for example, I'm over parameterizing the parameters and so things like that?
Yeah, because in some,
yeah,
I think if you do this data-driven path, if you can show the path in the end belong to this barren space, then you kind of have the two coming together.
Yeah, there are, I mean, I think one can say two things here. So one is that certainly one can do a posteriori result based on this. So that, I mean, so which means that suppose you do the minimization, and then in the end of the day, you find the numerical solution satisfies certain regularity assumptions. Then because our true solution also has the similar regularity class, then we can combine the two to get a posteriori error estimate. That's possible. So even without considering about optimization, because I'm assuming things on the solution that I get, numerical solution I get. And now if you want to combine, I mean, with optimization, then I think it's also possible, but one has to go to regimes that the optimization becomes sort of linear.
I see. Yeah, that'll be very nice. Thank you.
Thank you.
Oji, you have a quick question?
Yeah, actually, I want to ask if the points are fixed or not in this Monte Carlo formulation for the integral.
So what we do so what we consider here is that we fix a number of n. So what we do numerically is that we first sample these bunch of points. I think, I don't know, in the figure I showed you, I think it's about 30K. And then we do mini batches, but we never refresh them. So if you start to refresh them, then it's a different, then the generalization becomes a totally different concept.
But in this case, how you fix the boundary conditions then? This empty matters now.
So in the variational form, actually, because we're using, because we're using natural boundary conditions, in the variational form that we actually do not need to put in the boundary condition in a way that if you just minimize this within H1, it automatically satisfies the boundary condition. If you have different boundary conditions, then you also need to use a penalty or building things into the function classes as we discussed before.
Okay. But how can you guarantee your solution also satisfies boundary condition?
Oh, there was no guarantee. It's just because this is what you get from numerically, right? So that you can just hope that it's like in the even if you use a natural boundary condition, if you find the true optimal, it will satisfy the boundary condition automatically. If you do not find the true optimal, you can only approximately satisfy it, right? But you can guarantee it in the H1 closed sense that it satisfies the boundary condition, but you cannot guarantee that it's exactly satisfied. It's kind of like numerical, other problems in numerical analysis, right? Unless it's like it's built in the ansatz, and you cannot really guarantee that it's satisfied.
So it seems when you fix the points for the Monte Carlo, it seems you introduce some artificial error there, because in the original Ritz method, I think the points are not fixed somehow. Maybe.
No, in the original Ritz method, okay, so it depends on what you mean by original method. So so if you have boundary, then if that's what you worry about, one actually need to also sample from the boundary. So because if you have a boundary term here, right, so that you would have things like, for example, there is a boundary condition which is saying that U is equal to G on the boundary. Then you need to kind of do a penalty term like this. Then you also need to sample points on the boundary. And so for that, we also need to do some regularity of, on the boundary and so on. So, for simplicity, we didn't do that in the paper, but it's possible to do. I think it's probably, this is the problem that you have in mind, probably.
Okay, so let's unmute just for a moment and thank Zhanfeng for a really great talk.
Thank you.
So I think everybody's welcome to stay on this this Zoom link. We'll use the same Zoom link for the afternoon session. I'm going to create some breakout rooms in case anybody wants to make a smaller group. You're welcome to go from one breakout room to the other, or stay on this one, or whatever you want. So yeah, feel free to stay and chat as you like.
建峰啊，建峰。 Can we discuss in private?
Sure.
How do we where is the breakout rooms?
Oh, I think if you go down to the bottom, there's breakout rooms. And then I think you can just choose one to go to.
Okay. Thank you. We'll go to 剑锋还是 which one? Where is it? Oh, how do I do the? Oh, no man. Yes,
there are 6 rooms, I think. So pick one, and I'll join you.
Or you can send each other a private message and go to a room.
Oh, I don't know how to do the private message.
Okay, you guys go to room 2.
Okay, so which room you are going to be in, 剑锋?
I don't think it matters. You can pick one, and I'll follow you.
Let's go to room 2. Go to room 2. You guys are in room 2.
Let's go to room 2.
Okay. So I go to room 2. How do
I go to room 2 actually? Or join? Okay.
Just go. Move to room 2. Is that what you do? How do I get in there? I'm just sitting. How do I join the room 2? How do I do that? How do I get in the room 2? Sorry.
Let me see. I might be able to put you there. Hang on.
I beg your pardon. I click on the room 2, but I'm not in there.
Okay, I'm going to put you in room 2. Bye.
I got it. Okay.
Sorry, Haizhao, I saw you had a question, but you can probably join the great breakout room and
Sure, I will ask later.
question there.
Sorry, can I ask some questions?
Sure, go ahead.
Yeah. You can't see me, right? So I just ask questions.
Yeah, I don't, your video is not on, but your audio is on.
Yeah. All right. Just want to know, when you are building the models, how, when you're evaluating the model, you only evaluate, because I'm looking at the imaging perspective when considering like image processing. When you are training a model out, when you are evaluating the performance, right now you are using a numerical methods perspective where you are analyzing the generalization error. What about the model itself? Whether the model is a good model or not? Do you look at that perspective?
By that, do you mean like the architecture of the neural network, or what do you mean?
No, it's like when you are using the number of points, like you have the original ground truth. Let's say you are using an artificial number of points, then you are fitting a polynomials, and then you are reconstructing this assuming that you don't know the original point, and then you are reconstructing, putting random noise onto the what do you call the shape, the test data, and then you are reconstructing it, making out the model. But when you are building the model, is there a way that you are considering whether the model, like you are using the parameterization, how many number of points you are considering replotting it?
Well,
you get what I mean? Let's say, for example, originally you may have an ground truth of, let's say, 20 points, and then you are fitting the polynomials in, and then you are putting noise onto it, and then that means you are already have diverged from the original ground truth points, and then from this ground truth, you are there's no information that telling you the original are 20 points. You only have the what you call the models that's building the number is from a line. So how do you know whether you are actually plotting 30 points or 10 points or 15, which is the best model from that number of points?
So is your problem you have a two-dimensional domain and you're trying to fit a one-dimensional function over that two-dimensional domain? Is that what you're doing?
Yeah, no, I'm using a very simple example. Let's say I'm using only 1D example is like, for example, the polynomials.
Okay.
So my original data comes from 20 points. And then these 20 points, I'm fitting in polynomials. And then this polynomial, I'm putting it noise, artificial noise onto it. That means, and then I replotting this from this artificial polynomial with noise. That means it will diverge. It will have an error. And then from this error, you are right now actually using neural network to train it, to approximate back the you want to know the ground truth, because I was saying that the original ground truth are actually 20 points where you know exactly the location. And right now, when you are actually after training the model, how did you know whether 30 points are the best, 10 points or 15 points? You are only right now considering the what you call the generalization error and the what you call the approximation error. Do you consider the model itself, whether that is a good model or not? I'm more looking at the training the data set, training of the data set.
I'm a little bit still unsure about what you mean by model in this case. It sounds like you're thinking about, well, I mean, I guess there are two ways you could think about models. So you're using a neural network with some fixed architecture to approximate polynomials, but you seem to be talking a lot about the points that you're choosing.
Correct. Yeah. For example, the first author or the second speaker just now, first speaker or second speaker were talking about using parameterization. So that parameterization, I assume that is according to the same number of original data you choose.
Well,
means,
typically not. I mean, that was what Professor DeVore was talking about in the first talk, that, you know, the principle of neural networks is that you have many more parameters. You have some large parameterization space, but then you use some kind of regularization to limit the functions that come out of your training process.
Correct. The question is, I'm looking at the parameterization, whether are they interpolating more or extrapolating beyond the boundaries, or are they only considering the original position?
I mean, typically you want to do some kind of interpolation, and, you know, I guess extrapolation comes up too, but extrapolation tends to get much more, I mean, like all this stuff, and that's a lot of the questions about stability and generalization are like, how reliable is it? And yeah, people think about that quite a lot. I mean, I don't know that.
I'm actually thinking of, for example, using the statistical shape model. I'm not sure. Are you familiarized with it? Active shape model, statistical shape model.
No, I don't really know. And if anyone else on here has more knowledge
That
about
is
that.
the way I'm doing it is when training the boundary of a shape, and then the boundary of the shape are parameterized, and then I reparameterize it. So when I reparameterize it, the number of points I can actually interpolate or extrapolate. That means I can put in more or less number of points, so that I can reconsider another perspective. How can I optimize it? Optimize the training itself, the model itself.
Yeah, I mean, that's, I think, related to the question of overfitting. What's the capacity of your model relative to the dimensionality and expressiveness of the data you're trying to fit? I think there's a fair amount of work done on that, but again, I don't really know that particular literature. But it's related to overfitting and capacity of the model. So I think if you did a search on those kinds of terms, you'd find a lot of stuff.
Okay.
So yeah, sorry, I don't know.
It's all right. Yeah.
Better answer for that.
Because I can see so far the speaker has not touched on this. It's assuming that it's not focusing on the building up the models, but it's more on the approximation of the
right, yeah,
of the method itself. Yes. Yeah, thank you. Yeah, maybe I'm asking a different questions from not from the perspective of this group of expert here.
Yeah, no, I'm sorry, I just don't know. Yeah.
Hi, Joe.
Hi.
Nice to meet you.
Your slide looks great. It works. Okay.
I think it works.
Yeah. We still have several minutes.
Yeah, I just want to make sure, all the technology works. Hi, Chen Chao.
Hi, Liao.
You're in a car.
I'm in a car. We just had lunch, and it's takes longer than I expect. Internet.
At least you're not giving a talk while you're in a car.
But I'm not driving though, so it's okay.
That's better.
So yeah, California. How is California these days?
I'm sorry, cannot hear you.
You're still in Berkeley right now, right?
Yeah, I'm still in Berkeley. You can see I'm with my sweater.
I mean the pandemic there is okay.
Yeah, Berkeley never got so bad. But
the kind of one of the more liberal place, right? Oh, that's actually better for pandemic. That's good. Yeah.
But students are coming back, so we'll see how it goes.
So the in-class teaching or maybe online hybrid mode or something.
So this weekend, students are moving into the dorms, right? So we'll see how whether we can keep the infection rate low. It's
we also worry about the
unpredictable. It's pretty unpredictable.
So you can mandate that everybody has to wear a mask, right? California, do you have that?
I think we have an indoor mask mandate.
Regardless whether you're vaccinated or not, I hope.
Yeah, I think so. And when I walk outside now, actually, when people pass by, I wear my mask and I take it off when nobody's around. So it's not.
Yeah, we just went to this restaurant for the lunch. It actually said everybody wears mask, but you don't have to if you're fully vaccinated. So we are still kind of more relaxed here.
Yeah, I think we even you're vaccinated, we need to wear masks. I think it's minimum inconvenience with mask, but teaching with mask is a different challenge because the voice cannot project very well and people don't hear as well. So
so yeah.
Has the most priority.
So hi, Zhao, how long do you want me to talk? I should have asked you earlier, like 45 minutes and then 5 minutes for the talk?
Yeah, that would be great.
Okay, I'll try. I might have too many slides, but I can go certain parts faster. Yeah.
We never have enough time for a talk.
It's not a good habit, but we all do that. So
we have a break. Maybe if you don't have enough time, we can discuss in the short break.
Okay. Yeah. So it's a lot of it's a very nice group of speakers from different subfields of deep learning research.
Yeah, quite diverse.
That's really great group of speakers. Yeah, we're happy to have you all.
Tell me when to turn.
So are there lots of fires near you in California, or is it farther away?
Well, this year we have been very lucky. We haven't had pollution much at all. And I think the wind is blowing inland.
Yeah.
We haven't had any bad days at all.
Oh,
I joke about maybe all around us, the places need to be burned, already burned. I think there's some truth to that. We had pretty horrible 3 or 4 years, right?
Yeah, right.
And this year, eventually, there's not much more to burn.
Right.
So it's a.
The second one of the largest in the history. Or?
Dixie is Sierra Nevada, but so it's further inland from us, and the wind is blowing the other way. So we could be affected, but the wind has been going inland, and other people have been affected, not people on the coast. So it's a very big fire, but we haven't been affected because all the smoke has been going to other places.
The Midwest.
Yes, exactly. I joke about equal opportunity of pollution. So
yeah, it's been pretty clear here for the most part.
Yeah, but fingers crossed. Last year, August, we already start having fires. We still have this Dixie fire, which is very big. But Canada has a lot of fires. And so far, the Bay Area will have a lot of fogs. So that's a good thing. Just very moisture coming in from the fog.
Oh, yeah, right.
But I'm not holding my breath. We won't have more fires, which will be affected.
No.
So far, so good. Fingers crossed.
Nice to hear that. And probably it's time to get started for the afternoon section. So welcome back, everyone. Our first speaker in the afternoon is Professor Bing Yu, who is a Chancellor's Professor of Statistics, WE and CS at UC Berkeley. Today, she's going to talk about interpreting deep neural networks. Let's welcome.
Thank you. Thank you, Haizhao and other organizers for having me. It's really a pleasure to join this very distinguished group of speakers. So I think it's I'm changing gear for the conference. I won't have any theorems, and I hope still as interesting to this crowd. Oops, if I can move it. So the goal of our work is really try to tackle this pretty difficult problem of interpreting machine learning, or particularly interpret deep learning. And one of the strong motivations, at least in Europe, is actually this EU General Data Protection Regulation gives the right for the users, say a patient, to explanation. So more and more AI is coming to precision medicine, and people like us, everyone will be affected by some sort of algorithmic, at least clinical aid. So this regulation gives right for the patient to ask why you making this recommendation. If you're relying on algorithm, how did the algorithm give the recommendation? And this is just a few examples where interpretation is needed, right? I met actually IPAM a couple of years ago. Startup, CEO want to approve some deep learning based radiology like diagnosis, and FDA wants her to give some interpretation for the algorithm. And we work with Drosophila biologists, and we want to understand what genes drive a particular enhancer, which is really start the gene interaction. And we're working with cosmologists, you'll see later, and in general, say, sentiment analysis from Yelp, right? Why this sentence automatically is a positive sentiment sentence instead of a negative one. And a lot of my group's work is actually I'll call scientific machine learning. So the term has been used. Let me try to define what I mean. It's really try to use machine learning for scientific research, for discovery, theory, and knowledge, and try to build in scientific principles, but also try to use data to develop new science. So it's really interpretation of both. And I think scientific machine learning should hold a higher standard than just any machine learning. The paper 2019, a group of us from my students come together, really try to struggle with what do we mean by interpret machine learning, because we have genomics, neuroscience, and sentiment analysis, and we work on different interpretations and can we come together and define it. So what we came up with is really try to emphasize the audience and what the problem is interpretations relative to, and discover some reality checked interpretation instead of, you can interpret things which have no reality. In one graph, we call PDR, predictive accuracy, which is taken from machine learning or statistics. It's really say there's reality check there, but also at the descriptive level, we also want some reality check. When you have interpretation for certain genes driving a particular biological phenomenon, there's domain knowledge to see this interpretation actually makes sense. But you want the description to be capturing what the algorithm is doing than just imagined, and to a particular audience. For an algorithm to be explained to me is very different to a layman, another patient, right? So its audience has to come in for interpretation. And as already said, this PDR. And usually in machine learning, people tend to think roughly like there's a trade-off between predictive accuracy and descriptive accuracy. It's like, well, decision trees is simple, logistic regression may be okay, but actually for this, you need only, you cannot interpret decision tree with depth 5. 3 maybe, logistic regression with 100 terms is just equally non-understandable because you don't remember all 100 terms. But this is roughly people agree that deep learning is probably the highest in terms of accuracy, but also the hardest to describe or interpret. But you will see my 2 examples through distillation deep learning, we actually don't have this trade-off. We actually increase both interpretation accuracy and predictive accuracy. So this is just roughly can happen, but it's not always a trade-off. Something can do both. Interpretation can help. The generic model-based interpretability people like to seek are sparsity. And the important thing is simulatability. It's like decision tree has the easiest, right? You can kind of follow, say, oh, that's why this decision made. And deep learning is not penetrable if you want to simulate in a human mind very quickly. And modularity is like decomposability. Things can be taken into simpler parts. Oh, domain knowledge, right? Credit scores. We feel like we all understand. There's probably some data there. We know like 700 is good, but it's already become our knowledge, even though in the beginning, we don't exactly know how they take all our characteristics and made it into a credit score. But more and more things will be like that. We'll start taking this new score and start feeling that we have a sense of it. Post hoc interpretability is really already fitted the model, and you want to see which features are important. There are many ways to do that. And I want to emphasize what we try to do is really you not just give individual features, you can look at group of features for interaction. That's one thing my group has been really pushing. And also you look at individual level, not just the whole data set, this gene is important for population people, but for this person, what are the important factors? But one thing is, how do we know we trust some interpret machine learning? Where does trust come from? And my group again developed this PCS framework for truthful data science process. It's really you try to vet every step of the way before you come up with the model, before you interpret. Without the very much vetted, controlled, quality controlled process, I don't think I have a lot of trust in the model you fit. And relevant science, it's also very important. We can get a domain scientist to really provide confirming scientific knowledge to the interpretation and build on the accumulation of factual, reliable empirical evidence existing in the field. So now I'm going to expand these more philosophical points into 2 concrete projects. The first is really a more generic, I'll say, important score development for individual features and also interactions of features for a fitted deep learning model. So this is taking a model already fit, you have good prediction accuracy. Now you want to take a peek inside. And then how do we visualize this interaction feature so that it's easier for human mind? The previous work on post hoc interpretation have kind of more roughly fall into 2 categories. One is like gradient based, Lime and IG. The other one is more occlusion or contribution, but you take something out and see what happens. So the salient map and SHAP belong to this category. So what we developed belong to the second category. So this is the first actually case we try to look at for our own important score development for deep learning. So take a look from, say, LSTM, sentiment analysis, right? The movie was good, right? And we know it's positive, and we want to give some explanation. But the not good is not in not in good. You need to have a score for not good together. So we really want to give a score to not good, not just not and good. What we develop is really Jamie Murdoch, my former student, now in industry startup, developed this when he was an intern at Google, his mentor, Leo, and later myself. So the idea is really decompose the output from deep learning into two additive bits, one related to the thing you care about and the rest. And you do this additive decomposition for every layer and have a smart way of collecting and also distribute different bias for different terms, and you give the scores. So this is just what we did, so you have to validate it, right? We can decompose things in many different ways. Why this makes sense? Of course, when we think about it, we're putting a lot of understand deep learning into the decomposition, but eventually you have to evaluate it. And you basically take the original output into relevant bit and the irrelevant bit and run this through the layers and layers process, and we have a way to collect and propagate. It's a forward propagation of the scores, and then we end up with the final score. And you can do the later with generalize for convolution networks and general deep learning. In the beginning, it was only LSTM. Similarly, so example here. And after we have the scores, we feel like it's still not organized enough. The second paper, Chandan Singh, my current CS student, joined and really pushing this forward for the next stage. So you have this prediction. So now we're going to give scores. Our CD method give you scores for not, very, and good, right? This is the color means how positive, negative they are. The blue is positive and the orange is more negative. And then we combine two words to find the biggest jump of the score, because we also have score for very good. So it's kind of hierarchical clustering. And then we see, oh, the flip happened at the not very good. Everything's very positive until the last bit. So you can identify what's the important feature to turn the label negative. This is a more complex example where you can see underline the color shading is about each individual has a score, and then any phrases also have a score under our CD methodology. And you do hierarchical clustering, and you also can identify when the thing became negative and positive. So you really have now understanding how the algorithm is doing the labeling of sentiment analysis, positive and negative. This is a generalization to images, right? So you want to predict puck, and then we shaded. That's where we didn't do all the steps because many pixels, we jumped, and you can see the algorithm really start telling you for this image, the skates are very important, and also puck. And later you can remove the puck and see that actually skates are just important because they tend to appear together. It's association analysis. This is not the causal analysis. We also carried out human experiments to compare with other methods, right? The one is remember we had two categories. One is gradient-based, the integrated IG, and the other occlusion existed before our kind of occlusion method. And we have the CD scores without the organization. And we asked humans, we have about 10 or 12 graduate students, and did the experiment that we're giving them interpretations from the different methods. And we hope they can tell from the interpretation which one the prediction has more accuracy for individual examples. And for the SST, it's a Stanford sentiment trunk. That's a sentiment analysis data base. Both our methods really stand up, but it's kind of small data set. MNIST, everybody does pretty well. It's a relatively simple data set, but the power of ACD, the visual hierarchical presentation of the CD score, really showed up in the ImageNet, right? You can see that it really there's a very significant jump of people just find that very useful for them to predict which prediction is more accurate. And then we had another experiment showing that based on the examples, based on the interpretations, can you trust the model? And you can see that ACD also give good trust scores based on people reactions of the subjects. And the question I kept asking my students, and now we have this interpretation, you have to go back and really improve things. So this paper led by a visiting student, Laura from Denmark, was ICML, really did that. I'll just say very quickly, is that we basically use the interpretation in the fitting and saying that suppose you want to decrease the reliance of your prediction, say on gender, you want to be more gender unbiased, then you just force it through the explanation penalty. And you say that I want the score to be close to 0. And this way you're pushing the fit to be something not relying on gender very much. We can then improve really the decrease the reliance on unfavorable traits. So here's really scientific. Before I was really preparing ourselves, we really started from more generic problems, and now we want to connect to scientific reality. So we start out to work with postdoc from. This is really the result of NSF tripods grant we got, and Francois with the cosmology also postdoc, and Wusuk, the one on the top left, was also postdoc. So I said, well, let's work together and use this interpretation method already, but and Chandon joined, and 2 colleagues of Francois also joined from Berkeley Cosmology Center. So this is really try to put our interpretation to test. Does it really help science? So Francois and colleagues simulated the universe. A very important universe, which is the mass density of the origin of the universe, called omega m. So they use PDEs, and I think a lot of people probably know about the PDE generated than I do, today. And we observe this is all simulated, but eventually we use this as like an incubator. So later we can understand the universe by knowing what's going on and see whether the method is reliable. So we have the observed simulated map of a mass in the universe. And when you have this simulation result, and Francois already used deep learning and get the best retrieval of the omega m. And they simulate something called the 10 cosmologies. That means they actually have different 10 sets of parameters, not just omega m, there are also other parameters, a couple other parameters they use, and they simulate different sets of them and forward simulation. And for each of them, they also have many, many images. And deep learning really turned out to be the best method. I'll mention some of the early methods. Oops. How do we, one thing they've asked us is like, can we understand how this deep learning does the estimation? And maybe we can reduce, it's very costly to simulate this big universe, and can we reduce the computation through the understanding? Because if there's a certain part of the simulation really, it doesn't really help you to estimate omega m, maybe we can do a coarser simulation. So first thing to do when you really have like off-the-shelf method, every time you solve a real problem, the first thing is actually it's not exactly fit, but you can revise your tool to solve the problem. So one thing they told us that the interpretability really lies in the Fourier space. Is that when you go to the simulation also to do with the Fourier space, and they want to interpret the contributions of these different frequencies, like 0.1, 0.2, 0.3, and they want to have a score for this frequency bands. So we generalize our method to go to the transform space because it's an invertible transform, and then we can come up with scores for this whole frequency band. And this is the score for these different bands. And you can see that the highest score is at around 0.3. So that's a frequency band. So this is indication. And then beyond 0.8 or something, the deep learning, which does very good prediction, doesn't really rely on. So this is a cue that for them to say, maybe we don't have to simulate that those frequency bands with such a precision. Of course, this is only suggestive. So they could do is they could really remove that and see whether the result change, right? This is still association analysis, but with the simulation setup, they can now reduce computation in the high frequency band and see whether the result of estimate omega m would degrade. And then since we're Fourier, I worked on a wavelets image processing like 20, 30 years ago. And I said, well, if you do Fourier, we should do wavelets. It's a more flexible decomposition with both frequency. It's not, it's a local Fourier transform. So let's go wavelets. And actually independently, Francois was also making the same suggestion. So it's great that we really aligned with what we want to do next step. So, so here, before I go to wavelets, I want to talk about how does this compare with, this is a very simplistic simulation model to compare with other interpretation methods. And we generated model with a ground truth frequencies. And we see whether our CD score really give high weights to the identity, to the true frequencies. And you can see that we do quite a bit better than the comparative methods like deep lift, SHAP, and also IG. Right? This is a very clean signal, but we almost get 100%, and they have quite a few percent off. This is just a sanity check to see that we actually, in a situation we know what's going on, then we do identify the important frequencies. So as I mentioned earlier, right, relevancy is the key, right? You want insight, which we did provide some to the cosmology problem, and had to be validated and correspond well with what people know in cosmology. And that's all, it's also the reality check. There's another very interesting line of work that started from deep learning, Hinton and collaborators. It's people have been really complaining that deep learning is too big, right? Some of the big, have millions of parameters. It's impenetrable black box. And there's very interesting work started by Hinton. Well, actually started by another person, Rich Karuna. I should have mentioned that too, from Microsoft. And this Hinton paper really made it much more well-known, called model distillation. So the idea is that we have this pretty much black box model, pretty complex. But because the largeness of the deep learning, we know that has a lot of advantage in terms of computation flexibility and efficiency and approximation properties, that after we fit this complex model, can we distill into a simpler neural network model? That's the first work what we're doing. It's really, we start with this big complex model, but we find a smaller one. Other people have pushed the boundary to any interval model, not just a small neural network, but say decision trees or editing models, right? So this doesn't have to be, you can start deep learning network, you don't have to stay with neural networks, you can go somewhere else. And as I mentioned, decision trees is often doctors make decisions. We have another work we did with ER doctors at UCSF. It's really vetting, use the PCS framework, their decision rules for sending a kid in the ER department to CT scan or not. So this is very desirable decision trees, especially with human interactions. So we set out to do is that we want to do it through wavelets, because we think in physical sciences and biological sciences, it's really a very nice modern version for your analysis with a lot of physical connections. And we want to distill a deep learning model through wavelets. And we want to improve interpretability and compression and efficiency, right? If you have very simple models, you can do easier to store and easier to do a new computation of prediction. So this is very much driven by cosmology, right? Fourier transform, and wavelet just seems natural next step. I think for this audience, probably I don't have to give for usually machine learning and the statistics people, well, statistics people probably know some of it too, but for machine learning people, wavelets is probably still pretty foreign, except for a few people like Stefan Malad and Joan Bruno. So this is really a different tiling of the frequency and the time domain, right? Time series is tiling it for each time, and frequency Fourier transform is tiling the second picture, and wavelet transform is tiling both together. And Malad and Mayer, there are a lot of good standard reference books for orthogonal wavelets transform. So that's our idea. We want to learn wavelets from data. And what we do is that we first do, suppose you're giving a wavelet transform phi. And then you do forward transform, and then you also have a corresponding orthogonal with inverse. And then you put the whole thing, and then you have f hat, x hat. And that's the one fed into the pre-trained neural network. You can see that it's really the same thing because the wavelet transform inverse cancel, but for optimization for our method, we need to do the decomposition. So the F is all the things in the orange box. Then we design this loss function. Now you can see why my question about strong form came from in earlier talk. The first is really say you want the reconstruction loss to be controlled. And then the second loss are called wavelet loss. You want to make sure what you learn, its coefficients really satisfy all this defining equation for wavelets, that they actually form of wavelets. And the last part is by interpretation loss. You want in the F, the trim as a transform, things are very interpretable in the wavelet domain. So let me just expand and give you the details of the three terms. The first term is pretty obvious. I don't have to explain. It's the wavelet loss function. So this is just lifted out from Malar's. We're finding these defining properties of wavelets, right? This is kind of the filter bank presentation. And we take all these equations, orthogonal wavelet transform, giving a mother wavelet, phi, needs to be satisfied. And we just turn them into penalties, as in the strong form of earlier talk when you solve differential equation. And these two equations are not exactly defining because there's 7.31 we kind of didn't worry about because it's kind of hard to turn into like a penalty. But more or less, we are trying to make these defining properties of orthogonal wavelet transform into penalties so we can force through the wavelet loss function. And we also added something about the G function in the wavelet decomposition. So again, you have two equations and you turn it into one penalty because G hat 0 has to be 0. So you want that the sum to be small. So that's why you can reckon, but we did add one more term, which is the sparsity wavelet coefficients. And then all the other big terms are really copying from the defining properties of wavelets and make them into penalties, very much like in the strong form solution approach to partial differential equation. And the third term is the interpretation loss, which is building on, remember our work from CD, but we didn't use CD. Actually, we use a trim, which is, we use basically the derivative, normal derivative as the loss function, as the penalty. It's just easier to calculate. And this is just saying that you put it in the big F as a function, and you take the derivative f, and with all of that, you can take advantage of the PyTorch, all that have very good differentiation functions, and then you can calculate it very easily. So put it together, we have three terms: reconstruction term, wavelet term, to enforce wavelet, and the interpretation term. So this is just like a synthetic simulation to show that we actually recover the ground truth wavelet. So we have a synthetic input, it's kind of noise version of wavelets, and we fit fully connected neural network, and we distill the wavelet, as I described, by minimizing that three-term loss function, and we compare with ground truth. So initialization is one of the challenging problem for deep learning, at least before the recent wave, right? Jan LeCun's group always did, even in the 90s, while Spell Labs, and they were still working on, a neural network. Not many people working on it, and the folklore was that, Jan's group can really tune to make neural network, but initialization otherwise can be difficult. Now we have more standard way to do it for deep learning. But for this, we also have an initialization problem. So we start with a wavelet, COIF2 and SIM5, you all end up with something similar. And we also start with a wavelet and then did a random noise to it and still converge the right thing. So if you start with a complete random uniform noise, you do have to put, so what we did now, I don't have the result, but we're running it now, is that you start completely random, you need to force it to be a little bit like wavelets or smooth. So what we do is that we actually just forget about interpretation term, just enforce the wavelet term to get something pretty close in something remotely like wavelet. And then we add the interpretation term. Interpretation term doesn't make sense before you get something close to wavelet. So that will make it work. But you cannot run just we can hit instability if we just don't first force it a bit like a wavelet neighborhood. And so this is just a ground truth that from different initializations, you get something. You can see SIM5 gets something now that's close to the truth, but still pretty much on the line. So now back to the cosmology problem. It turned out after I made a suggestion about wavelets, and Francois also made the same suggestion, and he actually pointed out that people already used wavelets to do a cosmology. So what we did here is we use ResNet to do the estimation, and we use our method AWD to distill the wavelet. That's what you see, the 4 blocks. You have low frequency, low high, high low, and then high high. And for each of the peak, you basically use the wavelet moving around and get the peak counting, and then you see the 4 peaks. The first one is actually has pretty low, you don't see a peak, so only see 3 peaks for the high frequency, because the signals in this cosmology image is really the peaks, not the low frequency bits, because that's where the mass density matters. So what we did that instead of using a fixed wavelet, so this already in cosmology, people already use fixed wavelet to do the last part. So what we did is AWD, the first number on the left, is use ResNet and distill the wavelets, as I showed you, and then use the old peak method people use for fixed wavelets. And you can see that this is a prediction error, and we have the lowest prediction error, and we reduce the loss from ResNet by 15%. So that's significant. And we basically obtain both interpretability and improve the predictability. Remember my trade-off in the beginning, I said it's not always the case. You have to trade off interpretability with prediction. I think this just says that, to me, the deep learning still doesn't have enough regularity. And that's why we can still gain by having more regularity through forcing and wavelet transform. And we actually got both improved prediction performance and got interpretation out. And you see that if we don't put the last number, if we don't use the interpretation loss, just false wavelets, we have basically only adaptive wavelet, but not distilled, not taking care of the interpretation from deep learning network, then you still do better than DB5 wavelet. That's the third one from the right. Right, we get 1.3 instead of 1.5. So that's fixed wavelets and using the peak counting method. And if you use other methods, there's some Laplacian, you have different varied performance. But ResNet beat everything. But if we take advantage of ResNet and add wavelets, we beat ResNet by 15%. So this was a Nature astronomy paper, I think, using the peak count. So how do you do the estimation in the peak counting methods? Actually, you get the peaks and you form a multivariate Gaussian. And then because you have the simulation cosmology, the parameters, and you see which one is closer for new data. And then you just say, well, whatever the omega seem to be the closest in this kind of Mahabalus distance. And then that's the estimation method. So that's how you go from the peak counting kind of feature extraction back to omega m. And that's just people already use it for fixed wavelets. So we're just following the same method. So this gives you, we have two parameters on the wavelet loss and also on the interpretation loss, and they vary. You get different, slightly different wavelets, but this is symmetric, right? You can see that. We started with asymmetric and we end up with a symmetric. So there's quite a bit change. The first one you can see is asymmetric. And we both cut down the reconstruction loss and wavelet loss at the bottom. You see so there's a real trade-off with interpretation and wavelets. Okay, so now we have developed this method. My group also work with bioimaging people to understand basic site biology, and we'll also use deep learning there for some more like data extracted from images, but it's like one-dimensional time series data. And I said, let's try that and see, just going to see whether this methodology is really useful cross disciplines, not just from cosmology. Because statistics and machine learning is really, we try to solve many different problems, not just particular domain area. So this is a project I work with the ABC Advanced Bioimaging Center, Gokul, who is the executive scientific director. We have been working for this problem before the interpretation problem for 2 or 3 years. So this is a really interesting problem, fundamental problem in cell biology. So in cell biology, it's very, very important to track, they call molecular bipartners, that you want to know how these molecules interact. They often trigger one to the other. So this on the left hand, this you call this one, I call the orange one, and it's the clustering. And on the right is called oxalin, which is more expensive to track. So we want to use the easily observed clustering to predict the oxalin, which is really tell you the completion of very important process called CME, which I'll tell you next time. Next slide. So this is the first image processing. Identify, because there's a lot of good models. So blur imaging is microscopy. I think it's light sheet microscopy, and then you try to turn it into more like time series data. Yeah, so we want to really, predict from the orange to the green. And oops, what happened to? Sorry. Oh, I skipped. Somehow this got skipped. So I should say what's this about. I should have done the other slide later. So this is really about this something very important in biology called the clustering mediated endocytosis. This is a very basic cell functions, how the cell gets cargoes or food or whatever from outside the cell membranes to inside the cell, right? This is a very nice one I got from this paper, Nature Review 2018, you can see in the cargo, it's basically the cells outside needs to get in, and you get a coating, and then initialization, and then you kind of fold it in and enclose it, and then the yellow little sticks gets inside. So the coronavirus also had to go through this process, and there's papers studying this CME for COVID virus, how they get into our cells. And we want to know whether this something called CME happened. And clustering is very, very important. That's the orange one I already showed you. And then the green one actually is oxalin, will tell you that in cargo gets inside the cell completed. So not everything initiated by clustering will get completed. So we want to use clustering to predict whether that cargo actually got transported inside the cell. So there was something missing. Okay, so that's the background, very important basic cellular process. And through those video images, we already followed these bright spots and turned it into a time series. We tried to go back to the video and use deep learning, because deep learning for video hasn't really worked very well except for framing, so it didn't really help. So we just start using deep learning at the second stage after pre-processing using Gaussian deconvolution to as a time series model. And then we distilled the LSTM works the best in terms of prediction of labels. And we distilled, now this is a symmetric wavelet. This time it's R-score, so one is bigger. Before it's a prediction error, this is really try to see correlation with the proportional variance explained. So we want it to be bigger. You can see that DB5 get 0.19. LSTM really did a lot better, got 0.23. If you don't use the interpretation loss, it's still pretty good. It's not as good as LSTM, but know that if we combine the two together, the wavelet constraint and also interpretation based on LSTM, you really have a 0.03 jump. So that's quite substantial. So it's really both the power of wavelets and also the learning power of LSTM. Okay, so I think I probably have quite a lot of time for questions. So the first part, we try to lay out the framework for defining interval machine learning. Because every talk about interpretation, but it's like everything means different things. And so we define through the predictive accuracy, descriptive accuracy, and relevance. So basically answer the question for what and for whom, and with reality check through a predictive accuracy. And for what means descriptive, what you try to describe. And for whom means relevance. And then I introduced the CD, contextual decomposition, or the combined version ACD for a trained deep learning for features and group of features. And then the most scientific bit is really the AWD, right? We have this 3-term optimization, reconstruction, wavelet loss, and also the interpretation loss for wavelet decomposition. And we showed successes, both improve the prediction and interpretation at the same time, because I think the wavelet constraint added the extra regularization that's needed. And deep learning didn't give enough regularization, at least not in the right way, for cosmology and biology problems. And we are finishing a review paper, have actually all of the 3 projects in one. There's a book edited on explainer AI, so that should be coming soon. I'll put it on my website probably next week. So you can watch out for kind of a written version of the talk. So looking forward, we're very excited about the success of the wavelets, and we hope to get more scientific insights from this distilled wavelets for the cellular biology problem, and also for cosmology. And we're also working on expanding the 1-layer wavelet transform to multi-layers, right? Scattering transforms already multi-layer. And we think we can make some contribution there. So my idea is that we'll replace all the layers of 100, whatever, 80 layers to something much fewer, and also much fewer coefficients for each layer through the wavelet. Because you see, with mother wavelet, right, you define the mother wavelet, all the dilation and scaling just automatically done for you. So you only need to define the mother wavelet. The goal, I hope, is that for each layer, we can also reduce the number of layers, right? For ResNet, remember for cosmology, how many layers? Then we end up with one layer of wavelets. And with the peak method, we do better. And we also think for other problem, probably won't be one layer is enough. So can we build out multiple layers, but hope still reduce the layers, and for each layer only using one learned mother wavelet to summarize what's going on for each layer. And I was having some exchange with Haizhao that the most exciting for me also is really try to derive new PDEs, right? I know I'm speaking in front of all the PDE experts, but I hope to get help from you guys. It's really deriving new PDEs through wavelets. Right now we can learn data-driven wavelets already. Can we go back? And it's like, I know the solution of PDE now. Can I now, so for example, you guys can use deep learning and use our method to work with us to get wavelets. Would that tell us something about how do we revive some of the standard PDEs? And on that, I want to have a shout out for our new book to be on data science for people, especially not trained in statistics machine learning, to connect reality with symbols, and should be available. We're going to have a free online indirect copy by fall. And it's really intended to lower the barrier for people who want to get started on data science through this PCS framework. And we spent a lot of time on the whole data science lifecycle, and also try to teach critical thinking. How do you turn a domain problem and connect with symbols? What does X mean for your problem? If you don't have that connection, the mathematics won't have the relevance and the impact in the real world. Thank you.
Thank you very much for a very nice talk. If you have any question, please feel free to raise your hand or unmute yourself.
Can I ask a question?
Yes.
Yeah, I want to know more about this your model, distillation. Does it only been used so far for images, or has it been used for 1D problems?
Yes. So the molecular biology project, you're right that the data came from video, but we already distilled into a time series, and the LSTM is used on time series data. And then we distill the wavelet using the 1D data.
Yeah, but I want to know more about, because I've never used this before. How do you actually select, because you're using wavelet to select from a complex model to a simpler model? What about a problem that is no longer on images, no longer a 2D problem? That means when you cannot use wavelet to solve the problems, for example, shape boundaries problems.
I think you have to have a natural, for the whatever problem, you need to have a natural presentation of some generalization wavelets already. That has to be there. Right. So for time series, we already did it. For images, we already did it. For your problem, if you can have some wavelet presentation without deep learning, at least get some goal at that, then I think you can apply our approach.
Sure. Maybe I should spend more time.
Yeah, you should probably follow up. Send me an email and we can.
Yeah, I will. Maybe I should read more about this model distillation first. Yeah, thank you.
Yeah, it's pretty new. We submitted to NERSC. We're in the rebuttal stage now, but sure. We're quite excited about this, especially the improved performance.
Sure, I will. I can find your email on your website, right? Yeah.
Yes.
Yeah. I got it from this bit, from this here. All right, sure.
Thank you.
Thank you.
Any more question? Can I ask? Andrea, please go ahead. No? Okay.
No, I was just saying hello.
Hi, Andrea. I know you're coming.
Okay. Can I ask a very simple question? So from the the framework, we can see that you add some penalization to penalize the interpretation. In general, how can we design the loss function for interpretation? Is it problem dependent?
Well, you have many choices. We took the derivative, right? So you could try other ones, right? We took this as interpretation. It's for simplicity, and it worked pretty well. So, I mean, we build on the gradient has been used for interpreting deep learning by many people. So we just took one version of it. We didn't even use our own ACD, which is more complex, because we want the optimization to go more smoothly using what's available. And as I showed you, right, we did for this, if you remove the last number, if you use AWD without the interpretation loss, you don't do as well as if you do use the gradient version of interpretation loss. But that, just like penalties, I think you have to try and error for the domain problem. I think it's good we have many different choices, but it shouldn't be one size fit all, right? So just try different things, but computation feasibility plays a role on which one do you use. And for this one, because the gradient is easy to carry in PyTorch, we just do the gradient. We didn't even use our own more complex importance score. And I think for physical sciences and even biological sciences, imaging, I think there's a lot of potential for these adaptive wavelets and take advantage of the power of deep learning for predictive accuracy. Basic computation apparatus, you can search much bigger space in an efficient way.
Thanks.
And then you kind of summarize in wavelets, which we all have, warm and fuzzy feeling about, especially for this community. It's also very useful to have this physical, like for local Fourier transform interpretation.
Thanks. So maybe the simplest case you use is to minimize the norm of the change so that the change in the function will not be too large as an interpretation.
Yeah, the interpretation usually like you want things to have big change. That's important.
Thanks.
Right,
yeah.
And then that's kind of the idea. Something is problem, but you change, you see a big effect, and you can use difference instead of gradient. So that's all different versions of it.
Yes.
So going back to the earlier talk of Professor Liu, I can see that he already had a deep learning solver, and then he can also do this and get a wavelet presentation of his deep learning solution.
Thanks. And thanks a lot again for the nice talk. Maybe it's time for the next speaker. Could you stop sharing? And yes. Professor Andrew Montanari, could you try to share your screen? Okay, so our next speaker is Professor Andrew Montanari from the Department of CS and Statistics from Stanford University. Today, he's going to talk about minimum complexity interpolation in random feature models. Let's welcome.
Okay, thanks. Thanks for the kind invitation. Yeah, so this is joint work with Michael Celentano, who just graduated from my group, and Theodor Misiakiewicz, who is still a student in the statistics department in Stanford. Yeah, so this is the outline of the talk, and is all based on a paper of a few months ago. And so I'll give an introduction, then I'll describe the connection between the infinitely wide network and kernels, the curse of dimensionality, and then the main result of this paper, of this work, is proving that a certain method that we call minimum complexity interpolation is algorithmically tractable, polynomial term tractable. Okay. So this is the motivation that I come from is 2 layers neural network, or one hidden layer neural network. Here we have input vectors X, that is vectors in RD, And then we pass them, through the weights, first layer weights WIs, and then there is an activation function sigma, and then we take a linear combination of capital N of this function. So the parameter to remember here in particular is capital N, that is the width of the network. Okay, and I'm interested in, and I've been interested for a while in understanding how these networks behave in the limit of very large width. So how do you take the limit of very large width? Well, a natural idea is that, okay, the sum gets replaced by an integral. And so to do an integral, I need a measure. So let's say that I have a probability measure mu on RD. Here, the weights W's are in RD. So I have a measure mu on RD, or a subset of RD. And then I take an integral of this measure against the activation function, and I have a weight that can be positive or negative A that replaces the second layer weights AI. Okay, and so the parameters here in this infinite width network, of course, are this weight A of W. Okay, so in fact, in this talk, I'll be a little bit more general. All of the analysis can be generalized, and this can be useful for some specific examples. Instead of taking a combination of activation function of the standard type, that is sigma of Wi times X, scalar product, I take a more general activation function that is a function of the input vector X and of the weight vector Wi. So phi here is a generic function, and in fact, X can belong to a general covariate space X, and the weights can belong to a general probability space omega. And the corresponding infinite width network is this one, in which you instead integrate over mu. Okay, so I hope this makes sense. If not, please interrupt me, because a feature of these online talks is that it's never clear whether the audience is following. Of course, this infinite kind of model, infinite width model, they are not new, and they were studied since the 90s in approximation theory. And okay, here is just a slide to connect to that kind of literature. You can define a function class that is the class of this infinite width network, where A belongs to a classical space. Let's say A is in L2. Okay, so A is square integrable with respect to the measure mu. And the corresponding set of finite width network is this one. And so the results from starting from Sibenko in '89 and then so on, as I reviewed in Pincus, kind of take this form. If phi and mu are reasonable, so basically reasonable means there is some notion of non-degeneracy, then the space F2 is dense in L2. Okay, here I'm taking the feature space, the input features, to be R to the D, and there is some probability measure that is the distribution of the data. So typically you prove that this infinite width network is a dense subset of L2. And further, if you have any function in F2, you can approximate it arbitrarily well by finite width network. And one way to approximate it by finite width network is taking IID weights with measure mu. In fact, if you take these IID weights, this is in fact a way to prove approximation results. This is what's called the Morey argument. If you take this special case, you obtain this kind of bound. You obtain that L2 error of F star by an N neuron network is upper bounded by constant over N times the L2 norm of A. All right, so this is just a quick reminder to describe the connection between these infinite width networks and approximation theory. Now, suppose that we don't, so the point of view that I want to take in this talk is that I start with this infinite width network, and I look at it as a non-parametric model. I want to fit it to data. So there are two natural questions. How do we fit it to data? And the second is the theory question of what are its generalization properties. And okay, if there is one bit of information that I can convey here is that the answer to this question depends on the measure way we constrain the function A, in fact, in particular, how you measure its complexity. Okay, and to clarify this, I want to spend a little bit of time discussing a very well understood example, a very classical example, and consisting in doing what I mentioned before, that is, I measure the complexity of the function A by its L2 norm. Okay, so if I do this, you can push this norm and express it in function space. Okay, here there is a square missing, and or let's do this, and write this norm in function space as a norm of the function f. So for any function f, I define its k norm as the in for all the L2 norms over all A of the L2 norm of A, subject to A reproducing the correct f. Okay, now it is not hard exercise to check that this norm actually it's a way to express just the RKHS norm associated to this kernel. So by putting this complexity measure, L2 complexity measure on A, what I'm doing is that I'm recovering the reproducing kernel Hilbert space. And the kernel is just the product, the expectation of the product of the featurization map with itself. So it's the covariance of the featurization map. Okay, very nice. So in this case, we obtain a corresponding, we recover RKHS methods. And well, these of course are very successful methods and very interesting methods. And in particular, they attracted a lot of attention over the last couple of years because of their connection with neural networks in the so-called neural tangent regime. So setting the complexity in this form allows us to recover, for instance, 2 layers fully connected network in the neural tangent regime. Okay, so let me open a parenthesis to clarify this point, and in case for those in the audience that are not familiar with this literature. So what is the lazy or linear regime? Well, in over-parameterized neural network, one picture one might have in mind is that the set, so this is RP, the space of parameters of a neural network. And this manifold here, the submanifold of here is the set of empirical risk minimizers. So the set of theta such that the empirical risk evaluated at theta is 0. Okay? So these are the set of interpolators. So it's the set of neural network that achieve 0 training error. Now, what is this small arrow? This is the trajectory of gradient descent when you initialize at a random point theta 0. So the intuition behind this linear theory is the following. If the network is very over-parameterized, what happens is that this manifold of empirical risk minimizer is very large. So if I start at a random initialization, I converge very quickly to a interpolator that is close to this random initialization. If this intuition is correct, then you might as well linearize the neural network around initialization, construct a first-order Taylor expansion of the model around it, initialization, and then analyze this initialization. All right, now let me mention that linear theory probably misses some important phenomena and properties of neural network, but it's nevertheless an interesting regime. And so let me go with it. And if you take a 2 linear network, what happens and if you linearize, let's say with respect to the first order weights. So now I'm linearizing and I'm calling 1 over alpha the small parameter for my Taylor expansion and put a normalizing factor vector alpha in front. What happens when I linearize, you get a zeroth order term that has no free parameters, and then a first order term. And okay, the zeroth order term is often uninteresting, is roughly 0, but the first order term is, interestingly, is of course B, the vector, the change of the weights times the gradient of the model with respect to its parameters. And if you compute this Taylor expansion, you get this form. It's B times X times sigma prime W0 times X. Okay. So this gives you the linearization of the theory around its initialization. And okay, of course, this work, this is very much was pointed forward by work of Jacob Gabriel and Womler in 2018. And one corollary of this is that if this linearization is correct, then the implicit bias induced by, or implicit regularization induced by SGD is L2 bias, right? Because we know that if you're minimizing a quadratic penalty, a quadratic cost function, and using GD, you converge to the minimizer that has minimum L2 distance from the initialization. Okay, so in other words, what's happening is that linearization, if the linearized theory is correct, you obtain a linear model that is biased by this ridge penalty. All right, so now I rewrote the kind of prediction of this linear theory here, that really the neural network is equivalent or roughly equivalent to this linear model in which I penalize by the ridge penalty. And of course, this is as an equivalent infinite width limit in which I replace the sum by an integral. Now, this might look more complicated than the model that I wrote before, in which, because you have here this factor that depends on X instead of A of W, but just basically, essentially because all the Hilbert space are equivalent, you can rewrite this in the following form. You can rewrite this model as a model of exactly the form I wrote before, provided I use a different activation function as a different measure. Okay, this should be A. Okay, and I minimize the L2 norm. Okay, so this parenthesis was to show you that the random feature models with this penalty includes a special case, very large two-layer fully connected network in the neural tangent regime, and by a similar argument, you can also recover multi-layer fully connected networks in the same neural tangent regime. All right? So this kind of penalty is interesting, but it says its pros and cons. Its pro is that, of course, it can always be solved in polynomial time using the representer theorem. The con is that it suffers heavily from the curse of dimensionality. And this is what I'm going to talk next. Okay, curse of dimensionality. Perhaps I can pause and ask if there is any question. Okay, so I'll describe this issue with the curse of dimensionality referring to a result that we obtained a couple of years ago. There are many ways to look at it. So what I look is the following example. Assume data are distributed uniformly on the sphere of radius square root of d, so they are normalized to have L2 norm square root of d. The labels are some arbitrary function of the data plus noise. The noise is assumed to be independent. There are some weak assumptions on sigma, weakly differentiable with polynomial bounded derivative. And to state the results in simple form, I'll assume that this is the activation function is generic. And what I mean by generic, I mean that if I take the inner product of sigma with any Hermite polynomial, then I get something different from zero. All this product are non-zero. These are easily checked assumptions for many activation functions. finally assume that, so here I have 3, okay. I'm not stating this. So here I'll do infinite width network. Equivalently, I'll do kernel ridge regression with a sample size that is polynomially related to the dimension. Okay, and okay, we can assume that my kernel. So, okay, I should say one more thing to completely define the model. Here, the setting, the relation between activation function and kernel is that the kernel will be given to the integral of sigma wx1, sigma wx2, mu dw, as I wrote before, where mu is the uniform measure on the sphere of unit radians in d dimension. Okay, so this in particular implies that the kernel is a inner product kernel. Okay, so again, what I'm doing this is that I have data yi xi distributed in this way, and then I try to fit a model by minimizing over A the ridge penalty, which is also equivalent to minimizing over F in function space plus times, of course, the kernel, the RHS norm of F. Okay, so this is what happens to an infinite width network when you put L2 penalty, and of course includes neural tangent networks. Okay, so this is a result. It says the following: assume that n and d are polynomially related, so n is no longer larger than a polynomial in the dimension, and I call, for technical reason, I assume that n is not an integer power of the dimension. Something slightly more complicated happens there. Then for any lambda, the following happens: the risk of kernel ridge regression is equal to the projection of the target function. This is the risk, is the prediction error. So I fit F using the method that I described before, and then I look at the test error with respect to a new data point. Okay, so this is what I call RK RR here. And this is saying what? This risk is equal to the projection of F star onto polynomial of degree bigger than L. In other words, an equivalent way of stating this thing is that F hat of lambda, the result of kernel ridge regression, is the low degree polynomial component of F star. So you learn the low degree part of F star and you don't learn anything else. And further, no inner product kernel method can do better than this. Okay, so if you change the loss from square loss to another loss, you cannot do better. Okay, and this is true not in minimax sense for some bad F star, but pointwise for any F star. And another thing to point out about this result is that is achieved by lambda equals 0. So lambda equals 0 means really, what I mean by that, I mean that I'm doing minimum norm interpolation. So lambda equals 0, I'm minimizing, in other words, the RHS norm of F subject to fxi equal lambda yi for each I. Okay, so this means, this in particular says that interpolation in this model is optimal. Okay, so this is a sketch of the same result as a function of logarithm of the number of points, the number of data points versus number of dimension. If I call alpha, this means that n is d to the alpha. Something happens at the integers, but if you stay away from the integer, you see a staircase. And the level of the staircase corresponds to the projection of the function, of the target function, onto polynomials of degree bigger than L. Okay, so the consequence of this result that I want to emphasize is the following corollary. Take the following example of a target function. F star is equal to some G star of a one-dimensional projection. So this is a ridge function. Here, G star is a function R to R. Right? So the following corollary follows quite quickly from what I said before. If G star is not polynomial, then, in fact, even if it is a polynomial, but it's non-trivial if it is a polynomial, if it is not a polynomial, then for any L integer, if the sample size is less than d to the L plus minus delta, then the risk of kernel ridge regression is bounded away from 0. In particular, is equal to the projection, is approximately equal to the projection to degree L or L plus L or larger of G star in L2 of the Gaussian measure. Okay. And why is this a curse of dimensionality? Well, because learning such a function, if I know that it depends on a low dimensional projection of the data, will take only linear sample size. Okay, so by using kernel method, I cannot get consistent estimates of F star for any polynomial sample size, but if I know that it has a low dimensional structure, is sufficient nearly linear sample size. Okay, let me describe the same curse from a different point of view. Say that I take my general activation function, and as I'm doing in this part of the talk, as an inner product activation, and take this even more specific example of a target. My target function, this should be of x, sorry. But my target function is sigma, is a single neuron, is sigma of W naught times x. Then you can, of course, represent this as an integral, where the measure mu star will be just a Dirac delta at W naught. Okay? And now this is my target, and what I'm trying to do, well, I'm trying to fit it using a kernel method, so using a model of this form. Okay, again, this should be sigma, where A is bounded in L2. Yeah, so of course, this is a very bad model for representing this kind of functions. Okay, so this brings us to what we call minimum complexity interpolation. And what we mean by this is, okay, since L2 doesn't work, we can try to, so what was the problem with this curse of dimensionality in this thing is that we want A to be very small, sparse. Ideally we want A to be a delta function. Okay? So we might try to create, put a penalty here that depends on a function rho, convex function rho, and that induces sparsity. For instance, something that would be very nice is putting rho to be the absolute value. Okay, this is of course not a new idea. This appears implicitly in papers since the 90s in generalization, and is called convex neural network in this paper by Benjo et al. And was studied by a number of people, among whom Francis Bach. Okay, so there are two questions now that we can ask about this problem. What are the generalization properties of this method? And second is, can we solve this efficiently? And okay, in this talk, the residual of this talk, or in this paper, we focus on this second question. Can we optimize this problem efficiently? And why is the question non-obvious? Well, this is a convex problem. That's very nice. So we might hope to be able to, this is W, to solve it efficiently. but it's an infinite dimensional convex problem. And of course, if I was able to solve the infinite dimensional convex problems, I would be able to solve any NPR problem. Okay, so a first obvious step is that you can reduce this optimization problem to an interpolation problem. Why? Because you can call y hat I the values of the function at the sample points, and then call q of y hat the value of the penalty, the minimum value of the penalty subject to the interpolation constraint. So if I can compute this function q, now basically I can do this optimization because q would be convex, so this would be a convex, finite dimensional convex problem. So everything reduces basically to be able to solve the interpolation problem. All right, so this brings to this problem that is what we call minimum complexity interpolation. So we want to minimize this measure of complexity subject to matching the data on the sample points. And this is again infinite dimensional. This is a convex function. These are a linear set of constraints. So it's convex. Okay, so if so far basically what I gave you is motivations for looking at this problem. If the motivations convinced you, great. If it didn't convince you, or you fell asleep sometime, or you just joined, I think this is an interesting problem per se. Okay, so what is our approach to try to solve this problem? It's very naive. Okay, we just discretize the problem. So we have a measure mu. We want to do this in a way that is dimension independent, and it's good that we have a probability measure mu, because we can use the probability measure mu to sample IID weights with distribution mu, and then basically take the original problem and replace the measure mu by the empirical measure. By empirical measure, I mean just okay. So this is just the original problem in which I replaced mu by the empirical measure. Okay, now I stated the problem. I gave you our method to address it. Now I can state a result, and before that, the crux is of course in the assumptions. And what are our assumptions? Okay, now we have this featurization map phi, and we have n data points. So we can take the phi featurization map and evaluate it at n data points, and we'll obtain a vector boldface phi that is an n-dimensional vector. And this is, of course, a random vector because W is distributed as mu. The covariance of this random vector is the kernel matrix, the empirical kernel matrix. This is an n by n matrix whose entries, which is given by the expectation of the outer product of phi with itself. And so I can construct a whitened feature vector in which I multiply by k minus 1/2, so this is isotropic. So what are my assumptions? First of all, okay, data belongs to some ball of radius square root of d. The scaling with the radius is the right one to make things basically non-trivial. We assume that in specific examples, we assume that this feature vector psi, white-end feature vector, isotropic feature vector, is tau square sub-Gaussian when W has distribution mu. We assume that phi is Lipschitz in X for any given W, and Lipschitz constant can depend on W, so can be da. Random must be sub-Gaussian. And finally, the most important condition is this one, or the trickiest condition is this small ball condition. It says basically that if you take this random feature vector, so if you fix any basically two-dimensional plane in Rn, and if you project this random feature vector to this two-dimensional plane, its distribution doesn't concentrate on zero. Okay, namely, it's outside the box that is eta by eta, at least with probability delta. And eta and delta can be any arbitrary small numbers. And in fact, they can go to zero even inverse polynomially, I think, in some cases, at the cost of having the worst constants. I mean, worst exponents. Okay, this condition is implied by a stronger condition that is the more classical kind of small ball condition that says that will say something like this. So if you have this, you can get that as a consequence. Except that, okay, the second one is stronger because I have the constant 1/2 on the right-hand side. Okay, so this is a statement of our result. Take for simplicity rho to be x to the p between 1 and 2, and q is the dual of p. Then the model, this is the model that we learned by the discretized finite number of features model of random finite width model is close to the model that you learn by getting the infinite width network. In what sense is close? Well, we measure this in this L2 norm that is E of f of x a hat minus fn x a hat n square 1/2. So this is this norm. Okay, see here we are not, why this metric makes sense. Well, we're not that interested in measuring a hat and a hat n. We're not that interested in other specific things. What they are interested in really is that doing machine learning with this method. So we are interested that the prediction time, the discretized model gives you basically the same performance as the non-discrete model. And what we prove is that this difference is upper bounded by something that goes like a polynomial of the sample size divided by basically a polynomial of the number of random features. In particular, the right-hand side becomes small as soon as the number of random features is much bigger than the maximum of n square and n to the 1 plus q divided by 2. Okay, now I stated my result, our result. Let me emphasize. Okay, one thing is that, okay, I stated this result for x to the p, but we have, you can look at the paper for more general, some class of more general x's. Now let me emphasize two things, two weak points of this statement. First weak point is that the exponents here are not optimal. In particular, we know already from previous work, for instance, from joint work with Misiakiewicz and May, that in the case p equal 2, at least in some examples, then under some condition, n much bigger than sample size is sufficient. Okay, so the exponent here that I get, the theorem gives n much bigger than n squared, so this is suboptimal. So we know how to fix the proof in that case, but we don't know how to fix the proof for general p. So this is, and the other important weakness is that this rules out the special case p equal 1. Which is the single most important case. I think my thing froze. So the p equal 1 case is not covered. Yeah, we believe there are fundamental reasons for that. That is, if you could solve efficiently the case p equal 1, you would go against some basic complexity lower bounds. So you could solve NPR problems. Okay, so this is the theorem, just one figure for one small simulations. Here what we did is that we took, we generated synthetic data in 30 dimensions and used sample size 150. And the way generated data, we generate them as according to the hard example that I described before. That is, we generated this uniformly on the sphere of radius square root of d. And then we took yi equal f star of xi. I think this was noiseless, where f star of x was just sigma of w0 times x. Okay, so in other words, or I don't remember whether this is, but some function of w0 times x. So in other words, this is the model that is hard for kernel methods. It's the ridge function that is hard for kernel methods. And now I plot the test error as a function of the number of random features that I put. Okay, and okay, what we observe, okay, first look at these two curves in the case p equal 2. So the dashed curve and the red curve correspond to p equal 2. In the case p equal 2, as I mentioned, the infinite width limit corresponds to an RKHS kernel ridge regression with a kernel that is an inner product kernel. So we can compute the test error in this case. And this is the dashed curve is n equal to infinity. And if you look at the finite width approximation, we see that it improves and it saturates, reaching this dashed curve asymptote as it should be. Okay, so the theory works well for p equal 2. Now for p less than 2, we don't have an exact or a way to compute another way to compute the infinite width limit, but what we see is two things. First of all, so this is p equal 1.5, this is p equal 1.2. First of all, these curves, as the number of random features increases, seem to saturate to an asymptotic value. Okay, we would guess is what is predicted by the theory. And second, interestingly, we get a significant or a non-negligible improvement over the kernel method when we increase this sparsity promoting kind of penalty. Well, finally, we don't have any result for p equal 1, but we can still try to solve this method for p equal 1, and you get that we don't see any asymptotic floor, but we see that the performance increases and increases with the number of random features. So that's also very interesting. Okay, I want to spend a few minutes on the proof idea. So what is that we are trying to do here? We have the infinite width interpolation problem, and we replace it by the finite width interpolation problem. And this is really, as I mentioned before, corresponds to taking mu and replacing it by the empirical measure. Okay, so we want to show what? That in some sense, this interpolation problem concentrates, or the solution of it concentrates around the solution of this interpolation problem. And so one might hope to be able to use tools from uniform law of large numbers kind of result to prove such a statement. But this is difficult, this is challenging. Why? Well, because first of all, the limit problem is an optimization problem in an infinite dimensional space. My decision variable A is a function. And the finite approximation has a dimension capital N. So this is a problem in Rn. So you have a sequence of problems on spaces of increasing dimension. And so it's not obvious how to compare them using law of large numbers kind of arguments. Okay, so the natural idea is that you go to the dual problem, right? When you go to the dual problem, since we have lowercase n constraint, this becomes a concave maximization problem in Rn. So both the finite width and the infinite width problem are optimization problem in a finite dimensional space that is independent of capital N. And so we can hope to use uniform convergence tools to compare their optimizers. So what I said before is that we are really interested not, so what we are really interested is now, so this is the dual Lagrange parameter lambda. We're not interested in the value of lambda. What we are really interested in is the model that we get. But interestingly, if we compute the optimum lambda, you get out of it the model, and you know, just by the solving the KKT condition yields that the model is given by phi times this function or linear function S applied to lambda times the feature map integrated with respect to W. Okay, so what is S here? S is the inverse of the functional interverse of the rho prime. Just as a sanity check, if I take a rho to be rho of x to be x squared, that is the kernel method, then S of x is x, and what I obtain is f hat is equal to the integral. Oh, I should write up there. In that case, I obtain S of x equal x, and f hat of x lambda equal to the integral of phi x w times phi n w times lambda mu dw. And what is this? This is, by definition of phi, this is sum over I 1 to n lambda I times phi n of xi w. And remember that the kernel is defined as the expectation with respect to w of phi x1 w, phi x2 w. And so here what we get is exactly the sum over I 1 to n kx xi lambda I. Okay, so the case rho of x equal x squared, we recover exactly the standard formula for given by representative theorem. More generally, now you have this interestingly nonlinear function that makes your life much harder, of course. Okay, so now you have an infinite dimension, a finite dimensional optimization problem in lambda. And if you solve it, you get the model. So this is the infinite width model. And you have another optimization problem that is obtained by replacing mu by the empirical method, and you have your model. And so, a natural approach, that is what we follow. If we call, this lambda hat n, the optimizer of this, and lambda hat, the optimizer of this. A natural approach is what? We first prove that lambda hat n is close to lambda hat, and show that this implies that f hat of lambda hat n is close to f hat of lambda. So the hard part is, of course, this one. And okay, just a word about how we do that part. Well, we have, this is our objective, our dual objective. Okay, this is a concave function. And well, it has an optimizer somehow. This is lambda hat n. And then we have its expectation. This is f, and that has an optimized lambda. And so what we show is that at the infinite optimal lambda hat and at the infinite width optimizer, your objective finite width function fn has a small gradient. So here the gradient is small. And second, we prove that the function has a good curvature, is strongly concave in a certain neighborhood of lambda hat. Really, it's a certain corona. And once you have strong convexity and a small gradient, then we can prove our claim. Okay, I guess I'm basically done. Yeah, so the motivation for this work comes from this observation that in this linear training or lazy training regime, neural networks are equivalent to kernel methods. And kernel methods or RKHS methods are just feature models with quadratic penalty. And very wide neural network means that you're looking at some limit kernel. Right? So it's natural from this point of view, try to overcome the problem of this linear regime by introducing other biases, other inductive biases. And our main result is that this can be computed efficiently for certain type of penalties. That is somewhat sparsity inducing. That's all. Thank you.
Thank you very much for a very nice talk. If you have any question, please unmute yourself or raise your hand. May I ask a question about the numerical performance when you compare the proposed model with the deep neural networks? So we can see from your conclusion that there might be some
You're talking about this?
Yeah, yes. So now you just compare different parameters like P. You use, for example, linear model as the constraint, and you use some loss function with P as different parameters in the loss function.
Right. Yeah. So here we put different penalties.
Yeah, this is a very interesting idea, and the problem is it can be computed. It can be solved efficiently. In terms of performance compared to deep neural network in general problems. Have you tried to compare the performance?
No. I mean, here really what we are trying to do is, I mean, it's a good question. I mean, the comparison is really here to fully connected networks, right? Now, real multi-layer networks have all sorts of convolutional components, etc., right? So one idea would be, okay, take the fully connected block and replace it by this type of models, right? So this might work better, but yeah, I don't know.
I see.
Or,
like
since you mentioned deep neural networks, that is. But the first comparison to do that could be interesting is just take these models and try to compare it just to fully trained, 2 layers neural network, right? 2 layers neural network or 1 hidden layer neural network fully connected work a bit better than the kernels, right? Than the corresponding kernel. In some models, you have to search, not always, right? In some cases, the kernel works as well as the fully connected network. Yeah, it would be interesting to compare these two.
Thanks. Any more questions from the audience? If we don't have more questions, then it's time for a short break. We will meet again after 10 minutes. Thank you all.
Thank you, bye.
Could you try to switch your pages? It works. Thanks.
Great, thanks.
All right, maybe it's time to get started. So let's welcome back. Our next speaker is Professor Daniel Xu from Department of Computer Science at Columbia University. He's going to talk about computational lower bounds for tensor PCA. Let's welcome.
Great. Thanks. Thanks for the introduction, and thanks for the invitation to speak here. So yes, I'm going to be talking about a problem called tensor PCA. This is joint work with my former PhD student, Rishabh Dujaja, who moved on to a postdoc at Harvard. You may be wondering why I'm talking about this. It's not maybe directly relevant to deep learning, but there's some interesting connections and addresses some issues that should be of interest to people thinking about deep learning. Okay, so let me give a bit of motivation for this problem and why we should care about its computational tractability. So in a lot of problems in statistics, we find that there are useful statistical models that have hidden variables, and we would like to fit these kinds of models to data. But the standard way to doing that is to use likelihood-based methods like maximum likelihood estimation. But when we think about this kind of estimation strategy for these models, often in high dimensions, in the worst case, that optimization problem is intractable. Sometimes local search methods that people in statistics and machine learning like to use, like DM, will work, but not always. Okay, so it's useful to think about alternative estimation strategies purely from for computational reasons. And the method of moments is one such strategy that sometimes can be made computationally tractable. And here's an example. Sometimes you can arrange the moments of your the distribution usefully into some kind of tensor, and then you apply some kind of tensor decomposition approach. Okay, and an example of this is something that I worked on, which is if you're trying to fit mixtures of spherical Gaussian distribution to data, you just turns out that it suffices and under some condition to just look at relatively low order multivariate moments and fitting these kinds of you can estimate these things reasonably accurately, and then it amounts to kind of decomposing that tensor to recover estimates of the parameters. And sometimes this is computationally tractable. Okay, and this is a strategy that kind of is pretty useful, works for a lot of other hidden variable models. And it turns out some things like this have also been proposed as strategies for learning neural networks. Okay. But in these, so this is one connection. But in high dimensions, actually, these methods seem to be worse in a certain sense than the computationally tractable methods, in terms of what we can prove, and also sometimes the empirical performance as well. They somehow have worse sample complexity than the methods that we think should otherwise be computationally intractable. And it's interesting to ask why this is the case. And maybe this should shed some light on why sometimes the ways that we train neural networks are not quite as optimal as you might hope them to be. Okay, so this is the motivation for this kind of tensor decomposition problem. In fact, we'll look at the simplest kind of tensor decomposition problem where the tensor you're trying to decompose really only has a single component, a rank 1 tensor, but is corrupted by noise. Okay, and that's the tensor PCA problem. Okay, so tensor PCA is the following inference problem. You have capital N IID data points, each of which is some order k tensor. Okay, so k is some positive integer. So each of these data points is this order k tensor that's really just equal to a rank 1 symmetric tensor. Okay, that's given here. You can see my cursor, right? So it's a rank 1 symmetric tensor, but then it's corrupted by noise. Okay, and we'll say in this problem the noise is Gaussian noise. Okay. And so this vector theta is the unit vector, and that's the vector of interest. That's the vector parameter that you want to estimate. Let's say up to some sign flips. Lambda squared is the signal to noise ratio, and z, as I mentioned, is this order k tensor of Gaussian noise. So it's a order k tensor, so there's d to the k entries in it. And let's say every entry is an IID standard normal random variable. Okay, so that's the inference problem, and your goal is to get a good estimate of the parameter theta. So why is this an interesting problem to think about? Well, in the matrix case, it's a problem that I'm sure you know about. It's the when k equals 2, this is just a Spike-Wigner model. It's just you have a rank 1 matrix corrupted by noise, and this is something that you should can think about using PCA for. And so this is a natural model for studying the behavior of PCA. Now, if k is for general k, for k bigger than or equal to 2, this is kind of like a stylized version of the strategies of using method of moments with tensor decomposition, kind of like a stylized version of for studying those types of methods. Okay. So here, the difference here is that this is just a rank 1 tensor, so it's even easier. Usually the ranks of the tensors in the method of moments is usually higher, but we should be able to solve the rank 1 case before trying to attempt the higher rank case. Okay. And the reason this is the case is that usually theta is the parameter of interest, or is related to the parameters of interest in your statistical model. And the Gaussian noise here, okay, that's really not, the problems where this comes up is not really Gaussian noise, but there's going to be some sampling error due to the fact that you just estimate the moment tensors from finite samples, and you don't have the exact population moment tensors. Okay, so there's some discrepancy that is modeling that as Gaussian noise just to make things analytically tractable. Okay, so what's known here? So the matrix version of the problem, when k equals 2, what should you do? Well, as I said, the standard, this is kind of a model for studying PCA, so we'll see how well does PCA do. What do you mean by PCA? Well, you just take this matrix and compute the top eigenvector. Let's say you average these matrices together, compute the top eigenvector, and you can ask, when does this work? Well, this will work as long as the sample size is at least sort of the dimension divided by the signal to noise ratio, okay, and should be at least d over lambda squared. And this is easy to do because we all have a fast algorithm for computing eigen decompositions, so things are fine. Okay, but what about k bigger than 2? So k is at least 3 now. So things are quite different in these cases. This kind of problem, this tensor PCA problem for k bigger than or equal to 3, exhibits what's called a computational statistical gap. So what does this mean? This means that information theoretically, the necessary and sufficient sample size is just this quantity here, d over lambda squared, below which this quantity is information theoretically impossible. And maximum likelihood estimation works as soon as your sample size is above that quantity. Okay? But this is just information theoretically. Maximum likelihood estimation is not strictly an algorithm. We don't have general computationally efficient algorithm for implementing it. Okay. And what is the gap? The gap is that the known computationally efficient algorithms not just things based on gradient descent or anything, but any kind of computationally efficient algorithm that we might think of, they all require a much higher sample size before they start to work. The sample size has to grow with exponentially with k, so d to the power k over 2 divided by the SNR. Okay. So that's the gap that this, if you plot things on the log scale, log base d scale, the sample size, well, so this is the exponent of d. Below 1 is computationally impossible, or sorry, information theoretically impossible. Above k over 2, if the exponent's above k over 2, is computationally tractable, but we don't know of any efficient algorithms in this middle regime. Okay. And it's kind of a conjecture that that is, this is actually computationally hard in this regime when your sample size is here. Okay, so as I mentioned, there are efficient algorithms in the this easy regime, and they are all based on some kind of transforming the problem into a matrix problem. And this seems to be the best we know how to do. Okay. And what evidence do we have that the problem is actually hard in this intermediate regime when the exponent on d on the dimension is between 1 and k over 2? Well, we know that certain classes of algorithms will not work. Okay, so one possible class of algorithms is algorithms based on local search or local optimization. And these are known to not work in this regime. And we also know that certain kinds of convex relaxation approaches, things based on the sum of squares hierarchy, also will not work in this regime. So we know that certain types of algorithms don't work. And then we also have other forms of evidence that things should be hard in this regime. So one form of this is that if you believe some other kind of inference problem is computationally hard, then you should also believe that this inference problem is computationally hard in this regime. Okay? And so these are the kinds of problems that you should believe are hard, are the so-called hypergraphic Planck-Leap problem. There are other forms of evidence based on calculations and different types of information theoretic restrictions. I won't really get into these though. Okay, so we have this kind of setup where this inference problem is hard only in a certain sample size regime. When once you have enough data, the problem seems to be computationally easy. And we'd like to, as theoreticians, we would like to somehow establish this thing and put this thing on a very firm footing as possible. Okay, so it definitely would be great if we could prove that this tensor PCA problem does actually require, let's say, exponential time in the conjectured hard regime, but definitely we're nowhere close to being able to do this. So instead, we're going to shoot for something much more modest. Okay, we're going to try to prove modest lower bounds for very, very general classes of algorithms that have computational resource constraints. And turn out the kind of computational resource constraints will be both time and memory, and later, if I get to the proof, also communication. Okay. And we think that if we do this, we can get some insights into the existing algorithms that we have for this inference problem, which I think should be relevant for the kinds of strategies you might be thinking of for developing efficient algorithms for learning problems like you might try to learn with neural networks. And the other kind of side thing that we get out of this is that we get some insight into the role of overparameterization, which is something that I guess comes up in the context of neural networks. Why is it that we need to sort of use a solution concept that's much bigger than might otherwise be necessary? And we will have a very kind of precise way to say what we mean by overparameterization and specifically why it is beneficial for these kinds of tensor PCA inference problems. Okay. I'll get into that more as we get into the talk. Okay, so here's the main result very informally. Tells you can set up what I mean by computational resource constraints. So what can we prove? We can prove that every algorithm that's supposed to work, that you can prove that works for solving the tensor PCA problem in dimension D, order K, with signal to noise ratio lambda squared. Every algorithm that accurately estimates the parameter of interest theta has to have this kind of lower bound on the amount of resources that it consumes. So so it's really the product of three things: the memory size of the algorithm, the number of iterations, which is you can think of as a stand-in for the runtime of the algorithm, or at least it's a lower bound on the runtime of the algorithm, and the sample size. So this is where the capital N that I was talking about before. The product of these three things has to be at least some quantity. And that quantity is something that involves d to the power of k plus 1 over 2 divided by lambda squared. Okay. Now, again, to specifically why this is a strong lower bound. But one way to interpret this is that if you fix, let's say, any two of these resources, let's say you fix the sample size to, let's say just d, and you fix the amount of time you're willing to use, the number of iterations, then that gives you a lower bound on the memory size that your algorithm must use. Or alternatively, let's say you fix the memory size, you only want to consider algorithms that use order D memory and a particular sample size, let's say order D sample size, and that gives you a lower bound on the number of iterations your algorithm has to take. In that case, it'll have to take something that starts to grow with d to the power, or something that grows with k. And that explains why the algorithm might take a long time when k is large. Okay, so that's informally what the main result is. I'll get into, hopefully I'll get to say a little bit about the proof techniques in this talk, but at a high level, to preview it, we use techniques from communication complexity using this reduction that I guess was nicely described in the paper by Shamir and later by Dagan and Shamir. And so really our technical result is something about distributed estimation and how much communication is required to do that. But it's going to have implications for algorithms that really just run on a single machine. So algorithms that you might run for, even if you're not in a distributed setup. Okay. I'll say more also about a slight variation of the tensor PCA problem, which is the asymmetric version of it. Because this is where we'll be able to say something about overparameterization. Okay. Good, so this is the outline for the rest of the talk. I'll describe the computational model and present what the lower bounds are for the tensor PCA problem. Then I'll describe the asymmetric tensor PCA problem and give, again, the lower bounds and just say something about overparameterization. And then I think there should be time. This is not supposed to be like a full hour-long talk, so I think there should be time to say a bit about the proof techniques. Okay. Are there any questions at this point? Yeah, feel free to unmute and ask questions if you have them. Okay, so good. So I'm going to try to prove lower bounds, computational lower bounds for tensor PCA problem. So I need to tell you what the computational model is. Okay, so our computational model is supposed to somehow say something about how much memory an algorithm uses and also something about the runtime of the algorithm. Okay, so here's the model that tries to capture this. So every algorithm is going to have some kind of memory state. It's going to be able to write down some bits into this memory, and we're just going to regard this as a vector of bits. Let's say 0, 1 to the b. So that's the memory state. And then what does the algorithm do? It's going to make some passes through the data. It's going to somehow take the data and process each data point. Remember, each data point is this order k tensor. So it's going to make capital T passes through the data, and then in each pass, I'm going to go through the data points one by one. And what does it do? It's going to look at the ith data point. Okay, when it gets to the ith data point, it's going to look at it and compute some function of it both of the function of the data point and of the current memory state. And that's going to update the memory state. And you're going to do this with for the next data point, you're going to update the memory state again after that. And after doing this, for every data point, and capital T times, you make capital T passes through the data. Then you have to just, as a function of just the memory state, return some estimate of the parameter theta. Now this is very general because we're not even going to, restrict what it does in these update functions or what the final function it computes on the final memory state is. We have no restrictions on those quantities. Those really can be arbitrary functions. In fact, the update function can depend both on which pass you're going through the data point data's in, and also what you can do something differently for each different data point. Okay, so that's what we mean by an algorithm, memory bounded algorithm. So clearly here, B is just the amount of information it keeps track of after it processes every data point. So this is certainly a lower bound on the, really the amount of memory the algorithm needs. And really the number of iterations here is also really a lower bound on the number of, amount of time in some sense that the algorithm requires to execute, because we're not really counting anything about how long it takes to the complexity of computing any of these update functions or the final estimate. Okay, but let's see what can you do within this model. It's very general, but let's see how you might do maximum likelihood estimation. Okay, so maximum likelihood estimation turns out in this problem, it amounts to looking at the average of all of the data points. So this is, you just take the sample average of all of these tensors, it's called X bar, and looking for a vector theta hat, whose order K tensor product has as large of an inner product with that average tensor. Okay. And just to make things simple, let's say that even the parameter space is just not the entire unit sphere, but just this discretization of the sphere. Okay. You can really just enumerate through these things. Okay, so we're really here, we can take advantage of linearity so that this inner product here decomposes over data points. Okay, so it's really just the sum over all the data points of the inner product between this candidate tensor, rank 1 tensor, and the ith data point. Okay, so you can evaluate the objective for any candidate parameter vector just by, in a single pass over the data. Okay. And so then what's a way to implement this algorithm in this framework? You just kind of check the objective value for every candidate parameter vector. There's only 2 to d of them, and then return the one with the highest value. So the state that you need to track this information, well, you need to keep track of what the best value is so far. And then you also need to keep track of what the best parameter vector is so far as you're kind of trying out all 2 to the d parameter vectors. So the space you really need is something that's, ignoring discretization issues. Although I guess there's none here because of this assumption. You just need order d bits of memory. Okay. Now, of course, the runtime here is that we're going to try every possible parameter vector, so the runtime is exponential in dimension. Okay, so the memory is just linear in dimension, runtime is exponential in dimension, but this is maximum likelihood estimation, so we also have sort of the optimal sample size. And we're sort of nowhere close to being able to say something about this is the best you can do, but we'll try to say some things that are not too different from this. Okay, so that's a computationally intractable algorithm, even though it has optimal sample size usage and essentially the optimal memory size use. Okay, but what are efficient algorithms for tensor PCA? As I said, they all kind of somehow change the problem into a matrix problem. Okay, and here's one such algorithm. This is for the case where k is an even integer. So this is an algorithm called the partial trace algorithm due to Hopkins, Sherm, Shi, and Stroyer. So as I said, you try to transform the problem into a matrix problem. And how do we do that? Well, you can get a matrix from, so you have this kind of order K mean tensor. That's a tensor, order K. Let's try to collapse it down to a matrix. And here's how we're going to do it. We're going to essentially sort of sum over all of the kind of diagonal entries along, all but K minus, all but two of the modes. So K minus two different modes, you kind of sum up the values of the mean tensor along the diagonals. And you do that, so that's going to just take what the ijth entry of this matrix is, where your ij is here, but you sum over all the remaining just sum over the kind of pairs of modes. So if this was it's sort of analogous to taking like a trace of a matrix. Okay, so maybe, and then you have a matrix, and then what do you do with that matrix? I said this is the matrix method, so you just compute the top eigenvector of that matrix. Okay. Now this, if you think this is reducing to a matrix problem, maybe you think that this should be a problem where you need quadratic space, d squared space, but it turns out you can kind of implement the power method, with just linear amount of memory. Linear in dimension amount of memory. So you just need to kind of have enough space to just store your current, iterate for the power iteration. And that's just order D space. Okay, so why does this algorithm work? Well, so remember every data point was the rank 1 tensor plus Gaussian noise. When you sort of average all these tensors together, you get the mean tensor. Again, the mean doesn't change, so it's just the same rank 1 tensor, but now the noise has kind of has this variance down by a factor of n. It's really like 1 by root n times a Gaussian tensor. So, okay, so what does partial trace do? Well, it basically kind of sums up a bunch of the entries of the tensor together. Turns out that's not going to affect, it's still going to, the effect of doing that partial trace on the rank 1 part really just reduces it to another rank 1 matrix now. But you just kind of sum up coordinates, pairs of coordinates over pairs of modes. And because this is a unit vector, you get a bunch of things summing up to 1. So the effect of the partial trace on the rank 1 part just makes it down so that you have a rank 1 matrix. Okay. But the effect of partial trace on the noise actually kind of accumulates a lot of noise. You add up a bunch of ID Gaussian variables, the variance starts to grow, okay, and basically grows by this factor, okay, by a factor of d to the k over 2 minus 1. Okay, so you sum up a bunch of noise variables. So you sum up this many noise variables per entry of this matrix. So what's happened is that you've reduced the SNR. Before the SNR was something with lambda squared. You now reduce the SNR by this factor, okay, d to the k over 2 minus 1. But it's the matrix problem now. Okay, so we reduced the problem from this order k tensor problem to an order 2 matrix problem, but with a smaller SNR. And so the upshot is that you just plug in, how much data do we need to solve the matrix problem? Well, it's d over the SNR, but now the SNR is small, smaller by this factor. So the sample size that we need is d to the k over 2 divided by lambda squared. Okay. But it's a matrix problem because, and we can solve it using the power method. So we don't need many iterations of the power method for it to work. Let's just say logarithmic and d iterations, and I'm going to ignore log factors in all my discussion here. And the space that you need is actually very small as well. So I argued that you just need linear bits of memory, linear and d bits of memory. Okay? And here you can already see that the memory size and times the sample size times the number of iterations is really just d to the k over 2 plus 1 times the log factor divided by lambda squared. And our main result for tensor PCA is that this is optimal. This product of these three resources cannot be much better than this, what the partial trace algorithm has. Okay. So any algorithm for partial trace, or sorry, for tensor PCA, dimension d, order k, it's SNR lambda squared, that has much smaller resource usage in terms of measured in terms of memory size, iterations, and sample size. When you multiply those together, smaller than the one they had for that algorithm I showed before. It's necessarily going to return you a solution that doesn't have much to do with the actual parameter vector. It'll be nearly orthogonal to the parameter vector. Okay, so why is this interesting? Okay, I should say, there's this remark here that sample size should be needs to be at least d over lambda squared, but that's just because that's the information theoretic lower bound on sample size anyway. Okay, so this is interesting because this is the unconditional lower bound on the amount of computational resources, computational and information resources that an algorithm needs in order to solve the tensor PCA problem. So if you hope for your algorithms to return an accurate estimate, it has to use a large amount of resources. Good. So now, okay, this is nowhere close to being able to say that any particular algorithm needs to use exponential in dimension time or anything like that. But at least it does rule out certain algorithms with different computational profiles. So let's see what this kind of looks like. Okay, so here I'm fixing, there's three different resources. I'm going to fix one of them, say the memory size, to be only linear in the dimension. And then we can look at what things look like in terms of the other two quantities, the runtime measured by the number of iterations and the sample size. I'm going to put things on the log scale. So we're just looking at the exponents on D for the runtime and for the sample size. Okay, so this is the region of computational profiles. When you fix the memory size to be D, and now you look at how things vary in terms of the number of iterations and the sample size. Our theorem basically rules out any algorithm in this kind of striped triangle here. Okay, any algorithm that's going to use much fewer than, let's say, D to the K over 2 data points, okay, is going to have to use at least some polynomial number of passes over the data. Okay? And the partial trace algorithm is really sitting right here at this green dot here. Okay. So yeah, and remember it uses only linear memory. Number of passes it makes through the data is just logarithmic in dimension, so it's really at the vertically at the very bottom, and the sample size it needs is D to the K over 2. Okay. And what does the lower bound say is that we cannot hope to get say an algorithm with much smaller sample size usage without also either increasing the memory significantly or the number of iterations. Okay, so that's the way to interpret this lower bound for tensor PCA. Okay, let me. Okay, so that's all I want to say about that. I'm going to turn now to a variant of the tensor PCA problem, where there's going to be a little bit more something else interesting to say about overparameterization. Any questions at this point? Okay. Good. So let me tell you about the asymmetric tensor PCA problem. Oops, sorry. Okay, so it's kind of what you might expect from the tensor PCA problem. Every data point was a rank 1 symmetric tensor corrupted by noise. Now, for the asymmetric version of the problem, it'll be a rank 1 asymmetric tensor and then corrupted by noise. Okay, so what's an asymmetric tensor, rank 1 tensor? Well, you just take k different unit vectors, you take their tensor products in this order, and then you scale it by some quantity lambda. Okay. But otherwise, everything else is the same noise, Gaussian noise, order k tensor, ID standard normals, lambda squared is still the signal to noise ratio per data point. And really, a lot of things stay the same. So when k equals 2, this problem is quite easy. We know that you can just use the power method to compute the top singular vectors. That will give you, theta 1 and theta 2. And this is going to work, give you good estimates of the true parameters, as soon as the sample size becomes at least d over lambda squared, d over the SNR. Okay. But again, there's a computational statistical gap when k is at least 3. The problem, again, is, as I said, information theoretically impossible if the sample size below d over SNR, and brute force or maximum likelihood estimation works as soon as n is at least that quantity, d over lambda squared, but we don't have any efficient algorithm for doing this. And all the computationally efficient algorithms that we do have need a much higher sample size, okay, d to the k over 2 by lambda squared. Okay, so good. So there are efficient algorithms for asymmetric tensor PCA, and again, it's kind of obtained by transforming the problem into a matrix problem. And here's the particular way of doing that for the asymmetric tensor PCA problem. It's I guess people call it tensor. People would like to call it matrixization, and this is an algorithm that was kind of described in this paper by Montanari and Bouchard. So what do? You take this order k tensor, the mean tensor, x bar, which is the order k tensor that you get by just averaging all the data points together. Again, let's think of k being even. Well, you can kind of treat the first k over 2 modes as a single dimension or single mode, let's say rows, and then treat the last k over 2 modes as columns. So now you have d to the k over 2 rows and d to the k over 2 columns. And that you could just regard as a matrix. This doesn't change the information in the mean tensor in any way, it's just kind of interpreting things differently. So you just interpret it as a matrix. But it's a very big matrix. And now you take the rank 1 singular value decomposition of this matrix, okay? Let's say using the power method. And now this should, in some sense, tell you, it turns out this will tell you quite a lot about, let's say the left singular vector should be very close to like the tensor product of theta 1 by theta 2, so on up to theta k over 2. And the right singular vector, the top right singular vector should be the tensor product of theta k over 2 plus 1, theta k over 2 plus 2, and so on up to theta k. And so you kind of just need to undo, those tensor products. I mean, these are very close to rank 1 tensors. So there should be some way to try to do that. And it's not exactly just the kind of like the undoing of the matrixization operation that we did up here, but it's almost that, okay? And this basically works. Okay, and it kind of works for slightly different reasons. So matrixization, as I said, doesn't change any information, just interpreting things differently. Okay, so here, this matrix interpreting x bar now as a big matrix. Again, it's a rank 1 matrix corrupted by noise, but the left singular vector is this, like the tensor product of the first k over 2 parameter vectors, and the right singular vector is the tensor product of the remaining ones. So what happens is that we instead change the tensor PCA problem, the asymmetric tensor PCA problem, into one just in a much higher dimension k over 2, d to the k over 2. But it's a matrix problem now, and the SNR has not changed. Okay. So what's the sample size that we need? Well, the sample size should be growing with basically dimension over SNR, but now we're working in dimension d to the k over 2. Okay, and yeah, so how do in terms of other resources that we need to implement this algorithm, you need enough space to write down these left and right singular vectors. So d to the k over 2 bits of memory will be used here, but it's the power method, so you just need log d iterations. And now if you look at the product of memory size, number of iterations, and sample size, it looks like it's d to the k times log d over lambda squared. And this is optimal, okay, at least in terms of the product of these three resources. Okay, so our second theorem for asymmetric tensor PCA says that you cannot do much better than this. Okay, so now it's actually quite a bit harder because the product of these things, these three resources, has to be d to the k, whereas for the symmetric tensor PCA problem, it was just d to the k over 2. Okay, yeah, so strictly harder than the symmetric version of tensor PCA. And again, we can sort of fix one of the resources and then look at how things vary at different profiles, potential profiles of algorithms along the other two axes, other two dimensions, resources, time and sample size. So let's fix the memory size to d to the k over 2 bits of memory, because that's what we need for that matrixization algorithm. So what does our theorem say? It again rules out algorithm with computational profiles in this triangle. And the matrixization algorithm that I described again sits right here at this at the corner of this triangle. Okay, so the sample size is definitely in this easy regime, and the number of iterations it needs is just logarithmic in dimension. But trying to find an algorithm that uses a smaller sample size is necessarily going to, again, we have to increase the either the runtime quite a lot or the amount of memory that you need. Okay, so now I want to say something about I guess the one thing that you may notice that the matrixization algorithm uses quite a lot of memory, d to the k over 2, even though the amount of memory that you need to write down the answer is just order d, I guess k times d, but think of k as not growing with dimension, but just like a constant. Instead of d to the k over 2, you really just need order d memory to write down estimates for all the parameters. So this uses quite a bit more memory. Now you can ask, is this really necessary? What's the kind of role of using more bits of memory than you really need compared to the size of the solution you're looking for? Okay. Good. So I think of the matrixization algorithm as an over-parameterized algorithm because it's kind of keeping track of more information than you really need to write down a solution. Okay, so let's look at algorithms now that don't do quite this. They use much smaller amount of memory, okay, smaller than d to the b bits of memory, where b is something strictly less than k over 2. So let's fix that memory size and then look at the computational profiles that you might hope to achieve in terms of the iterations, number of iterations, and the sample size. Now, if you do this, what our theorem does is it rules out algorithms in this entire striped triangle, okay, which is now going to extend into the kind of easy regime in terms of the sample size requirement. So we know that there are computationally efficient algorithms that work when the sample size is in this regime, as long as n is at least d to the k over 2. But if you're going to use smaller amounts of memory, just only d to the b bits of memory, where b is less than k over 2, then you're going to necessarily need a much higher runtime. Okay, so much higher than what the matrixization algorithm requires. So I think this is one the concrete lower bound against algorithms that do not over-parameterize in this sense. Okay, that they necessarily will have a much higher runtime when given the same amount of data. Okay, so that's really what I had to say about over-parameterization. So I guess I have some time to say a little bit about the proof strategy. Say a few remarks about this. So I mentioned at the beginning, the kind of the technical nature of these results is basically a theorem about communication complexity, or essentially how much communication do you need to do distributed estimation, kind of solve the tensor PCA problem in a distributed setup. Okay. And we're going to use a particular reduction from this distributed estimation problem to the memory bounded inference problem setting. This reduction, I think it's, things like it have been used quite a lot in the literature, but we're using a particular form of it due to Shamir, and then also later Dagan and Shamir. Okay. So basically what the reduction does is it tells you how to transform, if you have a memory bounded algorithm for solving an inference problem, you can turn that into a protocol for distributed estimation with bounded amounts of communication. Okay. So if you have an algorithm with memory profile B to uses B bits of memory, uses T iterations, and uses sample size N, we'll have a protocol that uses this amount of communication. Okay, so what do we need to do then? We need to prove a lower bound on the communication that protocols need in order to solve the tensor PCA problem, and that's really what our technical result is about. So for the tensor PCA problem, we show that any protocol, particular communication model that solves, that accurately estimates the parameter, is going to need, communication, just number of bits to ever get sent, at least this quantity here. And since there are no such protocol to do better than this, then there's also no algorithm to have a better computational profile in terms of their memory size, number of iterations, and sample size usage. I can describe the reduction. It's kind of nice. I think maybe of interest to people if you're interested in proving these types of lower bounds. So it's a reduction from this communication in this Blackboard model of communication. This model, kind of says that there are going to be a lot of machines, let's say capital N machines, and each machine gets a single data point. Okay. How did the machines communicate? They all communicate in this via this public Blackboard, okay, that any machine can read without any cost. So that's, we're not going to track that amount, the cost to read the contents of the Blackboard, but writing to the Blackboard, we're going to track how many bits any machine ever writes to it. Okay. Good, and how the machines decide how to write, when to write, and so on, that's all dictated by the protocol. Okay, so based on who gets to write, that's dictated by the protocol, and also what's on the Blackboard currently, that will tell you who gets to write next, and then what that machine writes. Okay. So things are hard because a machine can only base what it writes on the Blackboard based on what it sees on the Blackboard so far and what it knows about its own data point. Okay. And somehow at the end of, after all the communication happens, you need to return some final estimate. That final estimate of the parameter has to just be a function of the Blackboard contents. And so here's how, if you have a memory bounded algorithm that uses B bits of memory, uses T iterations, and uses only sample size N, it turns out you can define a communication protocol in the following way. Okay. Let's just assume that the initial state of this algorithm is already written on the Blackboard. Maybe just say the initial state should be some dummy values. We're going to now define a protocol. Well, our protocol is going to be very simple. Just for every kind of iteration of the algorithm, T, and for every pass through the data set T, and every data point I, we're going to have the first machine, the ith machine, read the current state of the Blackboard, and then locally compute an updated version of the state based on its own data point, and according to what the update rule is, for this algorithm that gives you a new state, and then the machine is just going to write that new state onto the blackboard. Okay. And so just execute, kind of simulate running this out memory bounded algorithm, and then at the end of this entire process, you'll have written a bunch of states onto the public blackboard, and you can certainly use the same estimator that the algorithm, this memory bounded algorithm uses to give the final estimate of the parameter based on what's on the blackboard. Okay. And it's kind of hopefully it's clear that the total amount of communication that you would need to execute this protocol is exactly just the memory. You have to write b bits of memory every time, and how many times you have to do this? Well, it's just t times n. So the total amount of communication that gets used is b times t times n. Okay, so this is a reduction. These other folks definitely don't. I think this model is also something that's in the literature, but I think this is basically a nice strategy for getting computational lower bounds via communication complexity. Okay, so really, to really get into the details, what we have to do is prove some kind of information lower bound. We're going to use Fanon's inequality, some version of it for Hellinger information. Roughly speaking, what we show is that the the Hellinger information between a random parameter drawn from a prior and the contents of the blackboard, or the contents of the protocol, or the transcript of the protocol, cannot be very large if the amount of resources that you use is not sufficiently large. Okay, and so what we'll show is that this information quantity goes to 0 as the dimension goes to infinity, which will then imply that every protocol will at least fail for some parameter vector. Okay.
I'm sorry to interrupt, but we are running out of time.
Sure. Okay, I'm wrapping up now. So yeah, so this is really what we end up proving technically. Okay. Good, and I'll skip this. So yeah, so so I guess that the upshot is, of course, we don't prove exponential lower bounds for any kind of class of general algorithms. That's way beyond what anyone can do right now. But we do get some kind of more modest lower bounds via communication complexities. So if you're interested in these kinds of inference problems, I think they are very related to what goes on in with learning problems related to deep learning. You can go this route of studying the communication complexity of some associated problem. Yeah. And by doing this, we kind of show that certain algorithms are unimprovable. And it says something about the role of overparameterization, which again, I think is relevant for deep learning. Okay, that's all I wanted to say.
Thank you very much for a very nice talk. I'm afraid we don't have time for question. We could discuss later after the next talk. Okay, so our last speaker is Jason Lee. Jason, could you try to share your screen? Jason, are you there?
I think he's muted. Let me
I'm trying to join on my iPad. It says I'm trying to join on my iPad.
Sure.
It's not working for. Okay, now it works. Oops. Let me close this.
Okay, I think it works. So our next speaker is Jason Lee from the Department of EECS at Princeton University. He's going to talk about
on the foundation of deep learning, SGD, over parameterization and generalization. Thank you. Oh, not you changed the title. He's going to talk about a new talk. The title is the verbal tour of linearization and beyond in deep learning. Let's welcome. Jason, are you speaking? We cannot hear you.
Oh, I'm sorry. Okay, yeah. Now?
Yeah, I can hear you now.
Okay, sorry about that. But then you can't see me if I... Okay, I should have.
We cannot see the slide.
You cannot see this, right. Okay, here, and now?
Yeah, we can see that.
Okay, yeah, so today I wanted to talk about some of the, give an overview of the work done in deep learning using this linearization tool and how you can go beyond linearization because what it can prove, what it cannot prove, and how to go further. So there are some subjective statements, and those are my opinion, and but all of the mathematical statements are joint work. Okay, so I wanted to talk about a few topics. The first one is what is linearization in deep learning, how to go beyond this, more recent results in going beyond linearization, and sort of the open problems left. So I'll focus more about on what optimization-based algorithms, or mostly what gradient-based algorithms can prove for minimizing the train loss. So this means I will essentially not talk about methods such as spectral methods and tensor methods, which are also very efficient, give computationally efficient and statistically efficient methods for deep learning, simply because they kind of just don't fall well into the framework I'll use to think about things. Okay, so I'll categorize sort of proofs for gradient-based deep learning into three categories. The first one only uses that the gradient is non-vanishing. So this is like essentially gradient non-vanishing by the descent lemma, you make progress. And if you keep making progress, you converge to a global minimizer. Perhaps one of the simplest proofs you could ever come up with. Okay, and then there are proofs that require some information in higher order derivatives, though the algorithms do not. For example, if you want to converge to local minimizers, then perhaps local minimizers have better statistical guarantees than simply stationary points. You can do this via gradient-based algorithms, although though the algorithm doesn't need any Hessian information. And finally, I'll talk about sort of the third class is methods that require a sequential order of learning. They sort of need to argue that you first learn A, and then after you learn A, you can then learn B easily, and so forth. So let me give some examples to make this more concrete of these three categories of what we can learn with gradient methods. Category one essentially contains all of convex optimization. Convex optimization, like if you have the convex optimization, if gradient f of x is 0, implies global min. And then so the converse is, and then so of course, if the gradient is not 0, then you're not at a global min. So you can keep making progress until the gradient hits 0, which gradient descent will always hit 0 eventually. And then you must be a global min. So actually, so beyond convex optimization, there are a few interesting examples of where this gradient non-vanishing condition holds, yet it's not convex. Among these are sort of these single neuron models, plus well specified. So the data comes from W star plus noise. And then if you do gradient descent on the square loss, let's say, then you will find W star, although it's not convex. This kind of things go by many names: 1-point convexity, star convexity, most of local convergence. You might have heard of things like the PL condition, KL condition. There's 1,000 things. They're all kind of the same. Quadratic growth. Okay. Unfortunately, this is pretty restrictive. All of these models essentially need just a unique global min, because, or at least a connected set of global min. For example, this would not allow you to do a matrix factorization in the rank 1 case even, because W and minus W could be both global minima, but they're not connected, and there's no way for something like the PL condition to hold in that case. So kind of motivated by this need to go beyond just looking at the gradient, category 2, people started looking at what happens if the gradient is 0 and the Hessian is PSD. So this is essentially local minima, informally speaking. And now you can start talk about slightly more things. You can now have matrix factorization, matrix completion. So all of these matrix problems fall under this category, like SVDs, eigenvalue decompositions. Those are all non-convex problems. But you could argue one reason that they're efficiently computable is they have good landscape properties. And category 2 is really about these landscape properties. The topology, the geometry of the landscape. So then tensor decompositions also fall in this category: phase retrieval, saddle points. You can massage 2-layered networks with a carefully designed loss, not with a natural loss, into this category 2 methods. Category 3, these are more specific methods. They require very specific assumptions on Y condition on X. A lot of these argue sort of a hierarchical learning process. So I've given some references here. I'll discuss one of them, one of my own works, later on in the talk. And so category 3 proofs generally kind of look like chaining together steps of category 1 and 2. And then you kind of alternate between using these, and depending on which stage of the algorithm you're in and what you need to learn. Okay, so my plan for today is I'll try to cover using first order and second order information. I'll first talk about the linearization principle, and as it's sort of the most generally applicable, and then I'll move on to a little bit of things in category 2 and 3. Okay, so what is linearization in deep learning? This is nothing but Taylor's theorem. So you have, this is your network, just some nonlinear function of X. You Taylor series around your current point. This term will generally ignore, it can be bounded in, pretty simply, or just think about it as some order 1 quantity. This is the important term. And then for some reason, I'll throw away this term. More precisely, I should have wrote it like this. But it turns out that there are some simple scaling tricks you can do to make this very small. Little of 1 with respect to the width. I'll talk about this in a second. Okay, so then if the second term were negligible, then what we would have is that f theta is now linear in theta, right? This term here is linear in theta. And suddenly you've reduced deep learning to a linear function. So, and then if you can use over-parameterization kind of to kill this and this one. And then now suddenly you've just got a linear function. The important thing is killing the second term. The first term is not dependent on theta, so it doesn't affect optimization anyway. So this technique was first used in one of my earlier works with Sota no Katabi and Javin Martin Lee to prove that gradient descent can find global minimum with minimal over-parameterization. Later on, it was reinterpreted as sort of as this kernel viewpoint by Jacob and Du et al., Aurora, Shazad, and Bach, called the NTK. And then in parallel work, other groups of authors called it the pseudo network, but they're kind of the same thing, is that you just approximate the network with a linear function. And I'll show you the original proof from the Sota no Katabi et al. Paper of how this can get you to show you that gradient descent converges to a global minimizer. Okay. So you can think about this now. The reason sometimes this is called the neural tangent kernel is that it's just you think of that as a linear function and you think of this as the feature map. And then if you have any convex loss function or any loss function really, you can kernelize it and it's equivalent to solving a kernel machine with this kernel here. Okay, so we're not going to talk today much about kernel methods and the statistical properties of kernel methods. Instead, I'm going to focus on linearization, mostly as a tool for analyzing optimization. So let me look at two-layer neural networks. I'm only going to train the W's for now. The loss will be convex, it will be square loss. However, this is non-convex in W's. You train the W's, they're on the inside of the nonlinearity, this is non-convex. It's convex in the A's but non-convex in the W's. And then if you train both, it's non-convex still. Okay, but now look at this linearized guy. Now this is linear in theta. So linear function composed with any positive convex loss. That's a convex function theta. So actually, if I could magically optimize the linearized function instead of the neural net, I would have a convex optimization. In fact, it satisfies one of the conditions I mentioned. This is the Polyak condition. When the sigma min, the minimum singular value of the Jacobian is positive. So the Jacobian is a matrix that's parameters by n. It stacks the gradient with respect to theta of x1 through xn. Okay. And then, so I'll show you how we use this in our 2017 paper that I think first used this linearization, at least in the context of deep learning. Okay, so there's two steps you need to do here. The first is that you want to show that your linearized network f hat is close to theta for all the places GD goes. This is obviously not globally true, right? Like as soon as you theta minus theta, as long as the second term in the Taylor's theory dominates the first term, this is not true anymore. But the hope is that if you converge so fast that you don't need to move a lot, then this can be true. And in fact, the way you'll show you converge fast enough is by ensuring the Jacobian is positive, or the minimum singular value of the Jacobian is positive for all theta encountered by GD. Okay. The way we do this is by establishing two intermediate results. The first is showing that the Jacobian is sufficiently Lipschitz, which is equivalent to the Hessian being very small. This is essentially trivial, is essentially by a small rescaling trick. There's nothing deep here. And the second is showing that sigma min of J at initialization is positive via random matrix theory. This is difficult. Okay, and this is kind of trivial essentially. To make the J sufficiently Lipschitz. And then finally, if you're sufficiently Lipschitz, just by Wales inequality, the operator norm moves less than the Lipschitz constant. And then sigma min of J of theta is bigger than the initial one minus this. And then, so this is still positive. And then when this is positive, you converge geometrically. And because you converge geometrically, you don't move a lot, right? If you converge geometrically, it means your gradients are shrinking geometrically because the gradient norm is upper bounded by the loss. So then you must, and then so sort of you can just induct on this, right? You start out at a point where the sigma min is positive. So you take a gradient step that decreases the loss a lot. You moved a bit, still positive, you decrease the loss some more. And then eventually, because you're geometrically converging, the amount you can move is bounded O of 1. And then this is O of 1 also. But then you can use this rescaling trick to make this L very small. And that's essentially the heart of every NTK proof. Okay, so let's look at the Jacobian-Lipschitz lemma. And this is straightforward. This is just a calculation. And I did the calculation here for two-layer networks. You can do it for any depth. It's just backpropagation. There's nothing deep here. So it's the infinity norm of the derivative x Kronecker x is 2 norm. The infinity norm of the A's, remember my network looks like this. So you can see that this is roughly like, that looks like the Hessian, right? Because if I took 2 derivatives of this with respect to W, I get something that looks like this on the blocks. And then the Jacobian is the derivative of the Jacobian, which is the Lipschitz, is just the Hessian. You can see this looks exactly like the norm of the Hessian, right? You have x Kronecker x, that's this A's here, and then, sorry, there's missing a prime here. And W minus W bar, because that's the movement. And this is a deterministic lemma, like I said, it just follows from backpropagation equations. And the rescaling trick is just to make these very small. In what is now called NTK parameterization, if you just set these to 1 over root m, it becomes very Lipschitz as m goes to infinity. And now the deeper result that allows you to do this with minimal overparameterization is this. Okay, so now you need to lower bound the minimum singular value of the Jacobian. And this needs randomness of the data. So we assume that the data is ID Gaussian and the number of neurons is bigger than the dimension. This is usually true in practice, especially when you're talking about overparameterization. So the Jacobian minimum singular value is D times the sigma min of the initial W0 times the A infinity norm. Okay. So if you can put this together, what this paper guarantees, this theorem guarantees, is that if you have Gaussian data, truly the minimal overparameterization, right? M times D is just the number of trainable parameters. It's like MD bigger than n log n or something, and M is bigger than D. You use any full rank initialization, you decrease the loss to 0. And of course, if you decrease the loss to 0, you found the global min. And the proof is just like the circular reasoning almost. You don't actually construct the global min anywhere. You just show the loss goes to 0 very fast because the sigma min is positive. And then because the sigma min is positive, WT stays near W0. And these together imply the existence of a global min near W0. The width we have is in fact sharp up to polylog factors. And fairly recently, Zhang and Montanari proved sort of the other direction here. When M is less than D and MD bigger than N, and W0 is random, they proved also a similar sigma min lemma, something similar to this. It's not exactly the same, but it suffices to get this theorem. So combining these, really, you can remove this condition here, that M bigger, if you combine it with their work here. But they need random initialization. So you, instead of full rank, you can just initialize W0 randomly, which is done in practice anyway. So sort of these two results combine really for 2-layer networks to give a very complete story under the minimal overparameterization, gradient descent with this NTK rescaling trick. converge decreases loss to 0, although it's non-convex. Okay. You can compare this older result actually to the more recent NTK paper, and you'll notice that the width is essentially it depends on n in the weakest way, right? It's linear in the width. It's actually it's sublinear. It's actually n over d. Compared to like the papers following, usually you would need m bigger than a polynomial of n, very large polynomials, at least n squared from what I remember. So it's kind of the way you gain here is because you were able to prove a bound on this Jacobian at W0, and you used a little bit more heavyweight random matrix theory compared to the more recent NTK papers, which kind of just use data separation conditions. So kind of you're leveraging here the Gaussian data. So also you note that sort of the optimization and the random matrix theory part is very separated. So any data set in which you can give a quantitative bound on sigma min, this theorem would apply. So I could equivalently change this theorem to if sigma min of Jacobian of theta 0 is bigger than something, then this holds true. So everything reduces to proving a lower bound on the minimum singular value of the Jacobian. So in fact, here we did not establish that the behavior is approximating the infinite width kernel. So we did not prove that the Jacobian is converging to the NTK kernel, which is defined to be like expectation sigma prime WX sigma prime W bar dot X. You're not converging to this quantity necessarily, and nor do you need this. This is something too stringent to desire if your only goal is to prove optimization results. And the finite width kernel in this linear regime is not close to the infinite width. There's no convergence in the operator norm, for example. If there were a convergence operator norm, you would have a minimum lower bound on the singular value just by Wales inequality. And that's what these more recent papers do. But then you would need at least m bigger than n squared or something to get operator norm convergence. And here it's key that to do a sublinear n, you really do need to leverage the fact that you can lower bound the Jacobian without proving a convergence of the kernel. Okay. So that's kind of what I wanted to say about linearization. And now I want to move on to a slightly different question to motivate why linearization is not enough for what we desire. So at the end of the day, we are concerned with statistical learning, not necessarily with optimization. Optimization was sort of just an intermediate challenge in achieving good learning, good statistical behavior in an efficient fashion. So now let's turn to the statistical question. This is kind of considered one of the most natural questions in deep learning theory. So take that you have a teacher network, let's say a 2-layer to be simple. And given data from this 2-layer network, I want to learn to accuracy epsilon. How many samples do I need and how much time do I need? So let's look at some potential results. So sort of here, the information theoretic sample complexity is n proportional to dr, which you can attain by brute force search. You essentially search over all A's and W's, throw down your epsilon net, compute the loss in the epsilon net, and keep the smallest one. And that will get you something like dr here. Of course, that's exponential time in both D and R. No one's ever going to use this algorithm. It's kind of just only for proof purposes, really. So a very, very, very good result, if you can do it computationally efficiently, would be like poly in D and R. Okay. So now let's look at a simple case. if the activation were a monomial or polynomial, you could do this with a polynomial kernel in d to the degree of the activation times some poly-r factors. And this is sort of what NTK would do. NTK's behavior essentially is the same as that of a polynomial kernel. It's not too much difference. Okay, but then let's look at what is known sort of from the lower bounds side of things. So there's a lot of lower bounds for discrete distributions. These results kind of rule out any algorithm that do not use distributional assumptions or assumptions on W star that learn in poly DR, and probably even like d to the little of r probably is even hard. I didn't check very carefully. Okay, so the reason these are hard is if you could solve this teacher network problem, even the two-layer one, you can do things like learning intersection of half spaces, decision trees, juntas, many things that for a long time the learning theory community and the TCS community have considered to be somewhat intractable problems. And more recently, in the last year or 2 years, last year I think, there's even lower bounds if P of X is isotropic. So based on statistical queries, Diaco-Nicholas and also another paper by Goel showed something like you need D to the R queries, right? So that's kind of saying the kernel, this is like kind of pretty terrible. Is like, you know, we wanted D to the R is something, yeah, it's something not very good. Of course, you know, we shouldn't be scared off by lower bounds as long as we have good solid algorithmic ideas. And in fact, there are known cases of where there are algorithms that can actually solve this teacher network problem in the two-layer case through parameter recovery. So they solve something harder than the learning problem. For example, spectral methods pioneered by this paper of Janzemin, Zhang et al., they can learn teacher networks if R is less than equal to D and the sigma min of W star is positive. So in these constructions, sigma min is very close to 0 in these lower bound constructions. And in fact, you can do this even with SGD. This was done in a paper by myself, Rong Ge and Tenyu Ma, and then in the orthogonal case by Yuanzi Li and Tenyu Ma. They show SGD can estimate parameters, but under even stronger assumptions. Like they need this plus some positivity on the coefficients. Okay, so sort of how can we go beyond this with methods that are computationally efficient and try to get statistical efficiency, but perhaps without sort of these condition number assumptions. And now let's turn to sort of a functional analysis viewpoint. This is very related to what Andrea discussed in his talk using LP norms. Let's look at two function spaces that are kind of quote unquote natural in this case, in the two-layer teacher net problem. You can define f star of x again as a teacher network, and we will write as an integral with respect to a measure rho. And then this rho will be just delta functions in the case that, so just delta at wj with aj outside in this case. So if I want to represent a finite teacher network, I just write it as a as an integral of Dirac delta functions, which is of course equivalent to just a sum of neurons. And the features, this is sort of the natural featureization if you have a two-layer network. But what's very, very important here is the norm in which you measure your rho, which give you different function spaces. There's two kind of what I would call natural spaces. The first one I will call F2 of B. It's a Hilbert space. It's in fact an RHS. And it's also an NTK. It's the NTK with respect to the last layer parameters, the A's. So that's I don't know who first discovered this, at least as old as Radford Neal, Rahimi Rak, Cho, and Sol, studied for at least 20 years now. So it's well known that you can have these kernels like that are loosely induced or motivated by neural nets, but their behavior is not like that of neural nets in terms of statistical or computational, really. The second one is F1 of B. It's a Banach space. It's sometimes called convex neural nets, proposed by Bengio, Bach later studies. Many authors have studied this. And F1 of B is kind of nice because if you believe your teacher network is kind of small, then L1 norms give sparsity. And that's kind of why you would kind of think that F1 of B may have better statistical properties. And this would be correct. So the global, if you use weight decay on a two-layer network, in fact, the global minimum of the loss plus weight decay is given by F1, is the minimum F1 norm solution. Sort of mean field approaches are naturally lie around F1, and a lot of the work on implicit regularization by myself, Shizat Bach, Kai-Feng Liu, Colin Wei, all of this is sort of looking at F1 and its sort of statistical properties. So why do we like F1? If you are a statistician that doesn't care about computation, F1 has all of the magical properties you would desire. The sample size is proportional to the F1 norm squared over epsilon squared. And the F1 norm is adaptive to lower dimensional structure. Meaning if f star of x were some polynomial of ux and u just chooses r of the coordinates or r dimensional subspace, and this p is degree q, you only pay exponential in r to the q, right? You don't pay d to the q. A kernel method would pay d to the q. It just essentially ignores the fact that it's low dimensional. Even better, if you had a ReLU teacher net or sigmoid teacher net, it doesn't really matter. The sample complexity is d poly r for a reasonably small polynomial, like r squared or something. And this is easy to find by like Rademacher complexity. Okay. However, if you're concerned with computation like me, then you know this F1 space is really a red herring, a distraction. F1 almost certainly cannot be efficiently learned since it includes all two-layer teacher networks with R. So sort of all of the previous lower bounds apply to F1. And sort of thinking in this abstract functional analysis viewpoint or mean field viewpoint is very hard to leverage any data structure either in P of X or Y condition on X. So it's kind of unlikely that mean field or any SGD approach really, or any algorithm really, will yield polynomial time learning for all of F1. So now let's turn to F2. F2 is great if you like computation. It can be learned via SGD. It's a kernel method. It can be learned by matrix inversion since it's a kernel method. However, it has terrible, terrible statistical properties. It completely ignores low dimensional structure. Just as an example, if you depend only on one coordinate, like the function W or U sorry, what's my notation here? U transpose X to the qth power would need you D to the Q samples instead of D samples. Okay, this is terrible. F1 needed D samples, you pay D to the Q, although you only depend on one direction. Like a teacher network with a single ReLU has something like exponential, actually probably infinite F2 norm. But if you truncate, willing to tolerate some inaccuracy, it's something like exponential D over epsilon squared. And your sample complexity, the best result really I know of is something like D to the 1 over epsilon to some power. And as far as statistical results go, F2 and NTK all behave similarly. All of my comments here apply to NTK also. is that NTK sort of just ignore low dimensional structure. Okay, so the goal you really want to do is try to find the sweet spot. You want to find an in-between space that adapts to low dimensional structure and is computationally efficient, preferably via SGD. So, the obvious guess when I thought about this a year or two ago is LP norms. And Andrea luckily discussed it this morning, and as he told us, it's very, very hard to use random features plus LP regression on top of the random features for p equals 1. Like, you would need an exponential number of random features to get close to 1. And LP for like p equal 1.1 for some constant p, like you really need p equals like 1 plus 1 over d or something to get the statistical properties of the L1 norm. But this would be you would need exponential and d random features. So something like L1.1 would not get any of these low dimensional benefits of F1 I talked about. So kind of, I think this is the natural thing that the first thing anyone would think of is to look at LP. But as far as I can tell, it won't lead to tractable algorithms. So let's turn instead to a different motivation. Things we do, we should always, if you're looking at computation, you should always look at things that we know how to solve and build on top of those, instead of starting with like abstract function spaces. So let's look at what we do know how to learn very well. Quadratic activations. Okay, so quadratic activations, you can write again as this in this integral form to make an analogy. F2 then gives you a Frobenius norm inductive bias. F1 gives you a nuclear norm inductive bias. This is very good. Okay, this is everything we know about low rank, low dimensional. This is kind of bad. Okay, luckily, the reason I wanted to start with quadratic activation is, in fact, in this special case, F1 is learnable. So it kind of suggests that rank is a reasonable measure of low dimensional latent structure. And if you have monomial activations, the rank of the tensor does exactly correspond to the width of the network. So I will define this function class I call low rank polynomials. And this is the definition. You can think of it, it's like teacher network where all of the activations are monomials or polynomials with normalizations to make everything make sense. Okay, so this is an interesting class because you include teacher networks with polynomial activation of bounded degree, even analytic degree approximately. You can truncate analytic activations to log 1 over epsilon degree. Constant depth teacher networks with polynomial activation. It blows up exponentially in the depth, but as long as the depth is constant, it's still in this class with polynomial R. And the real reason is I can show you a non-trivial learning guarantee with SGD that's not attainable via kernel methods. Or in fact, not attainable except without pretty sophisticated methods. So let's look at what our baseline approaches do. F2 needs d to the p samples. They kind of just, this is the same thing with all kernels. They just ignore low dimensional structure. And you just get d to the power of the poly degree. F1 is d to the poly r. It's essentially optimal. Of course, the issue is it's exponential time. We don't know how to learn this efficiently. And one of my earlier works with U-Bai, you can learn this with a very, very modest improvement over the kernel. D to the p improves to d to the p minus 1. Okay, so a tiny, tiny improvement, but at least it shows that you can, you can beat d to the p with a computationally efficient algorithm also. So of course, there's still a huge gap here, right? This is the gap here. There's a lot to close here. And in fact, what I will show you today is SGD plus sign dropout. So I need to modify SGD a little bit on a 3-layer architecture, learns with n to the d to the p over 2. Sorry, this polynomial width, the width is actually d to the p over 2. So I need d to the p over 2 samples, and in time n poly d r p 1 over epsilon in M. Okay. And the data assumptions are mildish. There's some moment assumptions you need. Things like you essentially need like, how to say this? Like the moments of X tensor P over 2 behave like those of a Gaussian or any multivariate Gaussian. So any multivariate Gaussian with any covariance of bounded condition number, elliptical distributions on spheres, these are all fine. But it's not just tail assumptions. You do need things about the shape, the moments up to a pretty high degree. Okay. So the architecture. So then the running time, essentially, you should think the sample complexity is d to the p over 2. The width is d to the p over 2, and the running time is linear in the n. Actually, it's linear in the n, linear in the m, and polynomial in the other things. Okay. So what is the architecture? And then in analogy to Daniel's talk, you should think, okay, this d to the p over 2 should really remind you of his complexity results about learning tensors of order p, and they also need d to the p over 2. And that's kind of what's happening here under the hood, is that this 3-layer neural net architecture is simulating matricization, which is one of the techniques Daniel discussed. One of the simplest ways to learn an order p tensor with d to the p over 2 samples is to reshape it into a matrix of d to the p over 2 by d to the p over 2, and then do something like an SVD. So that's for like tensor decomposition or tensor completion. Our problem, very, very loosely, is kind of like tensor sensing. And that's kind of what's happening under the hood, is that we're going to use a 3-layer network that's implicitly doing a form of matricization. At least in the proof, we're using matricization. So we will only train WR, and we'll fix the ARs, A's and B's at random initialization. You can train them, but we don't know how to prove training them helps. But we do need them at random initialization. There's a lower bound if you only have a 2-layer network. Although it's not a very strong lower bound, so I won't even discuss it. But as far as I know, a 3-layer network is essential. You want to build a sort of a quadratic random feature set on top of a ReLU random feature set. So what is the algorithm? Algorithm is, first you want to estimate the covariance of the random features from the first layer. That's these G's. You form this sigma hat. You use the sigma hat as a weighted regularizer. This is some weird norm. It's not very important. The point is, it needs to be something like close to a 2 infinity norm, which is like every row cannot be too big. And that's for proof purposes. If you prefer, you can think of it as Frobenius norm, and morally it's still true. And then you run SGD with a modification of dropout is, instead of 0, 1, use plus minus 1. This prevents anti-K behavior from happening and lets you use much bigger learning rates. So kind of the reason this works is that, let me sketch the reason it works. If I knew the input were Gaussian, and I choose the G's to be Hermit polynomials instead of ReLUs, this makes the proof very easy to see, very intuitive if you think of Hermit polynomials. If you initialize this many Hermit polynomials, you can get a basis of degree p over 2 polynomials. Then you can express any beta dot x to p over 2 as linear in the Hermits. And then these go into the next layer, the final hidden layer. And the final hidden layer is going to do something simple. It's going to just learn to square these guys, which you should think of as quadratic activations. So sort of the one thing we know, the one thing that universally we know how to do computationally efficiently and statistically efficiently is quadratic activations, matrix sensing. And this needs almost no assumptions on data. So we're very, very good at learning quadratic activations of the input, even with random feature, like a random featureized version of matrix sensing. So you can think of this as random features, but now it's not RKHS, it's sort of a nuclear norm random features. And that allows you to get statistical benefits. And this allows you to be universal. So you don't need, like, the problem with just matrices is that you're not universal. You can only learn degree 2. Now you're universal. You've learned to square Hermite polynomials of degree p over 2. So that lets you learn anything of degree p. So that lets you learn anything of this form. And if you have multiple of these, you just use a different neuron to do this. So that lets you learn anything of this form here. Oops, this should be R. And that's essentially how this works, is that in the first hidden layer, you try to mimic a basis of Hermite polynomials if it were Gaussian. And then the second layer learns to square them. Sort of in the non-Gaussian case, you just learn something like an approximate basis of degree p over 2. I don't know what the basis is. If it's not Gaussian, it doesn't matter. It's approximately a basis. And then the second layer, I learned how to square it, but then the squaring is very statistically efficient. So there's several potential improvements. Something that I think is probably within reach is if you train the first hidden layer, the V's, you can improve the epsilon dependence by sort of a fine-tuning, like a feature learning argument. Because right now you're paying an extra 1 over epsilon squared is because you're only epsilon approximating. The hope is, like, if you fine-tune it, you can get rid of these epsilons. Although even this, I think, is technically not that easy. Anyway, it's not a very big improvement. The bigger question, is poly D possible? And we already heard from Daniel that there's very likely it's not possible. That D to P over 2 is kind of, for many reasons, is a fundamental limit in tensor completion and sensing. And our family of low-rank polynomials includes tensor completion, tensor sensing. SOS can only get D to the P over 2. Daniel showed some unconditional lower bounds today that indicate D to the P over 2. Okay, so of course, never be deterred by lower bounds. It just means we need better assumptions. Let's move on to hierarchical models. For example, deeper things. Low rank polynomials are very good for constant depth or depth 2. Perhaps we can learn things where we chain together low rank polynomials and then their functions of them. So this would be very nice because then you can start to talk about deep networks. And here's like sort of perhaps one that might be easier, like a ResNet-ish form of it. And this you might think is easier because you have some direct signal from the feature map. I still don't know how to prove this, but it seems maybe plausible. And sort of the big picture questions is trying to attain a systematic understanding of what is computationally possible via SGD. Like, what are the things we can learn beyond kernel methods? Right now, it's fairly limited. Like I said, the only thing that's really general and completely agnostic to data assumptions is sort of these quadratic NTKs, which we exploited with a 3-layer architecture. But what else can we exploit? And then what are the things that can use assumptions on Y conditional on X and assumptions on P of X? Really, P of X assumptions are not heavily used in any SGD analysis that I know of. Y conditional X are sometimes used in these category 3 proofs, but they're pretty fragile. You need pretty specific data assumptions. And how will these interact with architecture, algorithm, regularization? How will this interact to learn good representations, not only classification? So the big win in deep learning is not just classifying well with samples, it's that by classifying well, it also learns good representations. We have a pretty good understanding now statistically how this happens, but we have virtually no work on learning good representations beyond the linear case. That's sort of all I wanted to say. Thank you for listening.
Thank you very much for a very nice talk. Any question from the audience? Please feel free to unmute yourself or raise your hand. Jason, can I ask you a question about the
yes.
the linearization? Where you mentioned that you in your early work you require that the width is sublinear in terms of data samples, and in the NTK papers they require like at least quadratic, right?
Yeah, it's quadratic. I think the best you can do is quadratic.
Yeah. So could you explain the intuition why you can get better rate like sublinear?
Yeah, it's because in the NTK papers we took kind of a little bit of a not intelligent route to do this at some level. Is what kind of the argument, if you look at my papers as Simon Do, for example, is we had the Jacobian, I'll just use Jacobian. We use Jacobian transpose Jacobian. The infinite width one and then the finite width one. And we kind of just proved that this is small. Something. But to get operator norm convergence, I think you need at least superlinearity. I don't actually know. I think Andrea knows, but I think if it's not, I think it's at least n squared. It's definitely not linear. Like I know for a fact if it's m equal n over d, it's not true. You don't get operator norm convergence. So sort of the early papers here, they just use something like a matrix Bernstein, matrix Hufting, and you get some n to some c over root m. So you got something like this. And then once you get this, you know this is positive. The sigma min of this guy is positive. And then you just, so then sigma min by Weyls inequality, this is bigger than this guy minus nc over root m. So you kind of combine these two and you get something like poly n. And that's essentially what all of the NTK papers do.
Yeah.
Is sort of, they kind of avoid doing random matrix theory because now all you need to do is matrix Bernstein. You don't need to, the harder thing, the thing you should have done is directly analyze this minimum singular value, which is much harder.
Yeah. So
of course, you need Gaussian, you need data assumptions. Like Gaussian's not necessary, but like you definitely need something like, very high moments look like Gaussian. Like something you need something like the convex Lipschitz concentration to apply. That's sort of like the main thing you need.
Yeah. Can I ask another follow-up question about in this direction? So in the literature, do you know any paper studying the propagation of this Gaussian randomness around the iteration? Because the Gaussian randomness is the crucial assumption in proving the sigma mean is positive. And I think the key to prove global convergence is to prove that the sigma mean is always positive, as you mentioned in your talk. So is it possible to analyze propagation of the randomness around the iteration to prove that without linearization, or we can prove that sigma mean is positive?
Not that I know of. The only way I know is to prove that you don't move a lot from the initialization.
So how you move is still unknown.
Yeah, like for example, if you train this, let's say you add regularization, like weight decay, then you would move a lot, or you use logistic loss, so you would move a lot. And then how does sigma min of the Jacobian change? I have no idea. That, like, if you could prove a lower bound, you could basically, is this true? Sorry, let me think. If you could always guarantee to me sigma min of J is positive everywhere, or everywhere gradient descent went, or SGD went, yes, then you could solve all of the F1 things. Yeah, that's true. That's something we proved in a paper with Colin Way and Ting. Yeah, so like it's probably impossible. Like you would need, I don't know what you would need. You would have to be data assumptions.
Sure.
But sort of it's very hard to see data assumptions at this abstraction level. So it's probably not the right way to go about it.
I see. Thanks.
Yeah.
Any more questions from the audience? So if we don't have more questions, let's thank Jason again. So I think this is the end for afternoon section. In the evening, starting at 7 p.m. EDT, we will have contributed talks later. So welcome back. Thank you.
Thanks, Saijao, and thanks to all of our speakers today. It's been a great
Thank
day.
you. Bye-bye. Yeah, see you at the 7.
Bye.
Bye. Okay, hello everyone. So welcome back to the contributed talks. So our first speaker is Mojo from Duke University, and he gonna talk about towards neural network approaches for high-dimensional problems. So Mo, can you unmute and also share screen? Yeah, let's do a test. So make sure it works for you.
Can you hear me and see my screen?
Yeah, looks good. Looks good. Okay.
Okay.
Yeah.
Then shall I just wait for a few minutes?
Yeah, let's wait. Yeah, let's wait a few minutes. And also, let me try. Where's the third speaker? Let's make sure that all the speaker can do a test. So Haizhao, how about your student Shenwei do a test to check whether his slides works well on the sharing?
Do I need to stop sharing?
Yeah. More you can stop sharing. Let's do a quick test for everybody, so that to make sure we don't have surprise.
Can you see the screen?
Yeah, good. Yeah, some of it works. So you can, yeah. Ichi, are you there?
Probably too early for him.
Too early for him? Okay.
He's in China.
Okay. Yeah, too early. Yeah. Okay. All right. Let's wait a little bit then. Okay. So Mo, you can share screen now.
Okay.
Yeah. Okay.
And
yeah, let's wait a few seconds.
Sure.
You should start very soon. Okay, well, you can start now. Yeah, thank you.
Okay. Thanks everyone for coming. Today I'll talk about the neural network approaches for high-dimensional problems, and this is joint work with my advisor, Professor Jianfeng Lu, and also with Jiechun Han. And my short talk composed of an introduction part and two of my works, solving the eigenvalue problems and solving the HJB equations and some future directions. Firstly, the introduction part. We do have some requirement to solve the high-dimensional problems in practice. For example, the Schrödinger equation in the quantum many-body problems, the Hamilton-Jacobi-Bellman equation in the optimal control problems, and also the nonlinear Black-Scholes equations for derivative prices. And all of them suffer from the curse of dimensionality, which means that the computational cost will go up exponentially with respect to the dimensionality. And there has been some methods to alleviate this curse of dimensionality, such as the tensor decomposition method. But obviously, the most widely applied method is the neural network approaches. So here I have a brief summary of the common neural network approaches for high-dimensional problems. The first one is the least square formulation. That is when we are solving an equation in LU minus F, we just use LU minus F norm square integration as a loss function, and then parameterize this function U as a neural network and directly compute its derivative. And in some special cases, it is called the physics-informed neural network. And the second common method is called the deep risk method, where we use the variational formulation to minimize such a energy functional. And the third one is the weak formulation, where we introduce auxiliary function and make it in the weak form. And in this way, we make it an infinite problem. So it is a very good structure for the adversarial neural network. And finally is the deep SDE method. And actually both of my works are based on this method. That is when we are trying to solve a parabolic PDE, what we do is that we first define an SDE with the drift coefficient B and the diffusion coefficient sigma, so that the generator of the SDE is exactly this differential operator, 1/2 sigma sigma transpose Hessian of U plus gradient U inner product with B. And then we define another process y of t, which equals to U of t xt, where this U is the solution of the PDE. And then if we apply Ito's lemma and the PDE relationship, we will be able to obtain an SDE for this YT. And the loss function is constructed by matching YT, which comes from this equation 2, and G of X capital T, where G is the terminal condition of the parabolic PDE. And we will use 2 neural networks to parameterize this U and the gradient U. And this is the summary for the BSD method. And next, I will introduce my works. Firstly is to solve the eigenvalue problems. And the problem we are considering is to obtain an eigenpair lambda and psi such that L psi equals to lambda psi. L is such a differential operator. And for simplicity, we consider the periodic boundary condition. And what we do is that we construct a parabolic PDE with some certain terminal condition. And the equation is partial T of U minus LU plus lambda U equals to 0. And of course, the solution of this parabolic PDE forms a semigroup. And this is denoted by P lambda T. And we can find that if lambda and psi is a true eigenpair of this operator, then L of psi minus lambda psi will equal to 0, which means that the PDE will be static. And that motivates us to construct a loss function of P lambda T psi minus psi. And we minimize this loss function in order to solve the eigenvalue problem. And one remark is that this method is in the same spirit of diffusion Monte Carlo approach, but there are some difference. In the diffusion Monte Carlo, what we do is that we let capital T to be long enough so that whenever you start, finally it will converge to the ground state. However, what we do is that we fix the capital T and try to match the initial condition and the propagated situation. Therefore, our method is not only able to solve the ground state, but also able to solve the excited states. Okay, and maybe let us have a look at some details. We define SDE xt, and then we can use Ito's formula and the PD relationship to derive an SDE for U of t xt. And then we use 2 neural networks to approximate the eigenfunction and its skewed gradient. And we construct the loss function as mentioned by matching the neural network evaluated at xt and the U of txt obtained from this equation 3. And as for the numerical implementation, we use Euler-Maruyama scheme to discretize the process. And for the neural network structure, since we are considering the periodic boundary condition, we first map the input into a trigonometric basis and then put it into a deep, fully connected neural networks with ReLU as the activation function. And before going to the numerical result, there is a small technical detail I want to mention. That is, if you look at the loss function, we can see that a trivial solution is if you let everything is equals to 0. And in order to avoid that trivial solution, we introduce a normalization factor Z, and we divide the neural network by this factor so that we can avoid the trivial solution. And next is the numerical examples. We have a linear Fokker-Planck operator, a linear Schrödinger operator, and a nonlinear Schrödinger operator. Yes, this is the numerical result. On the top, it is a histogram of the function of the eigenfunction in high dimension, and the black line is the histogram of the true eigenfunction, and the blue dashed line is neural network approximation. We can see that it fits quite well. And on the bottom, it is the learning curve. We can see that And we use the L2 arrow to measure the error of the eigenfunction. And it also learns with a high accuracy. And in addition, we also have a linear Schrodinger operator and a nonlinear Schrodinger operator. And I didn't include the solution for the second eigenpair here. If you are interested, you can look at the paper in Journal of Computational Physics. And here's a summary of the deep eigensolver. Firstly, we reformulate the eigenvalue problem as a fixed point problem for the parabolic PDE. And then we borrow the model from this deep BSD method and then make it a control problem. After that, we discretize with Euler-Maruyama scheme and parameterize the function and its gradient with periodic neural networks. And we also make a normalization process to avoid the trivial solution. Finally, we minimize the residual of the fixed point problem using the Adam method. Okay, this is the deep eigensolver. Is there any question for this one? Okay, then I'll move on to the next one. The next one, I want to solve the Hamilton-Jacobi-Bellman equation. And the equation looks like this. There's an infimum over U of a linear operator. So it is fully nonlinear. And actually, this Hamilton-Jacobi-Bellman equation comes from the optimal control problem. And in order to state that, we first define an SDXT with both drift term B and the diffusion coefficient sigma depend on a control process U. And since we are considering a time static HJB equation with a boundary condition, we define a stopping time tau, which is the first exiting time of xt out of omega. And in the optimal control problem, we care about a cost functional, which is the expectation of the integration of a running cost f plus a terminal cost g. And there's a discount factor e to the negative gamma s, which means that the future cost is, the current cost is matters more than the future cost. And what we want to do is to find a process US in order to minimize this cost functional. And the minimized value is defined, or the optimal value is defined as the optimal value function v of x. And here, this x is the initial condition of the SDE. Okay. And according to the optimal control theory, this value function is exactly the solution of the HJB equation. Therefore, in order to solve the HJB equation, we only need to solve an optimal control problem. And in order to solve that, we leverage the actor-critic method from reinforcement learning. And basically, it just means that we do two steps consecutively. The actor refers to the control. That is to say, we do a policy improvement process in order to obtain a better control function to reduce the cost functional. And the critic refers to the value function. It means that we fix the control function and do a policy evaluation process to compute the value function for the given control. And let us have a look at some details. Firstly is the policy evaluation for the critic. That is to say, we fix the control function U, and then the corresponding value function is given by the expectation of the running cost plus terminal cost. It is exactly the cost function here, but now we do not have an infimum because the control function is fixed. And we can show that v of x satisfies an SDE like this. And then what we do is that we define two versions of temporal difference. The concept of temporal difference also comes from reinforcement learning, and it matches the discrepancy between a current estimate of the value function from a from a sample, and therefore, this first temporal difference is just the right-hand side of this equation minus the left-hand side of this equation. Therefore, if v is the true value function, then this TD1 should be 0. And TD2 is just that we remove this martingale term, and we get TD2. Therefore, if v is the true function, then this TD2, the second temporal difference, will have an expectation of 0. And this second temporal difference is a direct analog of the temporal difference in the discrete reinforcement learning setting. And minimizing the square of this temporal difference 2 is a common least square temporal difference that is widely used in reinforcement learning. And as for this first TD1, since v being the true value function results in a 0 TD1, we would expect that in the training process, such a temporal difference will give us a smaller variance during the training. So we name this the variance reduced version of temporal difference. And later, we will have numerical results to compare this to. And this is the critic. And as for the actor, we do a policy improvement. That is, we change the policy in order to reduce the cost functional. And what we do is simple. We first write down the cost functional, and then do a gradient descent method. And this is called policy gradient, also very common in reinforcement learning setting. Okay, and as for the numerical implementation, we use 3 neural networks to parameterize the value function, its gradient, and the control function using a fully connected neural network. And then we have 2 loss functions, one for the critic, one for the actor. And in the training or in the optimization process, we just consecutively update the parameters for the first and the second loss function. Therefore, this actor critic method is kind of an alternative direction multiplier method. And by the way, since there's a boundary condition, we also enforce another loss at the boundary to enforce the boundary condition. Yes. And for the numerical discretization, again, we use Euler-Maruyama scheme to discretize the process. And since there is a boundary, we figure out that in the numerical training, instead of using a naive scheme, which means that we use a constant step size delta t, it is beneficial if we use an adaptive step size, which means that the step size gets smaller when the trajectory of xt is closer to the boundary. This means that at the boundary, we are getting more accurate. And such an idea comes from this paper by Bushman. And later, we will also have numerical results to compare the 2 schemes. And yes, here is the numerical results. On the top, there are 2 figures, and the orange line denotes the true control function. Everything is in high dimension. I just shrink it into 1 dimension. And the blue dots are the control computed using the naive scheme. And on the right, the blue dots is the control computed by the adaptive scheme. And we can see that on the right, it is much more accurate. So the adaptive scheme is much more accurate than the naive scheme. And also on the bottom, there's a table comparing both different schemes and different versions of temporal difference. We can see that the variance reduced version of temporal difference, which is the TD1 I mentioned before, gives us the smallest error. With TD1, the variance reduced version of temporal difference, and the adaptive step size gives us the smallest error. Okay, and this example is called the linear quadratic regulator, which is the most common example in the optimal control problem. And next, I'll show some more numerical results. And again, on the top, it is the density of the function. On the left, it is 5 dimension. In the middle, it is 10 dimension. On the right, it is 20 dimensions. And on the above, it is the histogram comparison. On the bottom, it is the learning curve. We can see that the arrow is quite small. And we also have similar results on stochastic van der Pol oscillator example and a diffusive Eckno equation example. Okay. And then here is a brief summary for the deep actocratic HJB solver. We first reform. Do you have a question? Or okay. We first reformulate the HJB equation as a stochastic control problem, and then we borrow the actocratic model from the reinforcement learning to derive its continuous analog, and then discretize using Euler-Maruyama scheme and parameterize it by neural network, and use the adaptive scheme to improve the accuracy, and finally solve this ADMM-like optimization problem. And that's all. Here are some future directions that I may want to do. And thanks for listening. Is there any question?
Okay, yeah, thank you, Mo. Any questions? We have time for a quick question.
Can I ask a quick question?
Yeah.
In the first part, if you reformulate the problem to SDE and get some loss function, have you compared the method like the physics informed neural network? A very straightforward strong form residual minimization problem.
Unfortunately, we didn't do that. But if we use physics informed neural network, it means that at least we need to compute the second order derivative. And I think the most advantage of our method is that we do not need to compute the derivative of the neural network with respect to the input.
I see. Thanks.
Okay, yeah. So yeah, you can
stop
sharing. So let's move to the second talk. The second talk is by Guozhi Dong from Humboldt University of Berlin. And his talk title is Optimization with Learning from the PDE Constraints. So he sent us his video. So let me try to share with you. So let me see. Okay. Let me see. So let me optimize it. Let me play it.
Hey, everyone. I'm Guozhi Dong from Humboldt University of Berlin. I'm very happy to have the opportunity to present some recent works in this very interesting workshop. First of all, let me thank the organizers for the organization of the workshop, and in particular for giving me the opportunity to present the recording of the talk instead of a talk magnet. Therefore, I might not be able to answer your questions after my talk. However, I will give my email address so that if you are interested in my talk, please feel free to drop me emails if you have questions. I'm very happy to discuss with you. Okay, so this is the joint work with Michael Henry Kostas Papathistouros. Michael is a professor at Humboldt University. He's also the director of the Biostress Institute, and Kostas is a postdoc at the Biostress Institute. So in this project, we study a general optimization framework subject to some learning from differential equation constraints. So in this talk, I first introduce you this general framework, and subsequently I will give 2 concrete examples which also motivate our study. Okay, so the optimization problem we're going to study is actually summarized in this group box on the right hand side. So here are the objectives. You see, it consists of two components. The first one is a kind of data fitting term, which are quite standard in numerous problems or in imaging problems. And the second one is again quite standard, so it's kind of typical of regularization. So the parameter y and u are the components, and d are the measurements, and a is a linear operator. So the y and u are connected through an operator equation. So y equals pi n u. So the pi n is a learning informed operator, which corresponding to the type. And u itself might have some additional constant, since u is some physical parameters. So usually it has some uniform bounds on the quantity or on the magnitude. And this type of learning informed operator is intended to approximate some underlying physics models, which we call it y equals pi u. However, this pi u might not be known to us, or only partially known. So this is because it is characterized some physics process, and for this physics process, you only have some observation where you give some input, you observe these output pairs. So the input and output pairs are known. So the idea is to learn this underlying physical operator pi using some learning informed techniques, for instance, artificial neural networks. And we have some application in mind. So here there is a phase separation, and another one is a quantitative magnetic resonance imaging, where both have this type of properties. I will come to the examples later on. So before I introduce the general framework in more detail, since I already mentioned there is a learning informed operator involved, so I try to somehow review the current state of artificial neural networks. So from the functional or function approximation point of view, since I'm still quite new to this field, so this summarization here might be quite biased. Okay, so I consider a map to be classified in 4 categories. The first one, we can consider a map between finite dimensional space. And this has been well understood in the literature for artificial neural networks. So in particular, if the domain is bounded, and we have this universal approximation theory, which says this f, a continuous function f, basically, can be well approximated by artificial neural networks. And there are applications, for instance, the standard regression in statistics. So the second category, so F then is a map between infinite dimensional space and finite dimensional space. So for instance, you can think of this image classification, where the image can be considered an object in some infinite dimensional space if the image is a continuous function, for instance. And you try to classify the images. For instance, try to classify dog, cats. Therefore, map it to some real networks. So currently a very well developed tool for this is like convolutional neural networks, which can do tremendously good work for classify images. However, the storage part for instance, universal approximation type property still largely open. And the third class I would like to mention, which is also kind of complicated, to use neural networks as ansatz for the solution of differential equations. In this case, F will be a map from some bounded domain in Euclidean space to infinite dimensional space. So F is an object in some function space, where the function space has a solution space of the PDE. And there are many methods proposed. However, I would consider which is open is the theoretical understanding, where, for instance, the convergence, right, or even the universal approximation type theorem still cannot be directly applied in many of the cases for PDE solutions. And for the fourth category, as I already mentioned in the previous slide, it's kind of operator learning. So here is a map between infinite dimension space. So this is even less concerned in comparison to the problems in the first three categories. So the main difficulty is because of the lack of compactness, which makes the theoretical understanding and also the algorithm development fundamentally difficult. Okay, so let's come back to our general optimization problem. So here, I consider the operator equation to be implicitly characterized by some partial differential equations or system of differential equations. To assume that this equation is well posed. In that case, we have the prior understanding of the PDEs. So given the input U here, we should be able to find a unique Y. And in this sense, we call this map well posed. And we can come up with this solution map of this PDE or ODE. Okay. Based on that, we are interested in find some neural network approximation of this solution operator type. However, as I already mentioned, this task is fundamentally difficult. So it might be for a specific problem, we need to find a specific method also. So in general, I guess there shall be no universal method for the operator problem. The fundamental questions we can ask here, from the theoretical point of view, I can summarize the three problems here. And the first one is the well-posedness of the learning from operators or the learning from PDEs. So how about the existence, the uniqueness, and stability of the solution? After this is well established, we can ask whether there exists a universal approximation property of this learning from operator pi n to the original solution map pi. And Further, we can ask how about the approximation of the optimizers of the two optimization products. So one is very informed optimization problem, and the other is the original. Are the optimizers close to each other? And what about error bound? So in this project, we can actually have answered these three questions to some extent. Of course, based on some assumptions. And because of time constraints, I will not present the details of the results. Instead, I gave you two concrete examples. So the first one, approximation, is open control of some semi-linear elliptic PD. So here you remember we have this E, Y, and U equals 0, which are now replaced by this concrete PD here, where the feature is that it characterizes some physics process, since the diffusion usually can be observed, and then we can put the rest as some nonlinear map, which is a kind of a modeling process. And what we are interested in is actually the solution map, right? So we try to give a U, we try to find the Y. So the goal is to learn the solution map for this type of PD. And how to learn it? We really found that this task actually is not so trivial. So the idea for us is that instead of learning the solution map itself, try to focus on the nonlinear path. Try to replace this F by some learning informed operators or by some neural network operators. Okay? So the idea is that we use some neural network function to represent or to approximate this nonlinear map F through this relationship. Okay, so this is a non-trivial task, and I will not explain in detail here, but if you are interested, please feel free to drop me an email. We can discuss in details. So after we have learned this, we insert this A into the PDE, and we can, of course, establish the hypothesis and also the differentiability of the solution maps and so on. Then after that has been established, we can then prove some universal approximation property for the solution map of the learning from the PD and the original PD. So given F satisfies some assumptions, and actually using the universal approximation theorem for the map in finite dimensional space for bounded domains, we can actually have this result immediately. And based on this approximation, we are able to prove that the solution operators are also satisfy some universal approximation. So this say is kind of independent of this epsilon, but it depends on the bounds of the say deep here. Okay. And even further, we can prove the directional derivative of these solution operators, the universal approximation property. Basically, the P is some directional derivative of this pi m up to some direction, and this P epsilon is the directional derivative of this pi m up to the same direction, of course. And we can prove this type of estimates given this has been can be guaranteed again by the universal approximation served in finite dimensional space. Okay, so this is what we can prove for this type of problems. And instead of doing too much details to the numerical algorithms, I just here gave you some visual comparison of the learning informed solutions of the learning informed optimization problem, and this is the original sense way we cook up some examples. So here it's an uncanny equation. We set it as a benchmark example, and we use learning from models to approximate, which shows that the error somehow matched to what we can show in our field. Okay. And in the second example, we consider this quantitative magnetic resonance imaging. So here the model is called Bloch equation. So this is the UIU equal 0. And the interesting quantity is this rho, which is the density, the photon density, and T1, T2 are called exit times. So we are interested in reconstructing these three parameters, which I summarize as U here. Okay, so the F is like the Fourier transform, and the P is a subsampling operator. So we try to see how learning informed operator can help this task. So you can see that this PD, this OD actually, the Bloch equation has no spatial derivative. Can be significantly simplified if you introduce this learning informed operator. So you can directly learn this map from U to Y if you have some data pairs available. And this is then, based on that, we can again show the approximation property of the learning informed operators. So this turns out to be quite standard in comparison to the one for PD. Okay, and again, I can show you.
Okay, let me stop sharing. This is the end of his talk. So yeah, okay. So okay, so since let me see. Okay, so let's since he's not here, let's stop this talk. Let's move on to the next. Okay, so Sunwei, right? So the next speaker is Sunwei. Sunwei, can you share screen? Yep. Okay. So the next speaker is Sunwei Liang from Purdue. He will talk about solving PDEs and known manifolds with machine learning. Yeah, Sunwei, you can start now.
Hello everyone. My name is Sunwei Liang from Purdue University. Today my topic is solving PDEs on unknown manifolds with machine learning. This is joint work with Professor Si Xiaojiang from Shanghai Tech University and Professor John Harlin from Penn State University and Professor Haizhao Yang from Purdue University. Solving PDEs on unknown manifolds embedded in high-dimensional ambient space is a challenging computational problem that commands a wide variety of applications. For example, in physics and biology, such problems arise in modeling the granular flows, liquid crystal, and biomembranes. Also, in computer graphics, PDEs on surface has been used to restore the damaged patterns on the surface and brain imaging. Many methods has proposed for solving the PDE on surface, but most of them are limited to solving the PDE on surface of not very high dimension, for example, only in dimension R3. They typically parameterize the unknown manifold and use the tangential derivative to solve the PDE. For example, the finite element method that represent the surface using the triangular meshes. And some method will estimate the embedded function of the surface, such as level set representation or the closest point representation. Also, some method will use the weighted-based function method to solve the PDE on a non-manifold. The key issue with this approach is that when solving the PDE on the surface of high-dimensional ambient space, the computational cost may not be feasible. Also, it has been pointed out in some papers that some approaches may not be robust, and also the convergence near the boundary can be problematic. Now, let me introduce a diffusion mapping-based PDE solver on unknown manifolds. The unsupervised learning method called the diffusion mapping algorithm was proposed to directly solve the second-order elliptic PDE on the point count data. They approximate the differential operator with local kernel integral. The main advantage of diffusion mapping-based solver is that it avoids the tedious parameterization of submanifolds in the high-dimensional space. However, the estimate solution is represented by the discrete vector. Similar to the finite difference method, we can only get the solution on the given points. However, if we want to load the estimate solution on the new points other than the given data point count, we use some interpolation method to estimate the solution from the solution we obtained already. However, if the unknown manifold is very complicated, it's not easy to do the interpolation on the new points. Also, another problem of the diffusion mapping is that the size of the metric approximating the differential operator increase as a function of data size. So it means it will create a computational bottleneck if the PD solution involves the inversion of the eigen decomposition. And when I introduce the diffusion mapping officially later, we will see this problem again. One possible way to mitigate this limitation of diffusion mapping is the use of neutral networks. In recent years, we have witnessed the success of application of neutral network in scientific computing. It has been pointed out in many papers that diffusion mapping have good approximation properties, and it can lessen the curse of dimensionality. Also, there have been wide application of neutral network in high-dimensional PDE on the Euclidean domain. They typically will formulate the PDE problem as a regression problem, and the PDE solution is parameterized by the neutral network. And lastly, with the development of computation tools like the TensorFlow or PyTorch, and also the built-in optimization algorithm like stochastic gradient descent or ADAM, when it is more simple than the conventional method that to develop the mathematical software with parallel computing using the neutral networks. In this talk, I will introduce our method to solve the PDEs on unknown manifold by incorporating the diffusion mapping algorithm in the neutral network-based PDE solver. Firstly, the diffusion mapping algorithm is imported to approximate the second-order elliptic differential operator defined on the manifold. And then least square regression problem is formulated to imposing an algebraic equation. And then we will solve the resulting empirical loss function by finding the solution parameterized by the neutral network and using the optimization algorithm like SGD and ADAM. Now we come to our problem setup. We consider manifold M is a d-dimensional bounded and closed submanifold, and let U is the function on the manifold and is also a solution of elliptic PDE. And the formulation of elliptic PDE is in equation 1. And here we use the notation L to denote the differential operator of this term. Here we use the subscript G for the operator defined with respect to the Riemannian matrix G inherited by the M from the ambient space Rn. In our setup, we assume that we did not know the parameterization of the manifold, and we are only given a set of point count data set S, independent and identical distributed according to a measure pi. And here we given point count data of psi n. We have the point Si to S1 to Sn. Now let me introduce the diffusion mapping. The key idea of the diffusion mapping-based PDE software based on the asymptotic expansion. We use the notation G epsilon to represent the convolution of the kernel function H and the function U. And the function H is a exponential decay function, and with the fixed bandwidth parameter epsilon. And we can see in the second equation, we have the asymptotic expansion is equal to this one. And we can see the second term here, they involve a second order derivative in this expansion. And we can use this expansion to approximate the second order derivative in our PDE. And the L definition of this one is the definition of L is this one. And using this asymptotic expansion in the equation 2, we have the approximation of the differential operator L with using the local integration, this one, and have the error up to order epsilon. Now we have this approximation of the differential operator in the elliptic PDE, and now we approximating. We want to get the diffusion mapping discretization on the given point count data. We assume we're given a set of point count data S1 to Sn, and then the discretization of this integral is equal to the matrix W minus the matrix D. To get the matrix W, we can do the following. First, we can approximate the sampling density. Q is equal to d pi over dv, evaluated at the point Si, and the approximating sampling density Qi is equal to the sum average of the kernel function. And then we can define the coefficient for the integration on the manifold W, and each entity Wij is equal to this formula. Once we get this part, and we can divide the matrix D, and the matrix D is a diagonal matrix, and with the ith diagonal component dii is equal to the sum of the ith row of matrix W. So we have get the matrix W and D, and we can get the diffusion mapping discretization L epsilon. Now we have get the diffusion mapping discretization of a differential operator L epsilon, and we can solve get the solution by solving this linear system. And here the liquidity A is a diagonal matrix with the ith diagonal component is equal to the ASI. And L is long is our diffusion mapping discretization, and F is a vector with the ith component is equal to FSI. And then we can solve this linear system to get the solution on the given data point count, point count data. As we point out before, we can only get the solution on the given point count. So we cannot get the solution other than the given point count data. And also here, the size of this matrix is of size n by n. So with the increasing number of the training data n, the matrix size will become larger. So that means solving this linear system will have the computational bottleneck to get the solution. Now let me introduce the neural networks. First is the fully connected neural network, and the formulation of fully connected neural network is equal to the composition of nonlinear function. And here we have L hidden layer, and each hidden layer HL is equal to the composition of nonlinear activation function sigma and in a linear transformation WLS plus BL. Here the NL and NL minus 1 is the width of the hidden layer, and we use the theta to be the set of all the parameters in our neural network. In supervised learning algorithm, we want to approximate the math between the given training data point Si to Yi. So that means we want to find a neutral network phi as parameterized by the theta to approximate this one. And in general, we can use the empirical error defined with the square, mean square of this one. So the parameter of the neutral network can be identified by some optimization algorithm, like we mentioned as ADAM or the stochastic gradient descent. Now let me introduce our hybrid algorithm based on the diffusion mapping and neutral network. And we assume we have given data point count S, and we define a neutral network of phi S parameterized by the theta, and we want to minimize this this objective function. Here, L is long is a parameter is the diffusion mapping discretization on the given point count, and phi theta is a vector, and with the ith component is the neutral network output evaluation of the neutral network on the point Si. And we want to minimize this objective function to obtain the neutral network parameterized by theta. When the A is equal to 0, we will add the regularization term of phi theta, the L2 norm of this one, to guarantee the real polars of the problem. And also, when the mini-batch training is used to minimize the objective function sets, and we will select a subset of the given point count in each training iteration. That means we pick some rows of this differential matrix and also the corresponding entities of the function, the vector f. Now let me go to our theoretical part. And first one, we want to show that our method can give a consistent solution when we have a sufficient training sample and also have the neural network with infinity width or infinity layers. Now we go to our theorem. We assume that the function as is strictly positive and is bounded by two positive number, and we give some assumption on the manifold, and then we can show that with high probability that we have this error estimation. And here the n is the number of training sample, and here the m and the l is the m is related to the width of the neural network, and l is related to the layer of the neural network. Actually, in this error estimation, the first three terms corresponds to the diffusion mapping discretization, and last error is related to the approximation of the neural network. Now we move to next page. We want to show the global convergence of our method, and to establish a more general theorem for our problem, we define the empirical risk Rs with the two-layer neural networks optimized by the gradient descent. And here the empirical risk Rs is defined as the mean square error of given the training data point S. And here A is the matrix of n by n. And in our specific application, A represents the discrete differential operator on the given data point S. And we have a neural network is equal to this one, and here the M represents the width of the neural network. And we consider the activation function is the root of S to the power R. So to build our global convergence theorem, we adopted the neural tangent kernel, and we consider two neural network of this form. And now we first consider we first define the kernel for the parameter ak, k from 1 to m. The kernel for the parameter a is equal to the expectation of GA over the random variable W, and W follows the normal standard normal distribution, and GA is the product of these two functions. And we can get the kernel evaluate on the training sample, and it leads to the n by n grand matrix Ka. We assume that's the smallest eigenvalue of the Ka denoted by lambda s is a positive number, and also the smallest eigenvalue of A transpose. This A is this one is denoted as lambda A is also a positive number. And we can
yes, assume it's time. So hurry up. If you might want to wrap up. It's 20, right? Yeah. So yeah. Anyway, you can wrap up quickly. Yeah.
Okay. So we assume theta 0 is the initialization, and we have the AK and WK initialized by the normal distribution, and we can show that when the width of the neural network is sufficiently large, and we can show that the error, we have obtained the global convergence of the have a global conversion of the empirical laws. Now we will go through 3 numerical examples, and the first example is solving the ellipse PDE, and this one, and we have the on the 2D torus embedded in the R3, and we have the true solution is equal to this one. And because we say because the A of this equation is equal to 0, so we add the penalty term here to guarantee the well-wholeness. Now we define some error here. The first one is forward error to qualify the accuracy of the diffusion mapping, discretization, and inverse error to quantify the accuracy of the approximation by the diffusion mapping. And finally is the testing error. Is the error between the neutral network and the 300 Gaussian quadratic points that is not in the training data set. And we can show that our solution, our result, this is our result, and then testing error can give the conversion solution, and especially when the n is equal to large, when number of training samples is large, our method can still give a solution, but the diffusion mapping algorithm cannot give the solution because it involves a very large, need to solve a very large linear system. Also,
So can you just give a conclusion since you're already over 5 minutes already?
Okay, sorry, and finally we will have example of with diffusion condition, and in conclusion, we have proposed computation frameworks for solving the PD on the manifold, and which is hybrid method based on the diffusion mapping and deep learning. Okay, this is all for my talk, and sorry for the overtime.
Okay, yeah, okay. So due to the time, let's move to the next speaker. So Ichi, can you share screen?
Okay.
So our next speaker is Ichigu. Is from Purdue. In the past, he's a Purdue student. Now he's at University of Hong Kong. So he will give a talk on deep reason method for the spectral fractional Laplacian equation using the CS extension.
Okay. Thank you for inviting me. Thank you for inviting me to this to give this short talk. So this is one of my recent projects in which we solve the fractional Laplacian equation by deep learning. This is a joint work with Michael Ng at the University of Hong Kong. Okay. So in this problem, we let D be the dimension of a problem and let omega be a bounded Lipschitz domain. So our goal is to solve the following fractional Laplacian here. In this equation, we have a negative Laplacian to the power s applied on the solution. Here, the power s is a fractional number between 0 and 1. And the fractional Laplacian is defined by the spectral decomposition of a regular Laplacian. That means if we have the eigenpair for the standard Laplacian, then the fractional Laplacian applied on a function is defined by such a series, the spectral series. And we know it is not easy to solve such a fractional PDE because of a non-local property of such PDE. And if we use traditional PD solvers to deal with it, we will have much more complexity than solving a regular PDE. One popular method to deal with the PD1 is to use so-called Caffarelli-Sylvester extension. That means we can transform the fractional Laplacian 1 to a regular PDE given by the equation 2 here. In this extended problem, we introduce, people introduce one more variable, the scalar variable y. The y is a scalar variable here, and we can formulate such a standard, a regular PDE. And here alpha is set at 1 minus 2s, is also a fraction number between -1 to 1. And the ds is a constant, only depending on s. So the equivalence between 1 and 2 is that suppose u of xy solves 2, then the capital U of x defined by u of x0 is the solution of 1. So it suffices to solve 2, and we take y equals 0, we get a solution for 1. Existing methods are based on this CX extension include the tensor product finite elements and the enriched spectrum method. But it is clear that we have the drawback of using the CX extension is that we have one more dimension, because for example, if we are solving a 2-dimensional fractional Laplacian, if we use a CX extension, we need to solve a 3-dimensional extended problem. And it is difficult to solve a high-dimensional PD by using linear structures like a finite element and polynomials, because they have the degree of freedom of order n to power d, where n is the number of discretization in each direction. So when d is large, it is impossible to use such structures in practice. And in early work, people usually can at most do 2-dimensional examples. So our approach is to overcome this issue is to use a fully connected neural network, FNN, to approximate the solution thanks to its nonlinear structures to adapt to the high-dimensional functions. Okay. So our basic idea is to use the Ritz method. That means we should reformulate the PDE to a minimization problem and find a minimizer of the energy functional. So we transform the CS extended PDE to an equivalent minimization problem. First, we define the solution space. The solution space here is a subspace of the weighted subleft space H1 with weight function y to the power alpha. And we have some boundary condition to control the functions in this subspace. And here, because alpha is a fraction, so actually this this solution space has singularity when y equals 0. And we will deal with this issue later in the architecture of neural network. And next, we define the energy functional I. The energy functional I of W is defined as half times the inner product of half of the norm of gradient W, the weighted norm, minus ds times the integral over omega of f times W of x0. Okay, so this energy function is derived directly from the extended PDE. And we can prove the following result. We can prove that if U in the solution space solves the CS extended PDE, then U should be the minimizer of the energy functional I, or vice versa. So by this result, we can just find the minimizer of the energy functional. Then it plays the role of the solution of the PDE. And we know we can transform such a minimizer problem. We can solve it by deep learning as an optimization problem. Okay, so next, to use a risk method, we need to find a subspace of a solutions. We need to find a subset of a solution space and find a minimizer in the subset. So here we find a subset involving neural networks. We want to design a class of FNNs